to sleepy facts with Justin. Tonight, we are going somewhere very close. Somewhere you have looked at your entire life without ever quite knowing all of its secrets. We are going to the sky above you right now. The atmosphere stretches upward for hundreds of kilometers. It is a vast, layered ocean of invisible air, moving slowly and silently in great currents and gentle eddies. It breathes with the planet. It carries warmth from the equator to the poles. It holds the moisture from every ocean, every river, every quiet lake, and returns it softly as rain. And drifting through all of that, lit by the sun, shaped by the wind, are clouds. You have watched clouds your whole life. You watched them as a child, lying in the grass, finding shapes in the white and gray above you. A rabbit, a mountain, a slow, drifting ship with no particular destination. Clouds have always been there, patient and unhurried, asking nothing of you except that, occasionally, you look up. Tonight, we are going to look up together. We are going to take our time. We are going to move slowly through the science of clouds and the atmosphere. The way a cloud itself moves gently, without rush, following the quiet pull of the wind. There is no need to remember everything you hear. This is not a test. This is simply an invitation to let your mind settle into something soft and fascinating. The way a low mist settles into a valley just before dawn. The science of clouds is in many ways the science of transformation. Water becomes vapor. Vapor becomes droplets. Droplets gather in their millions to form something you can see from the ground. Something so large it casts a shadow on the earth below, and yet each individual droplet, taken alone, is far too small for any human eye to detect. It is invisible. It is almost nothing. And yet, together, those invisible nothings become something magnificent. That is one of the quiet wonders of the atmosphere. Things you cannot see, working together in ways you may never have thought to wonder about, to create the world you look up at every single day. The atmosphere itself is a gift. Without it, the surface of the earth would swing between extremes too harsh for anything to survive. day, unfiltered sunlight would scorch the ground. At night, the cold of space would reach all the way down to the soil, but the atmosphere acts as a great, gentle buffer. It absorbs, it holds, it distributes. It keeps the temperature of the planet within the narrow band that allows rivers to flow and flowers to bloom and people to sleep peacefully beneath a blanket of air 12 kilometers deep. 12 kilometers. That sounds like a great deal, and in some ways it is. But if you imagine the earth as a peach, the atmosphere would be no thicker than the skin of that peach. It is a remarkably thin shell of air, clinging to the surface of the planet by the force of gravity alone, held there as the earth spins through the cold and dark of space. And within that thin shell, everything that matters to the weather happens. Every storm, every gentle breeze, every soft afternoon rain that you have ever watched fall on a garden, every cloud that has ever passed overhead. Tonight, we will move through that shell together. We will begin at the ground and travel upward, layer by layer, until we reach the very edge of the atmosphere, where the air becomes so thin it is barely there at all. And along the way, we will stop to look at clouds of every kind. The low, soft blankets of stratus that sometimes wrap the world in gray, the high, feathery wisps of cirrus that paint themselves across a blue winter sky, the great towering columns of cumulonimbus that build themselves up from the warm ground like living mountains, flickering with lightning inside. We will talk about the tiny, invisible particles that every cloud needs to form. We will talk about the water cycle and the extraordinary journey that a single water molecule makes from the surface of the sea up into the sky, across the face of the continent, and back down again as rain onto a quiet hillside somewhere far from where it started. We will talk about fog and what it means when the cloud comes all the way down to meet you. We will talk about the colors of the sky, the deep blue of a clear afternoon, the amber and rose of a long sunset, the pale silver glow of an overcast winter morning. We will talk about strange clouds, clouds that glow at night, clouds that form in perfect undulating waves, clouds that look like they belong to another world entirely. And we will talk about clouds on other planets, because the atmosphere of Earth is not the only one worth knowing about. But we will do all of this slowly. There is no hurry here. Tonight, you are comfortable. You are warm. Your body is at rest. And your mind is welcome to drift along with the words. The way a leaf drifts along the surface of a slow river, turning gently, going nowhere in particular, simply carried by the current. If you fall asleep before we reach the end, that is not a failure. That is the point. The facts will be here tomorrow, and the night after that, and the clouds will still be forming in the sky above you, building themselves out of nothing, one invisible droplet at a time. So let your shoulders drop. Let the weight of the day begin to lift. Let your breathing slow just a little, the way the air slows in the hour before dawn, when the world is perfectly still and the sky is just beginning to lighten at its edges. The atmosphere is above you now. The clouds are drifting. We begin. The atmosphere is all around you. Right now, as you lie still and let your breathing slow, the atmosphere is pressing gently against every surface of your body, not heavily, not uncomfortably, just a quiet, constant, invisible presence. The weight of a column of air reaching all the way up to the edge of space, resting lightly on your skin. You never notice it. You were born into it. You have spent every moment of your life surrounded by it. And yet, if you were somehow lifted out of it, even just a few kilometers above where you are right now, the change would be immediate and profound. The air would thin, breathing would become difficult. The cold would deepen. The familiar blue of the sky would begin to darken toward something much closer to black. The atmosphere is not something separate from life on Earth. It is part of life on Earth. It is woven into every breath, every weather pattern, every sunrise and sunset. It is the medium through which sound travels to your ears. It is the reason the sky has a color at all. So, what exactly is it? In the simplest terms, the atmosphere is a mixture of gases that surrounds the Earth held in place by gravity. It has no hard boundary. It does not end at a particular line, the way the surface of the ocean ends at the shore. Instead, it simply grows thinner and thinner the higher you go, until eventually the molecules of gas are so far apart that the concept of an atmosphere no longer quite applies. Space begins not with a wall, but with a gradual fading away. The mixture of gases that makes up the atmosphere is remarkably consistent, at least in the lower portions where weather happens. Roughly 78 parts in every 100 are nitrogen. Just over 20 parts in every 100 are oxygen, the part that living things breathe and depend upon. The remaining fraction is a collection of other gases: argon, carbon dioxide, neon, helium, methane, and others, each present in tiny amounts, each playing its own quiet role in the chemistry of the sky. Nitrogen is the great, steady background of the atmosphere. It does not burn. It does not react easily with other things. It simply fills the space, diluting the oxygen to a concentration that is useful for life without being overwhelming. Pure oxygen, breathed for long periods, is actually damaging to the body. Nitrogen keeps it gentle, keeps it breathable, keeps it just right. Oxygen, of course, is the gas that makes the work of living possible. Every cell in your body right now is using oxygen to release energy from the food you have eaten. The process is quiet and continuous. It happens without any effort from you at all. Your body simply takes what it needs from the air around it, and the atmosphere, vast and generous, provides it without ever running short. Carbon dioxide makes up only a small fraction of the atmosphere, roughly 4 parts in every 10,000. That sounds like almost nothing. And in terms of sheer volume, it is. But carbon dioxide has an outsized influence on the temperature of the planet. It absorbs heat that would otherwise escape into space and radiates some of that heat back toward the surface. This is the greenhouse effect. And without any of it at all, the Earth would be far too cold for the life that exists here now. Carbon dioxide is, in the right amounts, part of what makes the planet comfortable. Water vapor is another critical component of the atmosphere. Though its concentration varies enormously from place to place and from day to day. In a hot, humid environment near a tropical coast or above a warm ocean, water vapor might make up as much as 4 parts in every 100 of the local air. In a cold, dry desert or high on a mountain peak, it might be almost absent entirely. Water vapor is the raw material from which clouds are made. It is the invisible precursor to every drop of rain, every snowflake, every morning dewdrop on a blade of grass. The atmosphere also contains particles, not gases, but tiny solid or liquid fragments suspended in the air. Dust from desert winds, salt crystals lifted from the surface of the sea, pollen from flowering plants, ash from distant volcanoes, soot from fires. These particles, collectively called aerosols, play a more important role in the life of clouds than most people ever consider. They are, in a very real sense, the seeds around which clouds grow. Without them, clouds as we know them could not form at all. The total mass of the atmosphere is an almost incomprehensible number, approximately 5.1 times 10 to the power of 18 kilograms, 5 million trillion kilograms of air, pressing down on the surface of the planet. And yet, distributed across the entire surface of the earth, that translates to a pressure of about 1 kilogram per square centimeter at sea level, something your body has been built to handle without ever thinking about it. Pressure changes with altitude. The higher you go, the less air there is above you, and so the lower the pressure. Climbers ascending very high mountains carry oxygen, not because oxygen becomes rarer relative to other gases. The proportion stays roughly the same, but because the total amount of air in each breath decreases, there is simply less atmosphere to breathe from. The mountain does not change the recipe. It just reduces the portion size. The atmosphere also has temperature gradients, regions where the air grows colder as you rise, and then, unexpectedly, warmer again. These temperature changes are not random. They are the result of different atmospheric layers, absorbing different kinds of energy from the sun and from the earth below. The layers of the atmosphere are like the layers of a very complicated, very slow-moving system of currents and boundaries, each one with its own character and its own relationship to the energy flowing through it. Those layers are where we are going next. But for now, simply rest with this. The atmosphere is not empty. It is not nothing. It is a rich, complex, living mixture of gases and particles and water, moving constantly, changing with the seasons and the time of day, shaped by the land and the ocean below it and the sun above it. It is the sky you have always known. And tonight, you are beginning to understand it a little more deeply. Let that thought settle quietly, the way dust settles through still air slowly, gently, without any particular hurry. The atmosphere is not one single thing. It is not a uniform blanket of air, the same from the ground all the way up to the edge of space. It is layered, stratified. Each layer has its own temperature, its own chemistry, its own relationship with the energy that flows through it. Scientists have given each layer a name, and each name tells a small story about what that layer does and where it sits. Think of it like a very deep, very still lake. At the surface, the water is warm and full of life and movement. Further down, the temperature drops and the pressure increases and the light fades. Deeper still, things become very cold, very dark, very quiet. The atmosphere is something like that, a series of distinct zones, stacked on top of one another, each one fading gradually into the next. We begin, as we always do, at the bottom. The lowest layer of the atmosphere is called the troposphere. This is where you live. This is where the weather happens. Every cloud you have ever seen formed in the troposphere, every storm, every gentle afternoon rain, every still and foggy morning, all of it takes place within this single layer, the one closest to the ground. The troposphere extends from the surface of the earth to a height of approximately 8 kilometers above the poles. and about 16 kilometers above the equator. The difference in height is caused by the rotation of the Earth and the greater warming of the atmosphere near the equator, which pushes the upper boundary of the troposphere higher in the warmer regions of the planet. Within the troposphere, temperature decreases as you climb. For roughly every kilometer you ascend, the air cools by about 6 to 7 degrees Celsius. This cooling is what drives so much of the weather we experience. Warm air near the surface rises, cools as it climbs, and eventually reaches a point where the water vapor it carries condenses into droplets. That is the moment a cloud begins to form, and we will explore that process in wonderful, unhurried detail in the sections ahead. At the very top of the troposphere is a thin boundary layer called the tropopause. It is the ceiling of the weather world. Above it, the ordinary rules of the lower atmosphere no longer apply. The temperature stops falling. The air becomes very dry, and the great churning, swirling weather systems of the troposphere can go no further. They spread out sideways when they reach the tropopause, like a river reaching the sea. Above the tropopause lies the stratosphere. The stratosphere is a very different kind of place. It is cold at its base, around minus 56 degrees Celsius, but it actually warms as you go higher. This is the opposite of what happens in the troposphere. The reason is ozone. The stratosphere contains a layer of ozone molecules that absorbs ultraviolet radiation from the sun, and that absorption generates heat. The upper stratosphere, far from being colder than the lower stratosphere, is actually significantly warmer. This warming from above rather than below makes the stratosphere extremely stable. There is very little vertical mixing. Air parcels do not rise and fall the way they do in the turbulent troposphere. The stratosphere is calm and layered and still. Jet aircraft often cruise in the lower stratosphere precisely because of this stillness. Above the weather, in smooth and predictable air, the ozone layer within the stratosphere is one of the most important features of the entire atmosphere. It absorbs most of the ultraviolet radiation the sun sends toward Earth radiation that, in large doses, damages living tissue and disrupts the chemistry of life. The ozone layer is, in effect, a shield, a slow, invisible, protective layer of molecules doing quiet and vital work, high above where any cloud can reach. The stratosphere extends from the tropopause up to approximately 50 kilometers above the Earth's surface. Above it lies another boundary, the stratopause, and above that, the next layer begins. The mesosphere is where the atmosphere starts to feel genuinely thin. It sits between roughly 50 and 85 kilometers above the surface, and within it, temperature falls again as altitude increases back to the pattern of the troposphere, but in a much emptier sky. At the top of the mesosphere, temperatures can drop to around minus 90 degrees Celsius, making it the coldest part of the entire atmosphere. The mesosphere is too high for aircraft and too low for satellites, which means it is one of the least studied and least understood regions of the atmosphere. It is a gap in our knowledge, as well as a gap in the sky. And yet, something remarkable happens there. When meteors enter the Earth's atmosphere, they burn up in the mesosphere. The streaks of light you see on a clear, dark night, what people call shooting stars, are the last moments of those visitors from space, burning away in the cold, thin air of the mesosphere, leaving a brief and beautiful trace. There is also a rare and extraordinary kind of cloud that forms in the mesosphere. These are called noctilucent clouds, and we will meet them properly in a later section when we explore the strangest and most unusual clouds that the atmosphere produces. For now, it is enough to know that even at the very edge of the cloud-forming world, there are still wonders to be found. Above the mesosphere is the thermosphere. Here, the rules change entirely. The thermosphere extends from about 85 kilometers to somewhere between 500 and 1,000 kilometers above the surface, and within it, temperatures rise dramatically, potentially to thousands of degrees Celsius. But those temperatures are misleading. The air in the thermosphere is so thin that there are almost no molecules present at all. Temperature in the conventional sense, is a measure of how fast molecules are moving. In the thermosphere, the molecules move very fast, but there are so few of them that a human body would actually feel intensely cold there. There is not enough matter to transfer heat. The International Space Station orbits within the thermosphere. Auroras, the northern and southern lights, those shimmering curtains of color that appear near the poles on clear winter nights, also occur in the thermosphere when charged particles from the sun interact with the atoms of the thin air there. The thermosphere is where the Earth's atmosphere reaches up towards space, and where space reaches back down. Beyond the thermosphere lies the exosphere, the outermost layer, where individual molecules of hydrogen and helium occasionally escape the planet's gravity altogether and drift away into space. The exosphere has no clear upper boundary. It simply becomes, eventually, indistinguishable from the void between worlds. So that is the atmosphere from bottom to top. The turbulent, cloud-filled troposphere, the stable, ozone-rich stratosphere, the cold and poorly understood mesosphere, the vast and near-empty thermosphere, and the gradually dissolving exosphere, where the Earth finally lets go. We will be spending most of our time tonight in the lowest of those layers, the troposphere, the place of weather and clouds and rain, the place where you are right now, breathing slowly and drifting towards sleep. The layers above are extraordinary, but they are distant. The troposphere is close. It is intimate. It is the sky you see every day when you look up from wherever you happen to be standing. And in that sky, right now, clouds are forming. Let that thought carry you gently forward, like a slow current of warm air rising from the sun-warmed ground. Every cloud begins with something invisible, not with a drop of water you could see, or a crystal of ice you could hold. It begins with water vapor, a gas, completely transparent, woven invisibly into the air around you. You cannot see it. You cannot feel it directly. And yet it is there, in every breath you take, in every room you inhabit, in every cubic meter of air above the ground. waiting for the right conditions to transform into something you can look at. The transformation from invisible vapor to visible cloud is one of the quietest and most continuous processes on the face of the earth. It is happening right now, somewhere above you. It has been happening every day of your life, and it follows the same patient logic every time, in every corner of the world, in every season and every climate. It begins with warmth. When the sun shines on the surface of the earth, on the ocean, on a lake, on a forest, on a field of grass still wet with dew, it transfers energy to the water at the surface. That energy causes water molecules to move faster, to vibrate with increasing intensity, until some of them break free from the liquid surface entirely and drift upward into the air as vapor. This is evaporation. It is happening right now from every wet surface on the planet, quietly and continuously, lifting water from the ground and the sea and sending it upward into the sky. The air, once it receives this water vapor, carries it upward. Warm air is less dense than cool air. It is lighter, and it rises. Imagine a parcel of air near the surface, warmed by the sun, carrying a cargo of invisible water vapor. It begins to lift, slowly at first, then more steadily, rising away from the ground the way a soap bubble rises from a child's hand. Gently, inevitably, following the laws of physics with perfect obedience. As it rises, something important begins to happen. The air parcel cools. This cooling is not caused by the surrounding air stealing warmth from the parcel. It is caused by expansion. As the parcel rises, the atmospheric pressure around it decreases. There is less weight of air above it pressing down. In response, the parcel expands slightly. And when a gas expands, it cools. This is a fundamental property of gases, and it is the engine that drives cloud formation. The parcel of rising air cools at a remarkably steady rate, roughly 10 degrees Celsius for every kilometer it climbs. As long as no condensation is occurring, scientists call this the dry adiabatic lapse rate. It sounds technical, but the idea is beautifully simple the air rises, the air expands, the air cools, and as it cools, it approaches a very important threshold. That threshold is called the dew point. The dew point is the temperature at which air becomes saturated with water vapor. The point at which it can no longer hold all the vapor it contains in its invisible gaseous form. When the air cools to its dew point, the water vapor has no choice but to begin changing phase. It transitions from a gas into tiny liquid droplets. This process is called condensation, and it is the birth moment of every cloud. You have seen condensation countless times. It is what happens when a cold glass of water sits in a warm, humid room and water appears on its outer surface, not from the water inside, but from the moisture in the surrounding air, which has been chilled below its dew point by contact with the cold glass. It is what happens to a mirror in a steamy bathroom. It is what forms the morning dew on grass and leaves and spider webs in the quiet hour before sunrise. In the sky, condensation happens in the same way, but on an almost incomprehensible scale. Millions upon millions of tiny water droplets form simultaneously, each one far too small to see individually, each one beginning to gather with its neighbors into something that grows and thickens and becomes, over the course of minutes or hours, a visible cloud. The altitude at which a rising parcel of air reaches its dew point, the altitude at which condensation begins, is called the lifting condensation level. And here is something rather beautiful about it. On a clear day, when you look at a sky scattered with small, puffy cumulus clouds, you will notice that their flat bases are all at roughly the same height. Every single one of them, different clouds, different sizes, different shapes, but the same flat bottom, all lined up at the same altitude. That shared altitude is the lifting condensation level. It is the height at which the rising parcels of air in that region have cooled to their dew point. The flat base of a cumulus cloud is the visible mark of an invisible threshold in the sky, a line where vapor becomes water, where invisible becomes visible, where nothing becomes something. There is something deeply satisfying about that. A line you can see from the ground, drawn across the sky by the physics of moisture and temperature, as precise and reliable as any measurement taken in a laboratory. But condensation does not happen in perfectly clean air on its own. Water vapor does not simply decide, upon reaching the dew point, to spontaneously form droplets in empty space. It needs a surface, something to condense onto, and this is where one of the most fascinating and overlooked characters in the story of clouds makes its entrance. In absolutely pure air, with no particles of any kind, water vapor would need to be cooled far below the normal dew point before droplets would form at all. This is called supersaturation, and while it can occur in controlled laboratory conditions, it is not what typically happens in the real atmosphere. In the real atmosphere, the air is full of tiny particles, particles of dust, lifted from dry soils by the wind, particles of sea salt thrown into the air when waves break on the ocean surface, pollen from trees and grasses, ash from wildfires and volcanic eruptions, even bacteria carried aloft by rising air currents. These particles are called condensation nuclei, and they are the surfaces onto which water vapor condenses to form the first tiny droplets of a cloud. Without condensation nuclei, the sky would be a very different place. Clouds would be rarer, harder to form, requiring much more extreme conditions before they could begin. But in the real, particle-rich atmosphere we inhabit, condensation nuclei are always present, always available, always ready to serve as the seed around which a droplet can grow. A single cloud droplet, newly formed around its condensation nucleus, is extraordinarily small. It might be 10 to 20 micrometers across, a micrometer being 1/1,000,000th of a meter, something so small that a single raindrop contains roughly 1,000,000 of these droplets. They are almost impossibly tiny, and yet, gathered in their billions and trillions within a cloud, they are enough to scatter the sunlight and give the cloud its white, and luminous appearance. The white of a cloud is the white of scattered light. The droplets within it are just the right size to scatter all wavelengths of visible light roughly equally. Red, orange, yellow, green, blue, all bounced in every direction. And the result is the bright, neutral white that you see when you look up at a young cumulus on a sunny afternoon. As the cloud thickens and deepens, the droplets inside it become more numerous, and the cloud becomes better at absorbing the light rather than simply scattering it. This is why thick clouds are gray at their base, not because they contain different water, but because less light penetrates through them. The deeper the cloud, the darker its underside appears from below. A cumulonimbus, towering to great heights, can have a base that looks almost black, not from any darkness within it, but from the sheer depth of cloud above. All of this, the evaporation, the rising air, the cooling, the dew point, the condensation nuclei, the gathering droplets, happens every day in every part of the world, at every altitude where the conditions are right. It is ordinary. It is routine. It is unremarkable in the sense that it never stops, never pauses, never fails to follow the same beautiful logic. And yet, when you look up and see a cloud drifting slowly across the blue, knowing what you now know about how it came to be there, it becomes something else entirely. It becomes evidence, visible proof of invisible forces, a record written in water of the temperature and moisture of the air at a particular height, at a particular moment. A cloud is the atmosphere thinking out loud. Let that settle softly over you, like the shade of a cloud, passing gently across the sun, cool, quiet, and gone before you quite notice it has happened. Yet a dot in every cloud, no matter how large or how small, no matter how high or how low, there is a secret at its heart. Not one secret, billions of them, billions of tiny, invisible particles, each one so small that hundreds of them could fit side by side across the width of a single human hair, each one sitting quietly at the center of a water droplet, the seed around which the droplet first formed. Without these particles, the cloud would not exist. these particles, the sky above you would be a very different sky indeed. These particles are called condensation nuclei, and tonight we are going to spend some time with them because they deserve it. They are one of the most overlooked and underappreciated characters in the entire story of the atmosphere, small beyond imagining, present in extraordinary numbers, and absolutely essential to the world of clouds and weather that shapes life on this planet. The word nucleus comes from the Latin word for kernel, the seed inside a fruit, the central thing around which everything else is arranged. A condensation nucleus is exactly that. It is the kernel of a cloud droplet. The first thing, the point of beginning. When water vapor in the atmosphere cools to its dew point and begins to condense, it does not form droplets in empty space. It forms them on surfaces, and in the atmosphere, the surfaces available are these tiny airborne particles, countless in number, diverse in origin, carried by the wind from every corner of the earth. Where do they come from? They come from everywhere. They come from the surface of the ocean, where breaking waves and the bursting of tiny bubbles throw microscopic droplets of salt water into the air. As the water in those droplets evaporates, it leaves behind a tiny crystal of sea salt, a perfect condensation nucleus, soluble in water, eager to attract moisture. Sea salt particles are among the most effective condensation nuclei in the atmosphere. They are hygroscopic, meaning they actively attract water molecules, beginning to absorb moisture even before the air has reached its official dew point. Clouds that form over the ocean, seeded by sea salt, can begin to develop at relatively low levels of humidity. They come from the soil. Wind passing over dry land picks up fine particles of dust and carries them aloft. Saharan dust is carried by the trade winds across the Atlantic Ocean and deposited as far away as the Amazon rainforest and the Caribbean islands. Some of it reaches altitudes of several kilometers, riding the great rivers of air that flow between continents. Desert dust particles are abundant, widespread, and among the most important condensation nuclei in the global atmosphere. They come from fires. When wood burns, whether in a forest fire, a cooking fire, or a field being cleared for planting, it releases enormous quantities of tiny particles of smoke and soot into the air. These combustion particles are extremely small and extremely numerous. A single forest fire can inject billions upon billions of particles into the atmosphere. They rise on the heated air above the fire, spread outward on the wind, and travel sometimes for thousands of kilometers before eventually settling back to the surface. Along the way, they serve as condensation nuclei, influencing cloud formation far from their origin. They come from volcanoes. A major volcanic eruption can inject sulfur dioxide gas high into the stratosphere, where it reacts with water vapor and other compounds to form tiny droplets of sulfuric acid. These aerosol droplets can remain in the stratosphere for months or even years, spreading around the entire planet, affecting the reflectivity of the atmosphere and occasionally influencing cloud formation in the upper troposphere. When they descend from above, they come from plants. Many trees and other vegetation release volatile organic compounds into the air as part of their normal chemistry. Compounds that react with other gases in the atmosphere to form tiny secondary aerosol particles. The blue haze that sometimes hangs over forested mountain ranges, the kind of haze that gives the Blue Ridge Mountains their name, or gives the Blue Mountains of Australia their particular soft color, is in part a product of these plant-derived aerosols, catching and scattering the light. They come from human activity, power stations, factories, vehicles, heating systems, agricultural practices. All of these release particles and particle-forming gases into the atmosphere in quantities that have measurably changed the aerosol content of the air in many parts of the world. These human-produced aerosols interact with clouds in ways that scientists are still working to fully understand. And in very small numbers, they come from space. Tiny fragments of meteors, ground to dust by their passage through the upper occasionally serve as condensation nuclei in the highest and coldest regions of the troposphere and mesosphere. The diversity of condensation nuclei in the atmosphere is remarkable. They differ in size, in chemical composition, in solubility, in their ability to attract water, and those differences matter enormously for the character of the clouds they help to create. A cloud that forms over the ocean, seeded primarily by sea salt particles, tends to contain relatively large droplets. Because sea salt is so effective at attracting water that each nucleus accumulates a great deal of moisture around it. When there are fewer nuclei and more water vapor per nucleus, each droplet grows larger. A cloud that forms over a polluted city, where the air contains far more particles than over the clean ocean, tends to contain many more, but much smaller droplets. The same amount of water vapor is distributed across a much larger number of condensation nuclei. So each one gets a smaller share. Smaller droplets are less likely to collide and merge into raindrops. This is one of the reasons that heavily polluted air can actually suppress rainfall. Not because the cloud contains less water, but because that water is divided into droplets too small and too numerous to easily fall as rain. This relationship between aerosols and clouds, the way that the number and type of condensation nuclei affects the size of cloud droplets, the brightness of clouds, and their likelihood of producing precipitation, is one of the most actively studied areas of atmospheric science. It matters enormously for our understanding of how the climate system works and how human activity is changing it. Clouds reflect sunlight back into space, and their reflectivity, their brightness, is affected by the size of the droplets they contain, which is affected by the aerosols that seed them. More aerosols, smaller droplets, brighter clouds, more sunlight reflected. Fewer aerosols, larger droplets, somewhat less bright clouds, more rainfall. The chain of consequences flowing from a single tiny particle is long and surprising, but let us not think too hard about chains of consequences tonight. Let us simply rest with the wonder of the thing itself. The idea that every cloud, every white, softly drifting shape in the sky above you carries within it, at the heart of every single droplet, a particle from somewhere else entirely, a fragment of the Sahara, a crystal of ocean salt, a piece of smoke from a fire on the other side of the world, a trace of something once alive. Clouds are not made of water alone. They are made of the whole world, gathered together at altitude, transformed into something luminous and temporary and quietly beautiful. Think of that the next time you watch a cloud move slowly across a blue sky. Somewhere inside it, invisible, essential, patient, are the seeds from which it grew. Each one a traveler, each one a messenger from somewhere else, carried on the wind to exactly this place, at exactly this moment, to do exactly this quiet and necessary work. The air above you is full of travelers tonight. They drift on invisible currents. They carry moisture on their surfaces. They wait with infinite patience for the air to cool just enough, and when it does, they become the heart of something you can see from the ground. Let that image drift through your mind now, softly and without effort, the way a particle of dust drifts on a slow current of warm air, going nowhere in particular, simply carried by the gentle movement of the sky. Water never stays in one place for long. It moves. It transforms. It travels across continents and between oceans and through the bodies of living things, always cycling, always returning, always finding its way back to somewhere it has been before. The water in the glass on your bedside table has been a glacier, an ocean, a cloud, a raindrop, a river, and the cell of some long-extinct creature whose name we will never know. It has been all of those things, and it will be all of them again. The movement of water through the earth system, from the surface to the sky and back again, is called the water cycle, or, if you prefer the more formal name, the hydrological cycle. Hydrological, from the Greek word for water. It is one of the most fundamental processes operating on this planet, and it has been running without pause for billions millions of years, long before there were clouds as we would recognize them, long before there was any life to observe it. The water cycle was turning quietly and continuously through deep time. Tonight, we are going to follow that cycle. We are going to begin at the surface of the ocean, the starting point of most of the water that eventually becomes a cloud, and trace the journey of water from there, upward into the sky, and eventually back down to the ground. It begins with the sun. The sun is the engine of the water cycle. Its energy strikes the surface of the ocean, and the ocean covers roughly 71 parts in every 100 of the Earth's surface, and transfers heat to the water molecules at the very top. Those molecules, energized by the sunlight, begin to move faster. Most of them stay in the liquid, but some of them, the fastest moving ones, the ones that happen to be at the surface and pointing in the right direction, break free. They escape the pull of the surrounding water and drift upward into the air as vapor. This is evaporation. It is happening right now, all across the world's oceans, at a rate that is almost impossible to picture. Every single day, somewhere in the region of 430 cubic kilometers of water evaporates from the ocean's surface and enters the atmosphere. 430 cubic kilometers. That is enough water to fill Lake Superior, one of the largest lakes on Earth, more than 3 times over. Every day, the vast majority of the water vapor in the atmosphere at any given moment came from the ocean. The ocean is the source, the great reservoir from which the sky continuously draws its moisture. But evaporation happens everywhere there is liquid water, from lakes and rivers, from wet soil after rain, from puddles on streets and water on leaves, and the surface of every swimming pool and every flooded field, even from snow and ice. Water can evaporate directly. The process is called sublimation, and it is why snow on a cold, sunny, dry day can disappear without ever visibly melting. Plants also contribute to the water vapor in the atmosphere through a process called transpiration. Plants draw water up from the soil through their roots, use it in their internal chemistry and release excess water vapor through tiny pores in their leaves called stomata. A single large tree can transpire hundreds of liters of water on a warm summer day. A forest transpires so much water that it measurably increases the humidity of the air above it, and can even generate its own rainfall. The combination of evaporation from water surfaces and transpiration from plants is sometimes given a single name: evapotranspiration, because in practice, when scientists are measuring the movement of water from the land surface into the atmosphere, it is difficult to separate the two processes precisely. Once water vapor has entered the atmosphere, it is carried by the wind. Wind is the great transporter of the water cycle. It moves moisture from the ocean to the land, from warm regions to cold, from the equator toward the poles. The winds that blow across the surface of the ocean pick up moisture and carry it inland, sometimes for thousands of kilometers, sometimes rising over mountain ranges, sometimes descending into valleys, always moving, always redistributing. As the water vapor travels with the wind, it is also rising and falling with the movements of air masses. When it rises, carried upward in a column of warm, buoyant air, or forced upward when it encounters a mountain range or a cold front, it begins to cool, and as we explored in our last section, cooling air eventually reaches its dew point, and condensation begins, and a cloud forms. The cloud is a temporary gathering, a pause in the journey. The water vapor, which has been invisible and scattered across a wide volume of air, is now concentrated into tiny droplets clustered together in a visible mass. It has changed its form, but not its destination. Eventually, the droplets in the cloud will grow large enough to fall. The cloud will produce precipitation, rain or snow or hail or drizzle, and the water will return to the surface. This return is called precipitation, and it is the downward leg of the water cycle. Precipitation falls over the ocean, where most of it simply rejoins the water from which it came. Precipitation falls over the land, where it has a more varied fate. Some of it falls onto vegetation and is intercepted by leaves and branches, caught before it ever reaches the soil. Some of that intercepted water evaporates back into the air almost immediately. Some of it drips from the leaves and reaches the ground. Some precipitation soaks into the soil. It becomes soil moisture, available to plant roots. Some of it percolates deeper still, seeping downward through rock and sediment until it reaches an underground reservoir, an aquifer, where it may remain for years or decades or centuries, stored in the dark beneath the surface. Some of it runs across the surface as runoff, gathering into streams, flowing into rivers, finding its way back toward the ocean. A water molecule that falls as rain on a mountain might spend several days traveling down a river before it reaches the sea, where it will evaporate again and begin its journey anew. And some precipitation falls as snow and accumulates in glaciers and ice sheets and snowpacks on mountain slopes. This frozen water is stored for much longer. The ice sheets of Antarctica and Greenland contain water that has been frozen for hundreds of thousands of years. Water that last fell as snow in a world very different from this one, long before any human being had drawn a breath. That ancient water is part of the water cycle too, locked away for now, but not permanently. Glaciers flow slowly toward the sea. Ice shelves calve icebergs that drift and melt. The frozen water, in its own slow time, returns. The water cycle has no beginning and no end. It is a circle, continuously turning. But it is not a simple circle. It is more like a great web of circles, nested within one another, operating at different speeds. The quick cycle of evaporation from a puddle on a summer morning and condensation into a cloud that same afternoon. The slower cycle of river water, traveling for weeks from mountain to sea. The very slow cycle of deep groundwater, moving through rock at the pace of centimeters per year. The ancient cycle of glacial ice, locked for millennia and then released. All of these cycles are happening simultaneously. Everywhere on Earth, time. The water above you tonight has been moving through these cycles since long before your birth, and will continue to move through them long after everything you know has changed beyond recognition. There is something quietly comforting about that. The water in the air around you right now, invisible, patient, carried on the slow breath of the atmosphere, is ancient. It has made this journey before, many times, across many thousands of years, and it is making it again tonight, above your rooftop, above your neighborhood, above the city and the fields and the coastline, rising, cooling, gathering, falling, flowing, rising again. The cycle turns, the atmosphere breathes, and somewhere above you, water vapor is cooling to its dew point, and the first tiny droplets of a new cloud are forming around their invisible seeds. Let the image of that slow, patient cycle carry you gently into stillness, the way a river carries a leaf, not hurrying, not pulling, simply moving forward at its own natural pace, toward somewhere quiet and still. Clouds come in an extraordinary variety of shapes and sizes. Walk outside on any given day and look up, and the sky will show you something different from what it showed you yesterday. Low gray sheets softening the light to a silver haze, tall white towers building themselves upward into the afternoon. Thin, delicate strands of white drawn across a deep blue sky, like the brush strokes of some patient, unhurried artist. Layers of small rounded puffs arranged in long rows, like the scales of a fish or the ripples on a sandy beach. For most of human history, people looked at this variety and saw it as beautiful and mysterious and largely unpredictable. Clouds were watched for signs of coming rain, of clearing weather, of a good day for sailing or planting or travel. But they were not systematically classified. They were not given names that connected one cloud to another, that placed each type within a broader understanding of how and where and why clouds form. That changed in the early 19th century, in the quiet hours of a London drawing room, when an amateur meteorologist and pharmacist named Luke Howard sat down and did something that seems simple in retrospect, but was, in fact, a small act of scientific genius. He looked at all the different clouds he had ever seen, and he sorted them into groups. He gave each group a name, a Latin name, chosen for its descriptive precision. And in doing so, he gave humanity a language for the sky. Luke Howard presented his cloud classification to the Askesian Society of London in the year 1802. He proposed 3 fundamental cloud forms, from which all others could be understood as combinations or variations. The first he called cirrus, from the Latin word for a lock of hair, or a curl, or a wisp. Cirrus clouds are high, thin, and delicate, drawn-out strands of ice crystals, barely there, more like a suggestion of cloud than a cloud itself. The second he called cumulus, from the Latin word for a heap or a pile. Cumulus clouds are the round, puffy clouds of fair weather, the ones children draw, the ones that sit on a flat base and billow upward in soft white mounds. The third he called stratus, from the Latin word for a layer or a blanket. Stratus clouds are flat and featureless, wide sheets of cloud that cover the sky evenly, without texture or definition, like a ceiling drawn across the world. And to describe clouds that were actively producing precipitation, rain, or snow, he used the word nimbus, from the Latin for a rain cloud or a storm cloud. A cloud that rains is a nimbo-something, or a something nimbus, from these 4 root words: cirrus, cumulus, stratus, nimbus. The entire modern classification of clouds is built. Every cloud type you will ever hear named is a combination or a variation of these 4 roots, describing the cloud's shape, its height, and its relationship to precipitation. The World Meteorological Organization, which maintains the current international standard for cloud classification, organizes clouds primarily by the altitude at which they form. There are 3 broad altitude ranges: low, middle, and high. And within each range, certain types of clouds are found. High clouds form at altitudes above approximately 6 kilometers in the cold upper reaches of the troposphere, where temperatures are well below freezing. clouds are made primarily of ice crystals rather than liquid water droplets. The prefix for high clouds is cirro, from Howard's original cirrus. High clouds tend to be thin and white and translucent. They let sunlight through rather than blocking it. They are the most delicate of all cloud forms and some of the most beautiful. Middle clouds form between roughly 2 and 6 kilometers above the surface. The prefix for middle clouds is alto, from the Latin word for high, which can be a little confusing, since these are the middle clouds, not the highest, but the naming reflects historical usage rather than strict logic. Middle clouds can be made of liquid water droplets, ice crystals, or a mixture of both, depending on the temperature at the altitude where they form. Low clouds form below roughly 2 kilometers, sometimes far lower than that, sometimes right down at the surface of the earth itself, at which point they become fog. Low clouds have no special prefix. They are simply named for their form: stratus, stratocumulus, nimbostratus. And then there are clouds that do not fit neatly into a single altitude band. Clouds that extend vertically through multiple layers, growing upward from a low base into the middle, or even high atmosphere. These are the convective clouds, cumulus and cumulonimbus, and they deserve their own category because their vertical extent is as important as their height. The full list of cloud genera, the basic types recognized by the World Meteorological Organization, contains 10 members. At high altitudes, there are 3 genera: cirrus, the thin, wispy streaks; cirrocumulus, a delicate layer of tiny rounded puffs, like the finest, most detailed of all cloud textures; and cirrostratus, a thin, widespread veil of cloud that often covers the entire sky and produces a pale, milky look, sometimes with a halo around the sun or moon. At middle altitudes, there are 2 genera: altostratus, a gray or blue-gray layer of cloud, thick enough to obscure the sun and often the precursor to rain; and altocumulus, a layer of rounded cloud masses, larger than cirrocumulus, but smaller and more delicate than stratocumulus, often arranged in waves or rows. At low altitudes, there are three genera: stratus, the flat, gray, featureless sheet; stratocumulus, the most common cloud type on Earth, a lumpy, rolling layer of low cloud that covers much of the planet's surface on any given day; and nimbostratus, the thick, dark, rain-producing layer cloud, the cloud of a long, steady, gray, rainy day. And crossing altitude boundaries, the two vertical clouds, cumulus, the familiar fair-weather puff, with its flat base and its rounded, cauliflower-like top; and cumulonimbus, the great storm cloud, extending from low in the atmosphere, sometimes all the way to the tropopause, generating lightning and thunder and heavy rain and hail, 10 genera. But within those 10, there are further subdivisions, species, varieties, supplementary features, accessory clouds, that describe more precisely the shape, the internal structure, the arrangement, and the special characteristics of individual cloud formations. The full International Cloud Atlas, maintained by the World Meteorological Organization, runs to hundreds of pages and contains descriptions and photographs of clouds in almost infinite variation. There are species names: fibratus, for clouds with long, thin, fibrous strands; uncinus, for cirrus clouds with a hooked or comma-shaped curl at their end, sometimes called mare's tails, because in a certain light they do look remarkably like the long tail of a horse, sweeping across the sky; lenticularis, for clouds with a smooth, lens-shaped form, often found near mountains, sometimes mistaken for other things entirely; fractus, for clouds with ragged, broken edges, as though torn by the wind. There are variety names: undulatus, for clouds arranged in waves; radiatus, for clouds arranged in parallel bands that appear to converge at a point on the horizon; vertebratus, for clouds arranged in a pattern resembling a fish spine; lacanosus, for clouds with regularly spaced holes or gaps, like a net or a honeycomb. Each name is a description. Each name tells you something about how the cloud formed, what the air is doing inside and around it, what the atmosphere is feeling in that particular place at that particular moment. Luke Howard, sitting in London in the early years of the 19th century, could not have imagined all the detail and nuance that his simple framework would eventually support. He gave science 4 words, and science, over the following 2 centuries, built from those 4 words an entire vocabulary for the sky, a language precise enough to be useful and rich enough to capture something of the genuine beauty and variety of clouds in all their forms. You already know some of that language. You have always known it. Cumulus, cirrus, storm cloud, fog. You have used these words, or words like them, without perhaps knowing that they connect you to a tradition of observation that stretches back more than 200 years, to a quiet man in London, watching the sky out of his window, reaching for words to describe what he saw. The sky has always been worth watching. It still is. And as you let your eyes close tonight, or let them rest gently on the dark of the ceiling above you, you can carry with you the quiet knowledge that the clouds outside, whatever they are tonight, whatever form they have taken, have a name. They belong to a family. They are part of a system that someone once took the time to understand and describe, so that all of us, ever since, could look up and know a little more clearly what we were seeing. Let that knowledge rest lightly in your mind, like a high cirrus cloud resting lightly in a clear blue sky, thin, luminous, barely there, and quietly beautiful. Some clouds are distant things. They hang at great heights, thin and luminous, barely touching the world below. You look up at them from far away, separated by kilometers of clear air, and they seem almost to belong to a different realm entirely. Something between the weather and the stars, something at the edge of what the atmosphere can do. But some clouds are close. Some clouds settle in around you, soft and gray and quiet, pressing the world down to a smaller, more intimate scale. Some clouds make the horizon disappear. Some clouds turn the afternoon light into something silver and diffuse, without edges or shadows, as though the sun has become simply a general brightness somewhere above. No longer a specific thing in a specific location. These are the low clouds. And tonight, we are going to spend time with them, with their textures and their moods, with the conditions that bring them into being, and with the quiet, particular feeling of a day spent beneath them. The lowest and most featureless of all cloud types is stratus. Stratus is, in its essence, a cloud that has forgotten how to be interesting. It does not build upward into towers. It does not arrange itself into waves or ripples or rows. It does not produce dramatic weather. It simply spreads horizontally, evenly, without ambition, covering the sky from one horizon to the other in a single unbroken gray sheet, like a lid placed over the world. Stratus typically forms at altitudes below about 2 kilometers, and often much lower than that. On coastlines and in valleys, stratus can form almost at the surface, so low that it is difficult to say whether you are standing beneath the cloud or inside it. It forms most commonly when moist air near the surface is gently cooled by contact with a cold land or ocean surface, by the slow sinking of air from above, or by the mixing of air layers with different temperatures. The cooling is gradual. The condensation is widespread, and the result is a sheet of cloud that forms without drama and departs without fanfare. A day under stratus is a particular kind of day. The light is flat and even shadowless, directionless. The same quality of light at noon as at 10 in the morning. Colors are muted. Edges are softened. The world looks like a watercolor painting in which all the contrasts have been turned down. It is not an unpleasant light, necessarily. Photographers sometimes call overcast light beautiful for the way it eliminates harsh shadows and renders skin tones and textures with great gentleness. But it is a light without drama, a light that does not insist on anything. Stratus rarely produces more than a light drizzle. Fine droplets, so small they seem almost to float rather than fall, appearing out of the gray air like something materializing from nothing. True rain, heavy and purposeful, is not what stratus does. It simply drips occasionally reluctantly, as though it cannot quite commit. When stratus descends to the surface of the earth, when the cloud base reaches ground level, it becomes fog. Fog is technically nothing more than a stratus cloud that has come all the way down. The physics are identical. The appearance from the inside is identical. The difference is only one of altitude. A cloud viewed from below is fog to anyone standing inside it. Fog viewed from above is a cloud. The boundary between cloud and fog is simply the boundary between the air and the ground, but the experience of fog is quite unlike the experience of looking up at a cloud from below. Fog removes the distance. Inside fog, there is no sky to look at, only the pale, luminous near distance, fading to nothing a few dozen or a few hundred meters away. The world shrinks. Everything beyond a certain point simply ceases to be visible, not because it has gone, but because the fog has gathered between you and it, absorbing the light, scattering it in every direction, turning the middle distance into a soft and uniform glow. There is a quality to dense fog that is unlike any other weather. It is quieter than clear air. Sound travels differently through the suspended droplets. High frequencies absorbed, low frequencies carrying further. Foghorns, with their deep, mournful tones, were designed specifically for fog chosen. Because their low frequencies travel further through the moisture-laden air than a higher-pitched sound would. The sound of a foghorn in thick coastal fog is one of the most evocative sounds in the world. It speaks of distance, of careful navigation, of something vast and quiet beyond. Fog forms in several different ways, and meteorologists give each type a name to reflect its origin. Radiation fog forms on clear, calm nights, particularly over land. When the sky is clear, the ground loses heat rapidly by radiating it upward into space. There are no clouds to trap the warmth and reflect it back. The land surface cools, and the air immediately above it cools along with it if the air contains sufficient moisture. It cools to its dew point, and fog forms in a shallow layer near the ground. Radiation fog is the fog of still autumn mornings, the fog that fills the low-lying fields and valleys while the hilltops remain clear, the fog that burns off quickly once the sun rises and warms the ground again. Advection fog forms when warm. Moist air moves horizontally over a cooler surface. The classic example is coastal fog, the kind that rolls in off the ocean on a summer morning. Along many coastlines, the ocean surface is cold, chilled by upwelling deeper water. Warm, moist air from further offshore flows across this cold surface and is chilled below its dew point, producing dense banks of fog that drift onshore with the sea breeze. San Francisco is famous for exactly this kind of fog. Great rolling banks of it, moving through the Golden Gate in the afternoons of summer, filling the bay, spilling over the hills, giving the city its cool, mysterious summer character. Valley fog forms when cold, dense air drains downhill into low-lying areas on calm nights. Cold air is heavier than warm air and flows like a slow, invisible liquid into the lowest available space. Valleys and hollows collect this cold air, and if the moisture is sufficient, fog forms within them, sometimes so dense that only the hilltops and ridges remain visible above it, like islands rising from a pale sea. Sea smoke, sometimes called Arctic sea smoke, forms when very cold air flows over relatively warm water. The warm water evaporates rapidly into the cold air above it, and the vapor immediately condenses again into wisps and tendrils of fog that stream upward from the surface, giving the appearance of a gently steaming pot. It is a beautiful and slightly unearthly sight. A cold sea that appears to be smoking, as though the water itself is on fire with cold. Stratus and fog, then, are the quiet extremes of low cloud, the most horizontal, the most featureless, the most diffuse of all the things a cloud can be. But low cloud also has a more textured face. That face belongs to stratocumulus. Stratocumulus is the most common cloud type on Earth. If you were to look at a satellite image of the planet on any given day, you would find that a remarkable proportion of the total cloud covers somewhere close to 30 parts in every 100 of all clouds globally is stratocumulus. It covers vast areas of the subtropical oceans. It drapes itself over coastal regions in the mornings before the warmth of the day breaks it apart. It forms the winter overcast of temperate regions. It is, in the quietest and most undemonstrative way, everywhere. Stratocumulus is a low cloud, typically below 2 kilometers. But unlike the smooth sheet of stratus, it has texture. It forms in rounded masses, in rolls and lumps and patches, arranged in layers. From below, a stratocumulus layer often looks like the underside of a vast, irregular quilt, gray or white patches separated by slightly brighter gaps, covering most of the sky without quite covering all of it. Sometimes the patches are small and tightly packed. Sometimes they are large and widely spaced. Sometimes they are arranged in parallel rolls, like long ocean waves frozen in the sky. Stratocumulus forms when a layer of moist air near the surface is gently lifted and mixed by light turbulence, by the gentle upward push of air over slightly uneven terrain, by the mixing that happens at the boundary between the warm lower atmosphere and the cooler air above. The result is not the even, uniform condensation of stratus, but a patchwork cloud forming where the mixing is greatest, gaps remaining where it is least. It is not a cloud of extremes. Stratocumulus does not produce dramatic storms. It does not tower into the upper atmosphere. It is the cloud of ordinary days, the cloud that makes the morning gray before the afternoon clears, the cloud that sits along the coast in the early hours and retreats with the rising heat of the day. But ordinary is not the same as unimportant. Stratocumulus plays a significant role in the energy balance of the planet. Its low altitude and relatively high reflectivity, its brightness when seen from above, mean that it reflects a great deal of sunlight back into space, cooling the Earth's surface. The great sheets of stratocumulus that cover the subtropical eastern oceans off the coast of California, off the coast of Peru, off the coast of Namibia, are among the most reflective surfaces on the planet. They keep those regions cooler than they would otherwise be. A world with less stratocumulus would be a warmer world. And scientists studying climate change are closely watching whether the great subtropical stratocumulus sheets are thinning or thickening as the planet's temperature rises. Because the answer matters enormously for the future of the climate system, but that is a thought for the waking world. For now, for tonight, let the low clouds simply be what they are. The soft gray ceiling of a quiet morning. The fog drifting through the valley below the ridge. The lumpy, textured quilt of stratocumulus pressed against the belly of the sky. These are the clouds that are closest to you, the clouds that have touched you. If you have ever walked through a foggy morning and felt the moisture on your face, cool and faint and barely there, the clouds that have sat above you on 1,000 ordinary days, unremarkable and quietly present. Let them be close now, too, soft and low and unhurried. Let the gray light of an overcast morning settle gently over your thoughts, diffuse, and even and without shadows, smoothing everything into something comfortable and still. Between the low clouds and the high clouds, there is a middle world. It sits roughly between 2 and 6 kilometers above the surface of the earth, too high for the fog and drizzle of stratus, too low for the ice crystal delicacy of cirrus. It is a zone of transition, a layer where the atmosphere is neither quite warm enough for the purely liquid clouds of the lower troposphere, nor quite cold enough for the purely frozen clouds of the upper. The clouds that form here are often a mixture of both, part liquid, part ice, blended together in proportions that shift with the season and the temperature and the particular mood of the air on any given day. The middle clouds are not the most dramatic clouds. They do not tower or flash or produce the grand meteorological events that make people reach for their cameras. But they are significant. They are often the advance guard of approaching weather systems. The first clouds to appear as a warm front draws near. The the harbinger of rain still hours or even days away, if you know how to read them. The middle clouds tell a story about what is coming. Tonight, we will read that story together. The first of the middle cloud genera is alto stratus. The name tells you what it is. Alto, meaning middle level, stratus, meaning a layer or a sheet. Alto stratus is the middle altitude version of stratus, a broad, even, layered cloud that covers the sky in a uniform sheet without the distinctive texture of altocumulus or the delicate translucence of the high cirrostratus above it. Altostratus is the cloud of the approaching storm. It is the cloud that appears in the sky several hours before a significant rain event, particularly when a warm front is moving through. A warm front is the leading edge of a mass of warm, moist air that is advancing over cooler air beneath it. As the warm air rises gently over the denser cold air ahead of it, it cools and clouds form in a characteristic sequence. The sequence typically begins with cirrus, thin, high wisps appearing in an otherwise clear sky, sometimes a day or more before the rain arrives. Then the cirrus thickens and spreads into cirrostratus, a thin veil of high cloud that covers the whole sky. Then, as the front draws closer and the cloud layer descends, altostratus appears, a gray or blue-gray sheet that covers the sky from horizon to horizon, thick enough to obscure the sun, though on thinner days you may still be able to make out the sun's disk through it, like a pale and diffuse light behind a sheet of frosted glass. That image, the sun visible but smeared, its edges dissolved, its light reduced to a gentle luminescence rather than a sharp disk, is one of the distinctive signatures of altostratus. Meteorologists sometimes describe it as a ground glass effect. The sun is there, but the sky has become opaque enough to remove its definition. It is a veiled light, muted and directionless, the light of a sky in transition. Altostratus is typically made of a mixture of water droplets and ice crystals. Its base sits somewhere between 2 and 4 kilometers above the surface, and it can extend vertically for a kilometer or more. When it is thick enough, it can produce precipitation, light rain or snow that falls from its base. Sometimes this precipitation reaches the ground. Sometimes, in drier air between the cloud and the surface, it evaporates before it arrives, trailing below the cloud base in faint, wispy streaks that never quite complete the journey. These streaks have a name: virga. They are a common sight beneath altostratus and other precipitating clouds, particularly over dry regions, and they have a particular delicate beauty, rain that has tried and almost reached the ground and quietly given up. Altostratus is not a cloud that asks to be noticed. It is functional, purposeful, often gray and uninspiring, in the way that the sky on a rainy November afternoon is gray and uninspiring. But it is a reliable narrator. When altostratus appears and thickens over the course of a morning, you can be fairly confident that rain is on its way. The sky is telling you something in the quiet language of cloud. The second middle cloud genus is altocumulus, where altostratus is smooth and layered and featureless. Altocumulus is textured and varied and visually rich. Altocumulus is a cloud of elements, not a single sheet, but a collection of individual cloud masses arranged in a layer. Those masses may be rounded, like distant cumulus shrunk to middle altitude scale. They may be elongated into rolls or waves. They may be arranged in a tight, regular pattern, or scattered irregularly across the sky, but they always have definition, always have three-dimensional form, always show light and shadow playing across their surfaces. Altocumulus sits typically between 2 and 4 kilometers above the surface, though it can extend somewhat higher. Like altostratus, it is often a mixture of water droplets and ice crystals. Unlike altostratus, it almost always has visible structure. The individual elements are distinct, separated by gaps of clearer sky, giving the cloud layer a patterned, textured appearance rather than a smooth one. The individual cloud elements of altocumulus are larger than those of cirrocumulus. The similar-looking high cloud smaller than those of stratocumulus below, a useful rule of thumb for telling them apart when you are looking up. If you hold your hand at arm's length and cover a cloud element with your little finger, you are probably looking at cirrocumulus. If it takes your thumb to cover it, it is more likely altocumulus. If you need your whole fist, you are looking at stratocumulus. The clouds of the middle atmosphere occupy a middle ground in apparent size, just as they occupy a middle altitude. Altocumulus comes in several species, each with a distinctive appearance. Altocumulus stratiformis is the most common variety, a widespread layer of rounded masses or rolls covering a large portion of the sky in its undulatus form. These masses are arranged in parallel waves or bands, all running in the same direction, like the ripples on the surface of a shallow pond, touched by a gentle and consistent breeze. Altocumulus lenticularis is one of the most striking cloud forms in the middle atmosphere. It forms when stable air is pushed upward by a mountain or a ridge, creating a wave in the airflow on the downwind side. Where the air rises in that wave, it cools, and a lens-shaped cloud forms. Where it descends, the cloud evaporates. The result is a smooth, elliptical cloud, sometimes several stacked on top of one another in a pile, that appears to hang perfectly still in the sky, even in strong winds. It is stationary not because the air is calm, but because the wave pattern is fixed, and the cloud continuously forms on the upwind side and evaporates on the downwind side at exactly the same rate. Lenticular clouds have a particular quality of stillness and definition that is unlike any other cloud type. They have clean, precise edges. They are smooth and symmetrical, and somehow too perfect, too deliberately shaped to look entirely natural. It is perhaps not surprising that they have, on numerous occasions, been reported as unidentified flying objects. From a distance, particularly at sunrise or sunset, when they catch the light and glow in extraordinary colors, a lenticular cloud is genuinely spectacular. It looks, more than almost any other cloud, like like something that has been deliberately placed. Altocumulus castellanus is a variety that forms towers, small turrets of cloud rise from a common base layer, like the battlements of a distant castle seen through a haze. This variety is particularly interesting to weather watchers because it is a sign of instability in the middle atmosphere, of air that is rising more energetically than is typical for the usually stable middle levels. When altocumulus castellanus appears in the morning, particularly in summer, it can be a signal that the atmosphere has enough energy and instability to produce significant thunderstorms later in the day. It is a morning warning, written in the shapes of small cloud towers, that the afternoon may be eventful. Then there is a formation that belongs not to a single cloud type, but to a particular arrangement that can appear in altocumulus, and which has one of the most evocative names in the entire catalog of cloud forms, a mackerel sky. A mackerel sky is a sky covered in altocumulus or cirrocumulus, arranged in a regular, rippled pattern, small, rounded cloud masses in closely spaced rows, covering the sky from horizon to horizon with a pattern that genuinely resembles the scales of a mackerel or other fish. It is a beautiful and slightly formal arrangement, as though the sky has decided to put on something organized for the occasion. Sailors and farmers and weather watchers have noticed the mackerel sky for centuries, and the traditional saying about it, mackerel sky, never long wet, never long dry, reflects the observation that such skies are often associated with changeable weather, neither fully settled nor fully stormy. The middle clouds, then, are the clouds of transition. They arrive before the rain and thin after it. They signal approaching systems and mark the passage of fronts. They arrange themselves in beautiful patterns above the working world, often going unnoticed in the ordinary business of the day, noticed only by those who have learned to look up and read what they find there. They occupy the middle distance of the sky, not the intimate nearness of low cloud, not the remote delicacy of high cloud, but something in between. something at the right distance to look at and appreciate, something that catches the light of early morning or late afternoon in long, warm gradients across its textured surface. Middle clouds are the clouds most likely to be beautiful in a quiet, unhurried way. Not spectacular, not dramatic, simply arranged with care in a sky that has a little time to spare. Let that quietness settle over you now. The middle sky, vast and textured and calm. The alto cumulus rolling gently in long waves above you. The light finding its way through the gaps between the cloud elements, soft and filtered and kind. A sky like that asks nothing of you. It simply is, and that is more than enough. High above the weather, above the rain and the gray and the turbulent churning of the lower troposphere, there is a different kind of sky. It is colder up there, much colder. At altitudes above 6 kilometers, temperatures are well below freezing even in summer, -30, -40, -50 degrees Celsius or lower. The air is thin and dry. The moisture that remains is not liquid. It is ice. And the clouds that form at these altitudes are made not of water droplets, but of ice crystals, tiny, hexagonal, endlessly varied, catching the light in ways that liquid water cannot quite manage. The high clouds are the most delicate clouds, the most luminous, the most easily overlooked, and when noticed, the most quietly beautiful. They do not produce rain. They do not darken the sky. They are translucent. You can often see the sun or moon clearly through them, sometimes surrounded by a ring of light, a halo created by the refraction of sunlight through their ice crystals. They drift at the edge of what clouds can do, at the very top of the cloud-forming world, and they are worth spending time with tonight. We begin with cirrus. Cirrus is the cloud that Luke Howard named first when he invented his classification system in 1802. And it is easy to understand why. Cirrus is perhaps the most immediately recognizable cloud type, the one most easily described in simple, vivid language. It is thin. It is white. It is drawn out into long, sweeping strands or delicate tufts, as though painted on the blue with a fine brush dipped in white. It sits high, typically between 6 and 12 kilometers above the surface, and it moves fast, carried by the strong winds of the upper troposphere. The winds at those altitudes, the jet streams, the great rivers of fast-moving air that circle the planet at high altitudes, blow at speeds that can exceed 200 kilometers per hour. Cirrus clouds are shaped by these winds. Their characteristic form, long, fibrous, often slightly curved strands, is a direct result of the ice crystals that make them up being carried horizontally by the fast-moving air, while they simultaneously fall slowly under gravity. The crystals fall. The wind blows them sideways, and the result is a long diagonal streak of cloud, thin at one end, where the crystals are newest and freshest, fading at the other where they have been dispersed and diluted by the surrounding air. One of the most distinctive varieties of cirrus has a name that reflects its shape with great precision. Cirrus uncinus. Uncinus being the Latin word for a hook or a barb. Cirrus uncinus clouds have a characteristic comma shape, or a gentle hook at their upper end, created when the crystals at the top of the falling streak encounter a slight change in wind direction or speed. The hook curls away from the main trail of the cloud. From the ground, a sky full of cirrus uncinus, each one curved and trailing, each one pointing the same general direction in the wind, looks remarkably like the tails of horses, all streaming in the breeze. And this is, in fact, what they are sometimes called: mare's tails. Mare's tails have been watched by sailors and farmers and weather observers for centuries. Traditional lore holds that mare's tails in a clear sky are a sign of approaching bad weather, that the high cirrus is the advance guard of an approaching warm front, and that within a day or two the sky will cloud over and rain will follow. This traditional observation is, more often than not, correct. When cirrus appears in a clear sky and thickens over the following hours, spreading from wisps into a more general high haze, it is indeed frequently the precursor of a front moving in from the west. Cirrus clouds are so thin that they are often transparent. You can look through them and see the blue of the sky beyond, a blue that is slightly paler, slightly milkier than the pure blue of a completely clear sky, but still clearly blue. The sun shines through cirrus without being obscured, casting shadows as normal, giving no hint of the extraordinary altitude at which that thin veil of ice exists above you. At sunrise and sunset, cirrus clouds are transformed. The low angle of the sunlight strikes their ice crystals and produces colors of extraordinary intensity, deep golds and ambers, vivid pinks and magentas, sharp reds that fade to orange, and then to rose as the light changes. A sky full of cirrus at the golden hour is one of the most beautiful natural spectacles available anywhere on Earth. The colors seem almost too saturated to be real. They last only minutes. As the sun drops below or rises above the horizon, the light angle changes and the colors shift and fade. But while they last, they are genuinely breathtaking. The ice crystals in cirrus clouds are not all the same shape. They come in several forms, depending on the temperature and humidity at the altitude where they formed. Some are simple hexagonal plates, flat, six-sided discs of ice. Some are hexagonal columns, long, thin prisms. Some are hollow columns, or columns with plates at each end, called bullet rosettes. And some are the elaborate, branching, fern-like structures that most people picture when they think of a snowflake. Though these complex forms are more common in clouds lower and warmer than typical cirrus, the different crystal shapes refract and reflect light in different ways, producing different optical effects when the sun shines through them. Most familiar is the 22-degree halo, a ring of light surrounding the sun or moon at an angular distance of 22 degrees, produced by refraction through hexagonal ice crystals oriented randomly in the cloud. If you see a ring around the sun or moon, you are almost certainly looking at cirrostratus, the next of our high cloud genera. And the halo is being painted for you by countless tiny ice prisms, each one bending the light by exactly the right amount. Cirrostratus is a high cloud that covers the sky in a thin, even veil. Unlike altostratus, which covers the sky in a thicker, grayer sheet, cirrostratus is translucent. The sun and moon remain visible through it, and the sky retains a pale, luminous quality rather than turning gray. The texture of cirrostratus is smooth and featureless. It does not have the defined elements of cirrocumulus or the fibrous strands of cirrus. It is simply a thin, white, milky covering, as though someone had stretched a sheet of finest frosted glass across the entire sky. The halo that cirrostratus produces is one of the most reliably beautiful of all atmospheric optical phenomena. It appears as a perfect circle of light around the sun, often with a slight iridescence, a faint rainbow of colors along its inner edge, produced by the varying thickness of the ice crystals, the traditional weather saying associated with the halo. A ring around the moon means rain is coming soon, reflects the same observation as the mare's tails saying. Cirrostratus is often the intermediate stage between the first thin wisps of cirrus and the thicker altostratus that signals approaching rain. The halo is a warning delivered in light. In some conditions, cirrostratus produces more elaborate optical effects than just the halo. Sundogs, also called parhelia, are bright spots of light that appear on either side of the sun, at the same altitude as the sun and roughly 22 degrees away from it to the left and right. They are produced by flat hexagonal ice crystals that have settled with their flat faces horizontal as they drift through the air, all oriented in the same direction. When sunlight enters the side of these horizontally oriented crystals and exits through another face, it is refracted at an angle that creates a bright, sometimes faintly colored spot at a specific position relative to the sun. Two sundogs, flanking the sun on both sides, sometimes so bright they look almost like two additional suns, are a genuinely striking sight and have been reported with wonder by observers throughout human history. Sun pillars are columns of light that appear to extend vertically above or below the sun, particularly at sunrise or sunset. They are produced by flat ice crystals drifting with their faces horizontal, acting as tiny mirrors and reflecting the sunlight downward toward the observer. A sun pillar above a low winter sun can look remarkably like a beam of light being projected upward from the horizon, as though from some source beyond the visible. Circumzenithal arcs, tangent arcs, halos of 46 degrees, parhelic circles. The catalogue of optical phenomena produced by high ice crystal clouds is long and extraordinary. Many of them are rare enough that most people go their entire lives without seeing them. But all of them are waiting somewhere above whenever the conditions of temperature and crystal type and sun angle happen to align. The third high cloud genus is cirrocumulus. Cirrocumulus is the rarest of the three high cloud types. It appears as a layer of very small white cloud elements, tiny rounded tufts or ripples arranged in a regular pattern across the sky. The individual elements of cirrocumulus are much smaller than those of altocumulus, small enough that each one could be covered by the tip of a little finger held at arm's length. They have no shading. They are too thin and small for any internal shadow to develop, which gives them a uniformly white, somewhat flat appearance, despite their textured arrangement. A sky covered in cirrocumulus is a sky covered in a fine, regular pattern, sometimes resembling fish scales, sometimes a finely woven net, sometimes the rippled surface of a shallow pool, disturbed by a gentle and consistent breeze. It is the cloud that, more than any other, gives rise to the term mackerel sky. Though altocumulus produces similar patterns at lower altitude, the cirrocumulus version is finer, more delicate, more closely spaced, a higher resolution pattern, as though the same image had been printed on a finer grain. Cirrocumulus is relatively unstable as clouds go. It tends to form and dissipate quite quickly, often transitioning into cirrus or cirrostratus as conditions change. A patch of cirrocumulus that appears in the morning may have transformed into something entirely different by afternoon. It is a cloud in motion, in more than just the physical sense, a cloud in transition, briefly occupying one particular form before moving on to another. The high clouds cirrus, cirrostratus, cirrocumulus are the clouds of the upper atmosphere. They are made of ice and shaped by the fastest winds on the planet. They produce halos and sundogs and pillars of light. They tell stories about approaching weather. They catch the colors of sunrise and sunset with a vividness that no low cloud can match. And they do all of this at a distance, 6, 8, 10, 12 kilometers above the ground, so remote that they seem almost to belong to a different world from the one you inhabit. They are the sky's most distant residents, the thinnest, the coldest, the most ethereal. When you look up at Cirrus on a clear, cold winter afternoon, those long, white strands drawn across the deep blue, moving almost imperceptibly in winds that are roaring at altitude. There is a particular quality to the experience, a sense of scale, a sense of the enormous depth of the atmosphere above you, a sense of something very far away and very quiet, doing its slow and beautiful work in the cold air above the clouds you know. Let that distance settle over you now, softly and without weight. The high clouds are far above. The ice crystals are drifting. The light is finding its way through them, bending and scattering, painting colors that no one below will notice. And down here, everything is still and warm and very close to sleep. There is one cloud that stands apart from all the others, not in altitude alone, though it reaches higher than almost anything else in the troposphere, not in size alone, though it can grow to dimensions that dwarf entire mountain ranges, not in the drama of what it produces, though it generates lightning and thunder and hail and torrential rain, and occasionally tornadoes. It stands apart because it is, in the most complete sense, a weather system unto itself, a single cloud that contains within its vast interior almost every atmospheric process that the troposphere is capable of producing, all happening simultaneously, all driven by one fundamental force. That force is heat, and the cloud it builds is the cumulonimbus. The cumulonimbus is the tallest, most powerful, most energetic cloud that forms in the Earth's atmosphere. It begins as something modest, a small cumulus cloud, a puffy white mound forming on a warm morning as rising air reaches its lifting condensation level and water vapor begins to condense. It looks at first exactly like the hundreds of other cumulus clouds forming in the sky around it. But this one is different. This one is forming in air that is not just warm at the surface, but deeply unstable throughout a great depth of the troposphere. Air in which a rising parcel, once it begins to ascend, finds that it remains warmer and more buoyant than its surroundings all the way up. And so it keeps rising, and the cloud it carries keeps building. The growth of a cumulonimbus is one of the most remarkable spectacles that the natural world produces. A small cumulus, maybe 1 kilometer tall, can grow into a mature cumulonimbus reaching 12 or 15 kilometers in height in as little as 30 to 45 minutes. The updrafts inside a developing cumulonimbus can be extraordinarily powerful. Rising currents of air moving upward at speeds of 100 kilometers per hour or more in the most intense storms. These updrafts carry water droplets and ice crystals upward with tremendous force, preventing them from falling, keeping them suspended, allowing them to grow by colliding with one another inside a large cumulonimbus. The physics of the atmosphere are operating at full intensity. In the lower part of the cloud, where temperatures are above freezing, water droplets are forming and growing. Higher up, where temperatures fall below freezing, those droplets are freezing into ice crystals. Higher still, where temperatures are far below freezing, the ice crystals are growing into snowflakes and aggregating into larger clumps. And in the updraft regions, hailstones are forming, carried up and down through the cloud repeatedly by the violent air currents, accumulating layers of ice with each pass through the freezing regions, growing from tiny ice pellets into stones, sometimes as large as a golf ball, or in the most extreme storms, considerably larger. The electricity of a thunderstorm, the lightning that flashes inside the cloud and strikes the ground, the thunder that rolls across the landscape moments later, is generated by the violent separation of electrical charges within the cumulonimbus. Exactly how this happens is still not fully understood, but the leading explanation involves the collision of ice particles within the cloud. When small ice crystals collide with larger, softer ice particles called graupel, in the presence of supercooled water droplets, the smaller crystals tend to acquire a positive electrical charge, and the larger particles a negative one. The updrafts carry the lighter, positively charged crystals toward the top of the cloud. The heavier, negatively charged particles sink toward the middle and lower portions. Over time, this separation creates a powerful electrical potential. A difference in charge between different parts of the cloud, or between the cloud and the ground below. When that potential difference becomes large enough, the air, which is normally a very poor conductor of electricity, breaks down. A channel of ionized air forms, invisible and almost instantaneous, connecting the charged regions, and through that channel flows a discharge of electricity so powerful that it briefly heats the surrounding air to temperatures around 30,000 degrees Celsius, roughly 5 times hotter than the surface of the sun. The blinding flash of that heated air is the lightning. The explosive expansion of that superheated air is the thunder. Lightning happens with extraordinary frequency across the planet at any given moment. There are roughly 2,000 thunderstorms active somewhere on Earth, producing approximately 100 lightning flashes every second. Over the course of a year, lightning strikes the surface of the Earth somewhere in the region of 1 billion times. It is not a rare event. It is a continuous feature of the planetary atmosphere, happening somewhere every second of every day, driven by the same basic process of convection and charge separation that has been operating since the atmosphere formed. The mature cumulonimbus has a distinctive shape. Its base is dark, often very dark, almost black when viewed from below. Because the cloud above is so thick and tall that it absorbs most of the light before it can reach the base, the cloud towers upward in a great column, bright white on its illuminated sides, shadowed and gray on the others. And at the very top, where the updrafts have reached the tropopause and can go no further, stopped by the stable stratosphere above, the cloud spreads outward sideways in a wide, flat, anvil-shaped formation. This anvil top is one of the most recognizable features of a mature thunderstorm cloud. It forms because the updraft, blocked from going higher, is deflected horizontally by the winds at the tropopause, the ice crystals at the top of the cloud, carried outward by these high-level winds, stream downwind in a long, thin, fibrous trail, sometimes extending hundreds of kilometers ahead of the storm. The anvil top is made of cirrus, the same high ice crystal cloud we know from fair weather skies. But it is cirrus generated by the violent energy of the storm below, not by the gentle lifting of a warm front from a distance on a clear day in summer. The sight of a fully developed cumulonimbus with its anvil top is one of the most impressive sights in nature. The sheer scale of it, a cloud that may be 20 kilometers tall, wider than some small countries, its interior seething with updrafts and downdrafts, lightning flickering within its dark interior, is genuinely humbling. It is a reminder that the atmosphere is not just the comfortable layer of air that we breathe. It is also capable of concentrating enormous amounts of energy into a small volume and releasing that energy with extraordinary intensity. A severe cumulonimbus, a supercell thunderstorm, as meteorologists call the most organized and long-lived variety, is a rotating storm with a persistent updraft called a mesocyclone. The rotation develops when wind speed and direction change with altitude in the surrounding environment, creating horizontal tubes of rotating air that the updraft then tilts into the vertical. A supercell can persist for many hours, moving across the landscape, producing large hail, damaging winds, and, in the most extreme cases, tornadoes, violently rotating columns of air that descend from the base of the storm and make contact with the ground. Tornadoes are among the most violent wind events on Earth. The most extreme produce winds that may exceed 480 kilometers per hour. Winds powerful enough to strip the bark from trees, to drive pieces of straw through wooden planks, to lift houses from their foundations and carry them hundreds of meters. And yet a tornado, for all its violence, is a small thing compared to the cumulonimbus that produces it. The tornado is a detail, a feature, a consequence of the larger storm system above. In the tropics, cumulonimbus clouds organize themselves into much larger systems. Clusters of thunderstorms merge and feed off one another, developing a shared circulation that can grow over days into a tropical cyclone. The weather system known in different parts of the world as a hurricane or a typhoon, a mature hurricane, is simply a vast organized collection of cumulonimbus clouds arranged in a spiral around a calm central eye, extracting energy from the warm ocean surface and releasing it in sustained winds that can exceed 250 kilometers per hour across a storm system hundreds of kilometers wide. From the ground, looking up at the base of a cumulonimbus on a stormy afternoon, it is easy to feel something close to awe. The cloud is alive in a way that no other cloud quite manages to be. Its surface roils and churns, new towers billow upward continuously from its edges. The light beneath it is strange and greenish and wrong feeling. The wind shifts and gusts and dies and shifts again. And somewhere inside that dark, towering mass, ice and water and electricity are doing things together that have been doing them for as long as the Earth has had an atmosphere. The cumulonimbus is not a gentle cloud. It is not a cloud you can watch from your bed through a quiet window without feeling something ancient and instinctive. Something that says, this is powerful, this is important, pay attention. And yet, from a safe distance, or from the memory of a storm already past. There is something deeply satisfying about it. The storm spent its energy. The rain fell. The lightning flashed and the thunder rolled. And then the sky began to clear. And the air afterward was cooler and cleaner, and somehow more itself than it had been before. That clearing after a storm, the washed blue of the sky, the sharpened green of the leaves, the particular freshness of the post-storm air, is one of the atmosphere's quiet gifts. The cumulonimbus spent hours building and raging, and then it dissolved, and what it left behind was stillness. There is something in that to carry with you into sleep. The storm builds, the storm passes, the sky clears, the air is clean, and the world, after all of that, is quieter and softer and more peaceful than it was before. Let that thought settle over you gently now. The storm has already passed. The sky is clearing. The air is still, and the clouds that remain are soft and high and very far away. When a cloud can no longer hold what it carries, it lets go. That is precipitation in its simplest form. The release, the moment when water that has been suspended in the sky, held up by air currents, kept aloft in the form of droplets and crystals too small and too light to fall on their own, finally grows heavy enough, or the air beneath it calm enough to descend, to return, to complete the downward leg of the water cycle and rejoin the world at the surface. Precipitation is the sky giving something back. It took the water up, evaporating it from the ocean, lifting it in rising columns of warm air, condensing it into cloud, and now it returns it, not all at once, and not all to the same place, but steadily, reliably, in an endless pattern of giving and taking that has been maintaining the water balance of the planet for billions of years. Rain, snow, sleet, hail, drizzle, freezing rain. Each one is precipitation. Each one is water returning from the atmosphere to the surface. And each one is produced by a different set of conditions, a different arrangement of temperature and moisture and atmospheric motion, a different story told by the cloud above. We begin with rain, the most familiar form of precipitation for most people one that falls on more of the planet, more of the time than any other. A newly formed cloud droplet is tiny, somewhere between 5 and 20 micrometers across. A micrometer being 1/1,000,000th of a meter. A droplet this size does not fall. It is so light that the faintest upward air current is enough to keep it suspended, even in perfectly still air. It would fall so slowly, at a rate of perhaps 1 centimeter per second, that it would take many hours to descend a single kilometer. In the churning air of an active cloud, where updrafts are moving at many meters per second, such a droplet has no chance of falling at all. For precipitation to occur, cloud droplets need to grow. They need to become large enough that gravity can overcome the resistance of the air and the lifting power of the updrafts. A raindrop that reaches the ground is typically around 2 millimeters across, 100 times the diameter of a cloud droplet. And since volume scales with the cube of the radius, that means a raindrop contains roughly 1,000,000 times the water of a single cloud droplet somewhere between the formation of a cloud and the arrival of rain at the surface. 1,000,000 tiny droplets have been gathered into a single falling drop. There are 2 main processes by which this growth happens. The first is called collision coalescence. It applies primarily in warm clouds, clouds whose tops remain below the freezing level, found mainly in tropical regions. In a warm cloud, all the particles are liquid droplets. They move through the cloud at slightly different speeds, depending on their size. Larger droplets fall slightly faster than smaller ones, even within the cloud. As a larger droplet descends relative to the smaller ones around it, it collides with them and absorbs them, coalesces with them. To use the technical term, each collision makes the larger droplet slightly heavier, slightly faster falling, more efficient at sweeping up the smaller droplets below it. The process accelerates. A droplet that starts slightly larger than its neighbors grows quickly into a raindrop. The second process is called the Bergeron process, named after the Norwegian meteorologist Tor Bergeron, who described it in the 1920s. It operates in mixed phase clouds, the clouds that contain both liquid water droplets and ice crystals, which is the case for most of the rain-producing clouds in temperate and polar regions. The Bergeron process depends on a remarkable physical fact. At temperatures below freezing, ice and liquid water have different vapor pressures. Water vapor is more attracted to an ice surface than to a liquid water surface at the same temperature. This means that in a cloud containing both ice crystals and supercooled liquid droplets that remain unfrozen even though the temperature is below zero. The ice crystals grow preferentially. Water vapor migrates from the liquid droplets to the ice crystals, depositing itself on their surfaces. The ice crystals grow. The liquid droplets shrink. Eventually, the ice crystals become heavy enough to fall. As they fall through warmer air below the cloud, the ice crystals may melt and arrive at the surface as rain. Or, if the air below is cold enough, they may remain frozen and arrive as snow, or they may melt and then refreeze as they pass through a layer of cold air near the surface, arriving as sleet or freezing rain. The Bergeron process is responsible for the majority of precipitation that falls over temperate regions of the world. Much of the rain that falls on a typical mid-latitude day started out as snow or ice high in the cloud above. The rain that falls on a garden in England or Germany or the northeastern United States on an ordinary gray afternoon was, only a short time before it reached the ground, an ice crystal drifting in the cold air of the upper troposphere. Snow is perhaps the most quietly beautiful form of precipitation. It forms when ice crystals in the upper cloud grow large enough to begin falling, and the air below remains cold enough that they do not melt on the way down. As they fall, ice crystals may aggregate, clumping together with other crystals to form snowflakes, which can be considerably larger than the individual crystals that make them up. The structure of an individual ice crystal, the hexagonal symmetry, the branching arms, the extraordinary variety of forms, is a consequence of the molecular geometry of water and the conditions of temperature and humidity within the cloud where the crystal grew. The six-sided symmetry comes from the way water molecules bond together when they freeze. The branching, the complexity, the delicate elaboration of the crystal's arms comes from the precise temperature and humidity the crystal experienced as it grew. Conditions that vary slightly as the crystal moves through the cloud, producing slight differences in growth at each point. The old saying that no two snowflakes are alike is, in essence, true, not because of some magical uniqueness, but because the path each crystal takes through the cloud is unique, and the structure of the crystal records that path with great fidelity. A snowflake is a diary of its own formation, written in ice. Very simple, very small ice crystals can be identical, but the complex, branching flakes that form under certain temperature and humidity conditions, the ones that look under a microscope like the most intricate lace, are so sensitive to the conditions of their growth that any two crystals following even slightly different paths through the cloud will diverge in their structure. By the time they reach the ground, no two are the same. Hail is a form of precipitation produced exclusively by cumulonimbus clouds, by the violent, powerful updrafts of thunderstorms. A hailstone begins as a small ice particle high in the storm cloud. The powerful updrafts carry it upward into the coldest regions of the cloud, where supercooled water droplets freeze onto its surface in a layer. Then the hailstone falls, perhaps into a region of the cloud where the temperature is warmer and the water is liquid, adding a layer of clear ice. Then the updraft catches it again and carries it upward, adding another layer of opaque ice. Each cycle adds a new layer. Cut a large hailstone in half, and you can see the layers clearly, alternating bands of clear and opaque ice, each one recording a cycle of ascent and descent through the storm cloud. The number of layers tells you how many times the hailstone made that journey. A hailstone with many layers has been in the cloud for a long time, caught in exceptionally powerful updrafts. The largest hailstones, the ones that fall from the most extreme supercell thunderstorms can weigh hundreds of grams and fall at speeds of more than 160 kilometers per hour. They can shatter windows, dent metal, strip leaves from trees, and in rare cases, cause injury to people and animals caught in the open. Drizzle is at the opposite end of the precipitation spectrum from hail. Drizzle consists of very small droplets, larger than cloud droplets, but smaller than typical raindrops, falling slowly from low stratus or stratocumulus clouds. Drizzle drops are typically less than 0.5 millimeter across. They fall at speeds of less than 1 meter per second, and in a light breeze, they can appear to drift sideways rather than fall vertically. Walking through drizzle is not quite like walking through rain. The drops are too small to feel individually on the skin. They accumulate rather than strike, coating surfaces with a thin, even layer of moisture without the audible pattering of rain. A foggy drizzle, fine enough to be barely visible, fine enough to hang suspended for long moments before finally settling, is one of the most enveloping weather experiences there is. It fills the air with moisture without seeming to fall at all. It is weather that surrounds rather than strikes. Freezing rain forms when rain falls through a shallow layer of cold air near the surface. The raindrops, still liquid, but cooled to below freezing, strike cold surfaces, roads, branches, power lines, rooftops, and freeze on contact. The result is a coating of clear ice, glaze ice, or black ice on roads that can be extraordinarily beautiful and extraordinarily dangerous in equal measure. A landscape after a freezing rain event, when the ice has had time to set and the sun comes out, is one of the most visually extraordinary natural spectacles of the temperate world. Every twig, every blade of grass, every fence post and telegraph wire is sheathed in a perfect, transparent layer of ice. The light catches it and scatters into thousands of tiny rainbows. The world sparkles as though it has been dipped in glass. Precipitation in all its forms is the delivery mechanism of the water cycle. It is the way the atmosphere keeps its accounts, taking water up through evaporation and returning it through rain and snow and drizzle and hail, always balancing, always maintaining the great circulation of water through the earth system that life depends upon. And at the most fundamental level, it is simply water coming home, returning from the sky to the surface, rejoining the rivers and the lakes and the ocean, beginning the journey again, the rain that falls on your rooftop tonight, or that has fallen, or will fall, has made this journey many times before. It knows the way. It always finds its way back. Let that thought carry you gently downward now. The way a raindrop falls through still air, slowly, steadily, without effort, following the quiet pull of gravity towards something solid and at rest. Of all the forms that water takes in the atmosphere, fog is the most intimate. Rain falls from a distance. Snow drifts down from heights you cannot see. Even low stratus hangs above you, separated from your skin by some meters of clear air. But fog is different. Fog comes all the way down. It fills the space you occupy. It surrounds you completely, pressing in from every direction, softening every edge, dissolving every distance. When you stand in fog, you are standing inside a cloud. The boundary between the atmosphere and your immediate world has been erased. There is no other weather quite like it. Fog is defined, technically and precisely, as a cloud whose base is at the surface of the earth. A cloud, in other words, that has descended all the way to the ground, or formed there in the first place. Meteorologists typically require that the visibility within fog be reduced to less than 1 kilometer before they officially call it fog. When visibility is reduced but remains above 1 kilometer, the condition is called mist. The difference between fog and mist is a matter of degree rather than kind. Both are clouds at ground level. Both are made of the same tiny suspended water droplets. But fog is denser, thicker, more complete in its transformation of the visible world. The physics of fog are identical to the physics of any other cloud. Air cools below its dew point. Water vapor condenses onto condensation nuclei, and tiny, droplets form and remain suspended in the air. What makes fog different from a cloud at altitude is simply location. The same process that forms a stratus cloud 200 meters above a hillside forms fog when the hillside is 200 meters higher than it would otherwise be, or when the air cools enough to bring the cloud base all the way to the surface. We touched on the main types of fog in our earlier section on low clouds. But tonight, fog deserves its own unhurried exploration. Because fog is not just a meteorological phenomenon. It is an experience. It changes the world in ways that are worth dwelling on, slowly and with attention. Radiation fog is perhaps the most familiar fog of temperate climates. The fog of still autumn and winter mornings, forming overnight and lingering into the early hours of the day before the sun burns it away. It forms on clear, calm nights when the ground loses heat rapidly through radiation. With no cloud cover to trap the warmth and reflect it back, the surface cools quickly after sunset. The air immediately above the surface cools along with it. If there is sufficient moisture in the lower air, and there often is after a recent rain or near bodies of water, the temperature falls to the dew point, and fog begins to form. The best conditions for radiation fog are a combination of clear skies, light winds, and moist air. Completely calm conditions are not quite ideal. A very gentle breeze, just enough to produce a little mixing in the lowest layers of air, actually helps thicken the fog by bringing more moist air into the cooling zone. Too much wind, on the other hand, mixes the cold surface air with the warmer air above before it can cool enough to form fog, and lifts the fog into a layer of low stratus. Instead, radiation fog tends to be thickest in valleys and low-lying areas where the cold, dense air drains from the surrounding slopes and accumulates. A valley on a still autumn morning may be filled to its brim with fog. A white, flat-topped lake of cloud, while the hilltops above it emerge into clear sunlight. From the hilltop, looking down into the fog-filled valley, you see the tops of trees and church spires and farmhouse chimneys poking through a perfectly smooth, perfectly white surface. The valley has become a sea. The familiar landscape below has been replaced by something flat and featureless and still. From inside the fog, the experience is the reverse. The hilltops have vanished. The sky has lowered itself to eye level. The world extends in every direction for perhaps 50 meters, perhaps 100, and then simply ends, not in darkness, not in a wall, but in a pale and luminous fading, as though everything beyond a certain distance has been erased with a soft cloth. Sounds behave differently in fog. High-pitched sounds are absorbed more readily by the suspended droplets, while low-pitched sounds carry further. The world becomes quieter in some ways and more resonant in others. A foggy morning has a hush to it, not the hush of soundlessness, but the hush of sounds arriving softened and directionless, as though the air itself has been padded. Radiation fog usually disperses during the morning as the sun rises and warms the ground. The warmth evaporates the droplets at the base of the fog layer first, thinning it from below. By mid-morning, the fog has often lifted, becoming a layer of low stratus, and by early afternoon, it has usually broken apart and dissipated entirely, leaving a clear and sometimes brilliantly sunny afternoon in its place. The morning that began in thick gray silence ends in sharp blue clarity. Advection fog is the fog of coastlines and of spring, the fog that forms when warm. Moist air flows over a cold surface and is chilled to its dew point. The most celebrated example is the sea fog that forms along coastlines where cold ocean currents run close to the shore. The California coast is famous for it. The cold California current flows southward along the coast, chilling the surface water to temperatures sometimes 20 degrees or more below the temperature of the air above it. When warm, moist air flows onshore from the Pacific and passes over this cold water, it is rapidly chilled. The moisture condenses into fog, sometimes before the air even reaches the shore, producing banks of fog that roll in off the ocean and advance inland, filling the bays This fog is so persistent and so characteristic of the city that it has become part of the local identity. The city sits on a peninsula flanked by water, with the famous opening of San Francisco Bay, the Golden Gate, acting as a funnel through which the afternoon sea fog pours in from the Pacific as the heating of the land creates a pressure difference that draws the cool marine air inland. The fog arrives almost every afternoon in summer, rolling in low and fast through the gate, spilling over the Marin headlands, advancing on the city in a great white wave. By evening, the city may be cool and gray and wrapped in cloud, while just a few kilometers inland the valleys bake in sunshine. Sea fog is different in character from radiation fog. It is often denser, more persistent, less susceptible to the warming of the sun. Because it is continuously fed by the cold ocean surface beneath it, it does not dissipate when the sun rises. It simply remains, sometimes for days at a time, until the wind direction changes and warmer air from a different source replaces the moist marine air that feeds it. Sailors have feared sea fog throughout maritime history. It removes the horizon. It removes landmarks. It removes all visual reference for navigation. It makes the world a sphere of gray extending perhaps a ship's length in every direction before the age of radar and electronic navigation. Fog was one of the great hazards of the sea. Ships ran aground, collided with one another, lost their bearings in fog, and found themselves miles from where they believed themselves to be. The sounds of fog at sea, the deep moan of a lighthouse foghorn, the bell of a buoy rocking in the swell, the creak of rigging, and the soft lap of water against the hull are among the most evocative sounds associated with the ocean. They are sounds designed to carry meaning through blindness. Sounds that say, "We are here. This is where we are. Navigate carefully. The world you cannot see is still present and still solid. Hill fog and upslope fog form when moist air is pushed upward by rising terrain. As the air climbs, it cools at the dry adiabatic lapse rate, and if it cools to its dew point before it, reaches the top of the hill, cloud forms. This cloud, from the perspective of someone standing at the level where it has formed, is fog. The hills of Wales, the moors of northern England, the uplands of Scotland. These places are frequently wrapped in hill fog, sometimes for days at a time, the landscape disappearing into gray at 200 or 300 meters of altitude, the upper slopes invisible and the lower valleys clear. There is a word in Welsh, unhurried, that describes a kind of longing, a deep nostalgia for something lost, or perhaps never quite possessed. Walking in hill fog in Welsh uplands, with the visibility closed in and the sounds muffled and the familiar landmarks hidden, produces a particular feeling that is not quite longing, but is related to it, a feeling of the world having become smaller and more uncertain, of being enclosed in something soft and slightly melancholy. It is not an unpleasant feeling, necessarily. It is a feeling of interiority, of being drawn inward, of the external world having temporarily withdrawn its usual insistence on being noticed. Ice fog is a form of fog that occurs in the coldest climates, in Arctic and Antarctic regions, in the deep interior of continents, in the coldest months of winter. It forms when temperatures fall so far below freezing that the fog droplets freeze in place, becoming tiny suspended ice crystals rather than liquid droplets. Ice fog is generally less dense than liquid fog, but it has a particular visual quality, a diamond dust sparkle, a glittering luminescence in sunlight that liquid fog does not possess. The ice crystals catch the light and scatter it in all directions, sometimes producing faint halos or sun pillars, even in the fog itself. In extremely cold conditions, temperatures below -30 or -40 degrees Celsius, ice fog can form from surprisingly little moisture, human breath, the exhaust of vehicles. Even the warmth rising from a building are enough to create local patches of ice fog in air that cold. In the small communities of the far north, in the depths of winter, the mere presence of people and their activities can generate visible fog in the surrounding air. Freezing fog is a fog whose droplets droplets are supercooled liquid, but below freezing temperature. When these supercooled droplets contact a surface, they freeze instantly on contact, depositing a layer of white, granular ice called rime. Rime ice builds up on every exposed surface, branches, fences, antennae, the windward side of trees, creating a world coated in white crystals, a landscape that looks as though it has been dusted with the most delicate frost imaginable. Every twig is outlined in white. Every wire wears a coating of crystal. The world is transformed into something intricate and cold and impossibly detailed. Rime is different from the clear glaze ice produced by freezing rain, where freezing rain creates a transparent coating that makes surfaces look wet and glassy. Rime creates a white, opaque, feathery deposit that makes surfaces look as though they have grown a fur of ice. A forest after a night of freezing fog and rime deposition is a forest of white trees. Every branch, every twig, every needle of every pine outlined in white against the gray sky. The whole landscape rendered in two colors only, white and gray, and the pale light between them. Fog, in all its forms, is the atmosphere at its most intimate. It is weather that does not happen above you or around you in the distance. It happens here. It happens where you are standing. It fills your immediate world, softens its edges, quiets its sounds, reduces its scale. There is something restful about that on reflection. The world made smaller, the distances closed down, nothing required of you from beyond the fog. The usual demands of the visible horizon, the insistence of the far distance, the pressure of everything that lies beyond immediate reach, all of it temporarily suspended. In the fog, the world is simply close, and everything close is quiet and soft and very near. Let that closeness settle around you now, like a morning fog settling into a valley, gentle, gradual, filling the low places first, softening everything it touches, making the world smaller and quieter and very still. The air is never truly still. Even on the calmest day you have ever experienced, A windless summer afternoon. The leaves on the trees completely motionless. The surface of a lake as flat and smooth as a mirror. The air around you is in motion, not at the scale you can feel on your skin, not at the scale that moves a leaf or ripples the water, but at the microscopic level, the molecular level. The air is always moving, always churning, always redistributing itself in response to the invisible forces that act upon it. Wind is simply that motion made large enough to feel. It is the atmosphere in the act of balancing itself, moving from places where there is more pressure to places where there is less, from places that are warmer to places that are cooler, from places where air has accumulated to places where it is lacking. Wind is the atmosphere's way of correcting its own imbalances. And since the atmosphere is always developing new imbalances, heated here by the sun, cooled there by the night, piled up here by a storm, thinned out there by rising air. Wind is always blowing somewhere at some scale, in some direction. The fundamental cause of wind is simple. Differences in air pressure. And differences in air pressure are caused, ultimately, by differences in temperature. When air is warmed, it expands. When it expands, it becomes less dense, lighter, in a sense, and it rises. As it rises, it leaves behind a region of slightly lower pressure at the surface, because there is now less air pressing down on that spot. Surrounding air at slightly higher pressure flows in to fill the gap. That flow of air is wind. When air is cooled, the opposite happens. It contracts, becomes denser, and sinks. As it sinks, it piles up at the surface, creating a region of slightly higher pressure. Air flows outward from this high pressure region toward areas of lower pressure. That outward flow, too, is wind. The sun heats different parts of the Earth's surface at different rates. Land heats up and cools down more quickly than the ocean. The equatorial regions receive more direct sunlight than the poles. Dark surfaces absorb more heat than light ones. Wet surfaces cool through evaporation in ways that dry surfaces do not. The result of all this uneven heating is a planet covered in regions of different temperature and pressure, all connected by the flowing air that moves between them. The simplest example of a thermally driven wind is the sea breeze, a wind you may have experienced if you have ever spent time near a coast on a warm day. During the day, the land heats up much more quickly than the ocean. The air over the land warms and rises, creating a region of low pressure at the surface. The air over the cooler ocean remains at higher pressure. In response, a gentle flow of air develops from the ocean toward the land, a sea breeze, cool and moist, arriving from the water and bringing relief from the heat of the afternoon. Anyone who has sat on a beach and felt that cool onshore breeze begin in the early afternoon, as the land reaches its maximum temperature, has felt this process directly on their skin. At night, the situation reverses. The land cools quickly after sunset, becoming colder than the ocean, which retains its heat longer. Now the air over the ocean is warmer, rises, and the flow reverses. A land breeze, light and dry, flowing from the cooler land out toward the warmer sea. The land breeze is usually gentler than the sea breeze because the temperature difference between land and ocean at night is generally smaller than the difference during the day. Sea breezes and land breezes are local winds, winds that operate over distances of tens of kilometers and are driven by the local contrast between land and sea. But the same fundamental principle: warm air rises, cool air sinks. Pressure differences drive flow, operates at every scale, from the local to the planetary. At the planetary scale, the uneven heating of the Earth by the sun drives a global circulation of the atmosphere that has been operating in essentially the same basic form since the Earth first developed its atmosphere billions of years ago. The tropics receive the most intense solar radiation. The air over the equatorial regions is continuously heated, continuously rising, continuously flowing outward at high altitude toward the poles. At the surface, air flows inward toward the equator from both north and south to replace the rising air. This surface flow toward the equator is the trade wind, one of the most consistent and reliable winds on the planet, blowing from the northeast in the northern tropics and from the southeast in the southern tropics, steady and dependable across the vast expanses of the tropical oceans. Sailors understood the trade winds long before scientists could explain them. The trade winds allowed sailing ships to cross the Atlantic from Europe to the Americas reliably and quickly. They blow so consistently that in the centuries of sail, a captain who understood them could plan a voyage with confidence, departing in the knowledge that the wind would be there day after day, carrying the ship westward across the ocean, the convergence zone, where the northeast trade winds of the northern hemisphere meet the southeast trade winds of the southern hemisphere, is called the intertropical convergence zone, sometimes abbreviated by meteorologists who are fond of their acronyms to the letters I, T, C, Z. This is a zone of rising air, low pressure, and heavy convective rainfall. The thunderstorms and downpours that characterize tropical weather. It is also a zone of light and variable winds at the surface, because the horizontal flow converges here and goes upward rather than continuing horizontally. Sailors of the age of sail knew this zone well and feared it. They called it the doldrums, a word that has passed into common usage to describe a state of stagnation and listlessness. Because a sailing ship caught in the doldrums could be becalmed for days or weeks, drifting with no wind, waiting for the air to move at higher latitudes. The atmosphere organizes itself into a different pattern. The air that rose at the equator and flowed toward the poles at high altitude descends again in the subtropics, roughly between 20 and 30 degrees of latitude north and south of the equator, creating zones of high pressure at the surface. These subtropical high pressure zones are associated with dry, settled weather. The great deserts of the world, the Sahara, the Arabian Desert, the Sonoran Desert, the Australian outback, are located beneath these zones of descending, dry air. The air has lost its moisture by the time it descended, having rained it out over the tropics during its ascent. Now it arrives at the surface dry and warm, and ready to heat the desert surface below it from these subtropical high-pressure zones. Surface winds flow both equatorward, becoming the trade winds, and poleward, becoming the prevailing westerlies of the mid-latitudes. The westerlies are the dominant surface winds of the temperate regions, the winds that carry weather systems from west to east across Europe, North America, and the southern hemisphere mid-latitudes. They are the winds that bring Atlantic weather to Britain, Pacific weather to the western United States, and drive the great storm tracks of the Southern Ocean around Antarctica. The westerlies are not steady and consistent like the trade winds. They are variable, shifting, carrying with them alternating high-pressure systems and low-pressure systems that produce the changeable, unpredictable weather of the mid-latitudes. A week of sunshine in a westerly climate can be followed by a week of rain, followed by more sunshine, followed by a cold snap, followed by warmth again, all driven by the parade of pressure systems moving from west to east on the westerly flow, high above the surface, at the level of the upper troposphere. The mid-latitude atmosphere is dominated by the jet streams, those great rivers of fast-moving air that circle the planet at altitudes of roughly 8 to 12 kilometers. The jet streams are narrow, perhaps a few hundred kilometers wide, but extraordinarily fast. Wind speeds within the core of a jet stream can exceed 300 kilometers per hour. They meander from west to east in great sweeping waves, sometimes dipping far toward the equator, and sometimes swinging far toward the poles, influencing the position of storm tracks and the character of the weather below them. Pilots flying from North America to Europe use the jet stream deliberately, positioning the aircraft in the fast-moving core of the jet to reduce flight time and fuel consumption. A flight from New York to London, riding the jet stream, can be an hour or more shorter than the return journey against it. The jet stream is an invisible river in the sky, and those who understand it can navigate it just as river travelers have always used the current to their advantage, mountain ranges interact with the wind in ways that produce some of the most dramatic and locally distinctive winds on the planet. When moist air is pushed against a mountain range, it rises on the windward side, cools, and produces precipitation. Often heavy precipitation on the slopes facing the wind on the other side of the range. The air descends and warms, but it warms more quickly than it cooled on the way up, because the moisture it contained was rained out on the windward side, and dry air warms more rapidly than moist air as it descends. The result is a wind that arrives on the leeward side of the mountain warm and dry, often dramatically warmer than the air it replaced. This warm, dry, descending wind goes by different names in different parts of the world. In the Rocky Mountains of North America, it is called the Chinook, a word from an indigenous language meaning snow eater, because a Chinook wind can raise temperatures by 20 or 30 degrees Celsius in a matter of hours, melting snow with astonishing speed. In the Alps of Europe, the same type of wind is called the föhn. In the Andes of South America, it is the sonda. In the mountains of Southern California, it is the Santa Ana, each one a local name for the same basic atmospheric process, playing out in a different landscape. Wind carries things with it, not just moisture and temperature, but physical material, dust and pollen, and seeds and spores, and the fine ash of distant fires. Wind is one of the great agents of dispersal and redistribution in the natural world. Seeds that evolved light, feathery appendages, the dandelion clock, the winged samara of the maple, the cottony fluff of the willow, did so because wind is reliable and omnipresent and free. Pollen from a single tree can be carried hundreds of kilometers by the wind, finding flowers it would never otherwise have reached. Fungal spores travel across oceans on the wind. Wind shaped the landscapes of the past in the ice ages, when great ice sheets covered much of the northern hemisphere, and the regions beyond the ice were cold, dry, and largely bare of vegetation. The wind picked up vast quantities of fine glacial dust and carried it southward, depositing it in thick layers across the mid-latitudes. This wind-deposited dust, called less, now forms some of the richest and most fertile agricultural soils on Earth. In the American Midwest, in the river valleys of China, in the plains of Central Europe, the wind built those soils. The wind made them possible. Tonight, the wind is somewhere. It is always somewhere. It may be still where you are, the curtains unmoving, the trees outside quiet, the air in your room as calm as air can be, but a few kilometers away, or a few hundred, or across the ocean, the air is moving. The pressure differences are real. The sun has heated something today that the night is now cooling. The atmosphere is balancing itself, as it always does, in the only way it knows. The wind carries no particular destination. It simply moves from high to low, from warm to cool, from full to empty. It does not choose its path. It does not decide anything. It simply follows the rules of the atmosphere with perfect obedience, going where the pressure gradients lead, shaping itself around the mountains and the coastlines and the forests and the cities, filling every space that is available to be filled. There is something deeply restful in that image. Movement without agenda. Flow without destination. The wind going where the physics takes it, unhurried and unconcerned, doing what it has always done and will always do, long after everything else has changed. Let the thought of wind carry you gently now, not pushing, not rushing, simply moving the way the air moves on a quiet evening when the pressure is changing somewhere far away and the leaves begin, very slowly, very softly, to turn. There is a weight pressing down on you right now, not a heavy weight, not an uncomfortable one. You have never felt it as a burden because you were born into it, and your body was built to carry it without effort or complaint. But it is real, and it is measurable, and it is one of the most important numbers in all of meteorology. It is atmospheric pressure, the weight of the column of air above you, pressing downward on every surface it touches at sea level on an average day. That pressure is roughly equivalent to 1 kilogram pressing down on every square centimeter of surface. Your body, with its many hundreds of square centimeters of skin, is bearing a total force of many tons, balanced perfectly, inside and out, so that you feel nothing. Atmospheric pressure is not constant. It varies from place to place and from day to day, rising and falling in response to the movements and temperatures of the air above. Those variations, small in absolute terms, but enormously significant in their consequences, are what drive the weather systems that shape the climate of the mid-latitudes: high pressure, low pressure, fronts, and troughs and ridges. The whole vocabulary of the weather forecast is built upon the behavior of atmospheric pressure and its relationship to wind and cloud and precipitation. Tonight, we are going to follow that story. Slowly and gently, without hurry. The instrument used to measure atmospheric pressure is the barometer. The word comes from the Greek words for weight and measure. The barometer was invented in the 17th century by Evangelista Torricelli, an Italian physicist and student of Galileo. Torricelli filled a long glass tube, closed at one end, with mercury, and inverted it in a dish of mercury. The mercury in the tube fell until the weight of the column was balanced by the atmospheric pressure pressing down on the mercury in the dish. The height of the mercury column, typically around 76 centimeters at sea level, was a direct measure of the atmospheric pressure. Torricelli's experiment was simple and elegant and immediately profound. It showed that the atmosphere had weight. It showed that that weight could be measured. And it showed that the measurement changed, that the height of the mercury column rose and fell from day to day in ways that turned out to be connected to the weather. Observers noticed quickly that falling pressure, a mercury column that was descending, often preceded stormy, wet, unsettled weather. Rising pressure, a column that was climbing, often preceded clearing skies and settled, fair conditions. The barometer became the first scientific weather forecasting instrument, and its readings have been guiding sailors and farmers and meteorologists ever since. The unit of pressure used in modern meteorology is the hectopascal, sometimes still called the millibar, an older unit of identical size. Standard atmospheric pressure at sea level is defined as 1,013.25 hectopascals. In practice, the pressure at sea level varies over a range of perhaps 100 hectopascals on either side of that standard value, depending on the weather system present. A pressure of around 1,020 hectopascals or above is considered high. A pressure below 1,000 hectopascals is considered low. These are the two great characters of the mid-latitude weather story: the high and the low, the anticyclone and the depression, the settled and the stormy. A high-pressure system, an anticyclone, is a region of the atmosphere where the pressure is higher than in the surrounding air. Air sinks within a high. As it sinks, it warms descending air compresses, and compression generates heat. Warming air can hold more moisture without condensing. So sinking air tends to evaporate cloud rather than form it. This is why high-pressure systems are generally associated with clear skies, settled weather, and sunshine. In summer, a high-pressure system brings warm, sunny days. The air is calm. The sky is blue. Cloud is absent or minimal. The land heats up in the direct sunlight. Temperatures rise. And if the high persists for long enough, a heat wave develops. In winter, the same high-pressure system brings cold, clear, frosty nights. Because with no cloud to trap the warmth, the surface loses heat rapidly after sunset, and temperatures can fall well below freezing under the cloudless sky. Wind around a high-pressure system flows outward from the center, but not in straight lines. The rotation of the earth deflects the moving air sideways, a phenomenon described by the Coriolis effect in the northern hemisphere. The Coriolis effect deflects moving air to the right of its direction of motion. In the southern hemisphere, it deflects air to the left. The result is that wind around a high-pressure system flows in a clockwise direction in the northern hemisphere and anti-clockwise in the southern hemisphere. If you have ever watched a weather map for a northern hemisphere country and noticed the isobars, the lines of equal pressure forming closed loops, and the arrows showing wind direction moving clockwise around the high-pressure center, you have seen the Coriolis effect written in the weather. A low-pressure system, a depression, or cyclone in the general sense, is the opposite of a high. It is a region where pressure is lower than the surroundings, and air converges toward it from all directions. That converging air has nowhere to go but up. It rises in the center of the low. As it rises, it cools, and clouds form, and precipitation follows. Low-pressure systems are the engines of stormy, wet, unsettled weather. Wind around a low flows inward toward the center. But again, the Coriolis effect deflects it sideways. In the northern hemisphere, winds around a low flow anti-clockwise, counterclockwise, swirling inward and upward in a great, slow spiral. In the southern hemisphere, the rotation is clockwise. This rotation is the same basic physics that produces hurricanes and typhoons at tropical latitudes, though those are much more intense, much more organized versions of the same fundamental structure. The mid-latitude depression, the everyday low-pressure system of temperate weather, typically forms along a boundary between two air masses of different temperature and humidity. These boundaries are called fronts, a term borrowed from military usage during the First World War, when the Norwegian meteorologists who developed modern weather analysis felt that the clash of air masses resembled the clash of armies along a front line. A warm front is the leading edge of an advancing mass of warm, moist air. The warm air, being less dense than the cold air ahead of it, rises gently over the cold air, creating a sloping boundary that extends hundreds of kilometers ahead of the surface position of the front. The gradual rising of the warm air over this extended slope produces the characteristic cloud sequence we described in our section on middle clouds. Cirrus, first, then cirrostratus, then altostratus, then nimbostratus, and a long period of steady, often persistent rain. The rain of a warm front is not the dramatic, violent rain of a thunderstorm. It is gentler and more patient. It falls steadily from a thick, gray sky, sometimes for many hours, sometimes for a day or more. It is the rain of autumn and winter in temperate climates. The rain that fills the gutters and drips from the eaves and turns the garden paths to mud. Not spectacular, but thorough. After the warm front passes, the temperature rises because the warm air mass has now arrived at the surface, and the rain often eases. There may be a brief interlude of clearer, milder weather before the cold front arrives. A cold front is the leading edge of an advancing mass of cold, dense air that is pushing under the warmer air ahead of it. Cold fronts are steeper and faster moving than warm fronts. The cold air pushes sharply under the warm air, forcing it rapidly upward. This rapid lifting produces intense convection. Cumulus clouds develop quickly into cumulonimbus, and the weather at the cold front is typically much more dramatic than at the warm front. Heavy showers, thunderstorms, strong and gusty winds, and a rapid drop in temperature all characterize the passage of a cold front. The cold front passes relatively quickly. The dramatic weather at the front itself may last only an hour or two, and in its wake, the air is colder, clearer, and drier. The sky behind a cold front often has that particular quality of clarity and brightness that follows a storm. A deep, sharp blue, with large cumulus clouds building in the fresh, unstable air, their white sides brilliant in the sun, their bases dark with shadow. Sometimes a warm front and a cold front merge to form an occluded front, a more complex boundary where the cold air has caught up with and undercut the warm air entirely, lifting it away from the surface. Occluded fronts produce a mixture of the weather associated with both original fronts, often in a more confused and less predictable pattern. The life cycle of a mid-latitude depression, from the initial initial development of the front through the deepening of the low pressure, the swinging of the fronts around the circulation, to the eventual occlusion and decay of the system, typically takes several days, and during those days, the pressure at the center of the low is falling. The winds are strengthening. The clouds are thickening. The rain is arriving. And the barometer in the hallway is telling the story. Its reading dropping steadily as the low approaches. Meteorologists track these systems using a network of weather stations, weather balloons, aircraft, ships, and satellites that together provide a continuous picture of the state of the atmosphere every 6 hours. Weather stations around the world take simultaneous observations of temperature, pressure, humidity, wind speed, and direction, cloud cover, and visibility. Those observations are fed into computer models, vast mathematical representations of the atmosphere that divide the air into a grid of millions of three-dimensional cells and calculate, using the known equations of atmospheric physics, how each cell will change over the coming hours and days. Modern weather forecasting is one of the great achievements of applied science. A 7-day forecast today is more accurate than a 3-day forecast was 40 years ago. The models are not perfect. The atmosphere is chaotic in the mathematical sense, meaning that small uncertainties in the initial conditions grow rapidly over time, limiting how far ahead any deterministic forecast can be accurate. Beyond about 2 weeks, the detailed day-by-day forecast becomes essentially meaningless. But within a week, modern forecasts are remarkably reliable, and they save lives by providing warning of severe storms, floods, and extreme temperature events. The atmosphere, for all its complexity, follows rules. The rules of thermodynamics, of fluid dynamics, of radiation physics and chemistry. It is not random. It is not arbitrary. It is enormously complicated, but it is lawful. It behaves according to principles that can be understood, described mathematically, and used to predict the future state of the sky above your head with increasing accuracy. The barometer falls, the cirrus thickens. The wind backs around to the south and freshens. The first drops of rain begin to fall. All of it connected. All of it following from the pressure maps and the temperature gradients and the fronts spinning around their low-pressure centers. Out there in the middle of the ocean, making their slow way toward the land, the atmosphere is always telling you what is coming. If you know how to listen, tonight, the pressure is what it is. The fronts are where they are. The weather systems are moving along their paths with their usual patient inevitability. And here inside, it is warm and still and quiet. Let the weather happen out there, in the dark and the distance, far from where you are resting now. The pressure changes, the fronts advance, the rain falls, or doesn't fall on the world beyond your walls, and inside, the air is perfectly still, and you are perfectly still within it. The earth is in a constant conversation with the sun. Every second of every day, energy arrives from across the vast distance of space, streaming outward from the sun in all directions. A tiny fraction of it intercepted by the earth, absorbed, transformed, and eventually returned. This exchange of energy, energy arriving, energy departing, the balance between them, is the fundamental process that determines the temperature of the planet. It is why the earth is warm enough for liquid water to exist on its surface. It is why life is possible here and not, as far as we know, on most of the other worlds in the solar system. And clouds sit at the very heart of this conversation. The energy that arrives from the sun travels through space as electromagnetic radiation, mostly visible light, with significant amounts of ultraviolet radiation and infrared radiation on either side of the visible spectrum. When this radiation reaches the top of the Earth's atmosphere, some of it is immediately reflected back into space, bounced off clouds, off ice and snow, off the atmosphere itself, without ever reaching the surface. The rest penetrates the atmosphere and is absorbed, either by the atmosphere, by the land surface, or by the ocean. The fraction of incoming solar radiation that is reflected back into space without being absorbed is called the albedo, from the Latin word for whiteness. A surface with a high albedo is one that reflects a large proportion of the light that strikes it. Fresh snow has an albedo of around 90%. It reflects almost all the sunlight that hits it. The open ocean has a low albedo, absorbing most of the sunlight it receives. And clouds, depending on their type, their thickness, and their altitude, have albedos that vary enormously, from very low for thin, wispy cirrus to very high for thick, bright cumulonimbus anvils. The global average albedo of the Earth is around 30%. Of all the solar energy that arrives at the top of the atmosphere, roughly 30 parts in every 100 are reflected directly back into space. Clouds account for the majority of this reflection. They are the largest single contributor to the Earth's albedo, reflecting more sunlight back into space than all the land surfaces and ice sheets combined. This reflective roll of clouds has a cooling effect on the planet. By bouncing sunlight back into space before it can warm the surface, clouds reduce the amount of energy available to heat the Earth. Without clouds, the average temperature of the planet would be significantly higher. The surface would absorb more sunlight, warm more, and reach a new, higher equilibrium temperature. But clouds do not only reflect incoming sunlight, they also trap outgoing heat. The Earth's surface, warmed by absorbed sunlight, radiates energy back upward. But it does not radiate energy in the same form as it received it. The sun, being extremely hot, radiates energy primarily as shortwave radiation, visible light. The Earth's surface, being much cooler, radiates energy primarily as long-wave radiation, infrared, which is invisible to the human eye, but detectable as heat. This outgoing infrared radiation is what carries the Earth's absorbed energy back into space, completing the energy balance. But clouds intercept some of this outgoing infrared radiation before it can escape. Cloud droplets and ice crystals are good absorbers of infrared radiation, much better absorbers than they are of visible light. When a cloud absorbs outgoing infrared radiation from the surface below. It warms slightly and re-radiates that energy in all directions, including back downward toward the surface. This is the greenhouse-like warming effect of clouds, and it partially offsets their cooling, reflective effect. So clouds do two things simultaneously and in opposition. They cool the earth by reflecting incoming sunlight, and they warm the earth by trapping outgoing infrared radiation. The net effect of clouds on the planet's temperature at any given moment depends on which of these two effects is larger, and that depends critically on the type, altitude, and thickness of the cloud. Low, thick clouds, stratocumulus, nimbostratus, thick stratus, have a strong cooling effect. Their bases are at low altitudes, meaning their temperature is not much colder than the surface below. They do not trap very much extra heat relative to what the surface itself would radiate. But they are thick and bright, and they reflect a great deal of incoming sunlight. For low clouds, the reflective cooling effect is much larger than the infrared trapping warming effect. Low clouds cool the planet. High, thin clouds, cirrus, cirrostratus, have the opposite character. They are too thin and too sparse to reflect much sunlight. Most of the incoming solar radiation simply passes through them, but they are cold, very cold, at their altitude of 6 to 12 kilometers, and they absorb outgoing infrared radiation from the warm surface below and re-emit it at a much lower temperature, sending significantly less energy into space than would have escaped without the cloud. For high, thin clouds, the infrared trapping warming effect dominates. High clouds warm the planet. The beautiful complexity of clouds in the climate system is that different cloud types have these opposing effects, and the balance between high and low cloud cover at any given moment is what determines whether clouds are on net, cooling or warming the planet at that time. Globally, averaged over the whole planet and the whole year, the cooling effect of clouds slightly dominates. The Earth is somewhat cooler with its cloud cover than it would be in a hypothetical cloud-free world, but the margin is surprising. surprisingly small, and the balance shifts dramatically from region to region and season to season. Over the subtropical oceans, where great sheets of stratocumulus cover the cool water surfaces, the cooling effect of clouds is enormous. These regions would be significantly warmer without their cloud cover. Over the tropics, where deep convective clouds reach high into the atmosphere, the warming and cooling effects are more nearly balanced. The thick bases reflect sunlight, but the high, cold tops trap outgoing infrared over the Arctic and Antarctic, where low clouds sit above snow and ice that is already highly reflective. The geometry of the energy balance produces surprising and counterintuitive results. Scientists have been trying to accurately quantify the effect of clouds on the Earth's energy balance for decades, and it remains one of the most challenging problems in climate science. The difficulty is not with measuring the overall effect. Satellites have been measuring the radiation balance at the top of the atmosphere for many years, and the measurements are quite precise. The difficulty is in understanding how clouds will change as the climate changes, and therefore how the cloud contribution to the energy balance will shift in a warmer world. Will a warmer world have more low clouds or fewer, more cirrus or less? Will the great subtropical stratocumulus sheets thin and retreat, removing their cooling influence and allowing the ocean below to warm further? Or will they thicken and expand, providing a natural break on warming? These are questions that climate scientists are actively working to answer, using satellites and aircraft and surface measurements and climate models of increasing sophistication. The clouds themselves are, in a sense, both a symptom and a cause of climate change. They respond to the changing temperature and moisture of the atmosphere, and in responding, they feed back positively or negatively on the very changes that produced them. A cloud feedback that amplifies warming is called a positive feedback. A cloud feedback that dampens warming is called a negative feedback. The sign and magnitude of the overall cloud feedback in the climate system is one of the key uncertainties in projections of future climate, current evidence assembled from decades of satellite observations and model comparisons suggests that the overall cloud feedback is positive, that as the planet warms, the changes in cloud cover will tend to amplify rather than reduce the warming, but the magnitude of this positive feedback and the regional patterns of cloud change that produce it remain areas of active research. The Earth receives energy. It reflects some. It absorbs the rest. It warms until it radiates enough infrared energy to balance what it absorbs. Clouds shape every part of that balance, modifying how much sunlight reaches the surface, how much infrared escapes to space, and therefore what temperature the surface must reach to achieve equilibrium, the temperature of the world you live in, the temperature of the air in this room, of the summers you have experienced, of the oceans and the mountains and the great plains, is the result of that balance, not a fixed or permanent result, but the current output of a system that is continuously adjusting, continuously responding, continuously finding its temporary equilibrium, and then being nudged away from it by the clouds passing overhead and the sun rising and setting and the ice melting and the forests breathing. The clouds above you tonight are part of that great conversation. They are reflecting some of the sunlight they received today back into space. They are trapping some of the warmth rising from the surface below them. They are tilting the energy balance slightly in their particular direction. And the planet, patient and enormous, adjusts. Think of that balance as something you can rest within tonight. The energy arriving, the energy departing, the world finding its temperature in the space between, an equilibrium maintained not by any single thing, but by the accumulated effect of everything, all acting together, all connected. You are part of that system. Warm, radiating a little heat of your own into the air around you, held in balance by the same laws that hold the planet in balance. Let that thought be the last one that requires any effort. Everything else can simply happen on its own, as it always has, as it always will. The climate of the earth has never been perfectly still. Long before human beings existed, long before any creature walked on land or swam in the sea, the climate was changing. Ice ages came and went, separated by warmer interglacial periods. The continents drifted slowly across the surface of the planet, changing the circulation of the oceans and the patterns of the atmosphere. Volcanic eruptions injected vast quantities of gases and particles into the sky, temporarily cooling the surface. The brightness of the sun itself has changed slowly and continuously over billions of years. Climate change is not new. What is new? What is genuinely unprecedented in the history of the atmosphere is the speed of the change that is currently underway and its cause since the beginning of the industrial era, roughly 200 years ago. Human activity has been adding carbon dioxide and other greenhouse gases to the atmosphere at a rate that has no parallel in the geological record, except for the most violent and catastrophic volcanic events of the deep past. The concentration of carbon dioxide in the atmosphere has risen from approximately 280 parts per million before industrialization to well over 400 parts per million today. A concentration higher than at any point in at least the last 3 million years. This increase in greenhouse gas concentration is trapping more outgoing infrared radiation, warming the surface of the planet. The warming is real, measurable, and unambiguous. The global average surface temperature has risen by more than 1 degree Celsius since the pre-industrial period, with the rate of warming accelerating in recent decades. And within this broad story of warming, clouds play a role that is complex, fascinating, and still not fully resolved. We explored in our last section how clouds affect the Earth's energy balance, reflecting sunlight, trapping infrared, cooling and warming in different proportions depending on their type and altitude. The question that climate scientists are working urgently to answer is this: as the planet warms, how will the clouds change? And when they change, will those changes amplify the warming or resist it? This is not a simple question. Clouds are produced by processes that respond to temperature, humidity, atmospheric circulation, and aerosol content, all of which are changing as the climate changes. The response of clouds to those changes involves physics and chemistry at scales ranging from individual cloud droplets to the global circulation of the atmosphere. It is arguably the single largest source of uncertainty in projections of future climate. Let us begin with what is already being observed. Observations from satellites and weather stations show that over the past several decades, the patterns of cloud cover around the world have been shifting. In the mid-latitudes, storm tracks, the paths along which the great low-pressure systems travel, appear to be shifting poleward toward higher latitudes. This shift carries the associated cloud cover with it, changing the amount of cloud over different regions and affecting how much sunlight reaches the surface in those areas. The subtropical regions, already relatively cloud-free due to their position beneath zones of descending dry air, appear to be expanding. The dry, cloud-free zones are growing larger, extending into areas that once had more cloud cover. This expansion of the subtropics is associated with a poleward shift of the jet streams, itself a consequence of the differential warming of the tropics and the poles. The great stratocumulus sheets of the subtropical oceans, those vast, cooling cloud decks that cover so much of the eastern subtropical ocean surfaces, are being watched with particular attention. There is evidence that these cloud sheets are sensitive to the temperature of the ocean surface beneath them. As the ocean warms, the thermal structure of the lower atmosphere changes in ways that may reduce the extent and thickness of stratocumulus. If the stratocumulus sheets thin and retreat significantly, the ocean's surface beneath them would receive much more direct sunlight, warming further, potentially thinning the clouds still more. A positive feedback loop that could accelerate warming in those regions considerably. Some climate model simulations suggest that under sufficiently high greenhouse gas concentrations, concentrations well above those of today, but not inconceivable under scenarios of continued high emissions. The subtropical stratocumulus sheets could abruptly break up entirely, exposing the ocean's surface to direct sunlight and causing a rapid additional warming of several degrees Celsius in those regions. This scenario is sometimes called a cloud tipping point. Whether the real atmosphere is capable of crossing such a threshold, and at what level of warming it might occur, is an area of intense current research. In the tropics, the relationship between warming and deep convective clouds is equally complex. Warmer temperatures produce more evaporation, putting more water vapor into the atmosphere. More water vapor means more fuel for convection, more energy available to drive the updrafts of cumulonimbus clouds. Tropical storms and thunderstorms may become more intense as the climate warms, even if they do not necessarily become more frequent. The most violent storms, the ones that produce the heaviest rain and the strongest winds, may grow stronger in a warmer atmosphere. At the same time, the anvil tops of tropical cumulonimbus, those high, spreading cirrus canopies that cover vast areas of the tropical upper troposphere, may change their altitude and extent in ways that affect the infrared trapping characteristics of the tropical atmosphere. There is a hypothesis called the iris hypothesis, after the iris of an eye, which suggests that as sea surface temperatures rise, the anvil clouds of tropical cumulonimbus contract, like the iris of an eye contracting in bright light, allowing more infrared radiation to escape to space and providing a negative feedback that moderates warming. The evidence for and against this hypothesis has been debated for decades, and the question is not yet fully resolved. The altitude of cloud tops is itself changing as the troposphere warms and deepens, because a warmer atmosphere supports a higher tropopause. Cloud tops are rising. High clouds are moving to higher altitudes, while their base temperatures remain roughly the same. Higher cloud tops are colder, and colder cloud tops radiate less infrared energy to space, trapping more heat below. This rising of high cloud tops is a positive feedback. It amplifies warming by reducing the escape of infrared radiation, aerosols, those tiny particles that serve as condensation nuclei. Add another layer of complexity to the cloud-climate relationship. Human activity has dramatically increased the concentration of aerosols in the atmosphere over many industrialized regions. And aerosols affect the microphysics of clouds in ways that have significant consequences for the climate system. More aerosols mean more condensation nuclei, which means more but smaller cloud droplets for the same amount of water vapor. Clouds with more, smaller droplets are brighter. They reflect more sunlight, and they are less likely to produce rain because the small droplets do not easily coalesce into raindrops large enough to fall. This brightening and lifetime extension of clouds due to increased aerosols is called the aerosol indirect effect, and it is a cooling influence on the climate. It partially offsets the warming from greenhouse gases, but aerosol concentrations are changing unevenly around the world. In some regions, cleaner energy policies and air quality regulations have significantly reduced aerosol emissions over recent decades. As these aerosols decrease, the clouds seeded by them become dimmer and shorter-lived, and the cooling influence they provided is reduced. In some scenarios, the reduction of aerosol cooling as air quality improves could temporarily accelerate surface warming in those regions, even as the underlying greenhouse gas warming continues. The full accounting of how clouds will change in a warming world, and what those changes will mean for the rate and pattern of that warming, is one of the most challenging problems in all of science. It involves understanding processes that operate at scales from micrometers, the size of a cloud droplet, to thousands of kilometers, the scale of a global cloud regime. It requires observations from the surface, from aircraft, from weather balloons, and from satellites. It requires computer models that can represent both the large-scale circulation of the atmosphere and the fine-scale physics of individual cloud droplets, and it requires a humility before the complexity of the system, an acknowledgement that the atmosphere is capable of surprising us, that it may respond to warming in ways that our models have not fully anticipated. What we do know with confidence is that clouds matter enormously for the future of the climate. A world in which clouds change in ways that amplify warming will be a significantly different world from one in which clouds change in ways that resist it. The difference between those two futures is measured in degrees of temperature, in meters of sea level rise, in the character of the seasons and the severity of the storms. Scientists are working carefully and continuously to narrow that uncertainty. New satellite missions are measuring the radiation balance and the properties of clouds with greater precision than ever before. New field campaigns are gathering observations of clouds in remote and poorly sampled regions. Over the Southern Ocean, over the Arctic, over the deep tropics, new computer models are incorporating cloud physics at finer and finer scales. The clouds are being watched, and slowly, patiently, they are giving up their secrets. But tonight, that work belongs to the scientists in their laboratories and their data centers. Tonight, the clouds outside are simply clouds, doing what they have always done, forming and drifting and reflecting and trapping, following the laws of physics with their usual perfect obedience, indifferent to what any of it means for the long future of the world. They were here before we understood them. They will be here after we have learned everything there is to know about them. Patient, continuous, endlessly varied, always forming somewhere in the sky above a world they have helped to shape and will continue to shape in their quiet and enormous way. For as long as the sun shines and the ocean breathes, rest within that patience now. The clouds above you are ancient in their process, even when they are only moments old in their form. They carry within them the same physics that have governed the atmosphere for billions of years. Nothing about what is above you tonight is rushed. Nothing is urgent. Everything is simply following its nature in the way it always has. And so can you. Most clouds follow familiar rules. They form at predictable altitudes, in predictable conditions, producing predictable weather. You learn their names and their habits, and after a while, you can look up at a sky and read it with reasonable confidence, recognizing the approach of rain in the thickening cirrus, the promise of a settled afternoon in the bright cumulus of a summer morning, the long gray patience of a nimbostratus delivering its steady, unhurried rainfall onto the world below. But the atmosphere is enormously creative, and sometimes it produces things that do not fit the familiar catalog, things that make even experienced meteorologists pause and look again. Clouds that seem to belong to a different world entirely. Clouds of impossible color, impossible shape, impossible altitude. Clouds that glow in the dark. Clouds that roll across the sky like a breaking ocean wave. Clouds that sit perfectly still in a howling wind, smooth and symmetrical and faintly unreal. These are the rare and strange clouds, and tonight we are going to spend time with them slowly, without hurrying past any of them, giving each one the attention it deserves. We begin with noctilucent clouds. Noctilucent means, in Latin, night shining. And that is exactly what these clouds do. They shine at night, not reflecting the light of the moon, but lit by the sun, which has set below the horizon for observers on the ground, but still illuminates these clouds from below because of their extraordinary altitude. Noctilucent clouds form at the very edge of the atmosphere, in the mesosphere, at altitudes of around 80 to 85 kilometers above the Earth's surface. They are the highest clouds in the atmosphere, forming roughly 5 times higher than the highest cirrus clouds of the troposphere. At that altitude, the air is so thin and so cold. Temperatures in the mesosphere can reach minus 130 degrees Celsius or lower in summer, that even the tiny amounts of water vapor present are enough to form ice crystals on meteoric dust particles that serve as condensation nuclei. Noctilucent clouds are most commonly seen in summer at latitudes between about 50 and 70 degrees north, or south. Roughly, the latitudes of Scotland, Scandinavia, northern Canada, and the equivalent southern hemisphere regions, they appear in the deep twilight, after the sun has set, but before the sky is fully dark, glowing with a pale electric blue or silver-white light on the northern horizon. Their brightness and color are unlike any other cloud. They are too bright for the twilight sky around them, too luminous, as though they are lit from within rather than illuminated from without. The structure of noctilucent clouds is delicate and intricate. They show bands, whirls, and wave-like patterns that reflect the complex dynamics of the mesosphere, atmospheric gravity waves, waves in the density of the air, similar in principle to waves on water, but propagating through the atmosphere, create the rippled, banded patterns visible in the cloud. These patterns can change over the course of an hour of observation, the waves slowly propagating through the luminous cloud layer. For centuries, noctilucent clouds were essentially unknown, or at least unreported in the scientific literature. The first confirmed scientific observation of noctilucent clouds was made in 1885, just 2 years after the eruption of Krakatoa, and for many years it was suspected that they might be connected to the material injected into the upper atmosphere by that eruption, but they persisted long after the Krakatoa aerosols had settled, and it became clear that they were a natural, if rare, feature of the upper atmosphere. In recent decades, noctilucent clouds have been observed at lower latitudes than historically recorded, seen occasionally as far south as Central Europe and the northern United States. Scientists believe this expansion may be related to changes in the mesosphere associated with climate change. As the lower atmosphere warms, the upper atmosphere may actually cool, and changes in water vapor transport to the mesosphere may be increasing the frequency of conditions favorable for noctilucent cloud formation. If so, these extraordinary glowing clouds are themselves a kind of signal, a message written in ice at the edge of space, readable by anyone patient enough to to watch the summer twilight from noctilucent clouds at the top of the atmosphere, we descend now to a very different kind of strange cloud, one that forms much closer to the ground, but looks, in its way, equally impossible lenticular clouds, those smooth, lens-shaped formations that develop in the wave patterns downstream of mountains, can take forms that stretch the imagination. A single lenticular cloud is already striking in its stillness and symmetry, but sometimes, when the atmospheric conditions are precisely right, and there are multiple layers of air at slightly different altitudes, all developing waves simultaneously, a stack of lenticular clouds forms above a mountain peak, each lens perfectly centered above the last, each one slightly smaller than the one below, the whole assembly arranged in a precise vertical column. This formation is called a pile of plates, or sometimes a pile de siettes, using the French term. From a distance, the stack of smooth, disc-shaped lenticular clouds above a mountain can look extraordinarily like a stack of plates, balanced one upon another. Or, and this is perhaps the most commonly noted resemblance, like the popular conception of a flying saucer, the resemblance is genuinely striking. The clouds are smooth where other clouds are textured. They are symmetrical where other clouds are irregular. They are stationary where other clouds drift, and they are often somewhat iridescent, showing faint colors along their edges in the right lighting conditions. The iridescence of lenticular clouds deserves its own moment. Cloud iridescence, also called irisation, is a phenomenon in which portions of a cloud show delicate pastel colors, pinks and greens and purples, sometimes arranged in bands parallel to the cloud edge, sometimes scattered in irregular patches. It is produced by the diffraction of sunlight around cloud droplets or ice crystals that are all of very similar size. When droplets are uniform in size and small, as they often are in the freshly formed edges of lenticular clouds and altocumulus, they diffract sunlight at precise angles that depend on wavelength, separating the colors of sunlight and producing the faint, jewel-like display. Cloud iridescence is one of the most beautiful and least noticed optical phenomena of everyday skies. It tends to occur near the sun, which is also where most people avoid looking, and it can appear and fade within minutes, but when you know to look for it, particularly in the thin, fresh edges of lenticular or altocumulus clouds within about 45 degrees of the sun, you will find it far more frequently than you might expect. Morning glory clouds are among the rarest and most extraordinary cloud formations on Earth. They appear as long, rolling tubes of cloud, sometimes a single tube, sometimes a series of parallel tubes, moving rapidly across the sky at low altitudes, typically at sunrise or shortly after. Each tube can be hundreds of kilometers long, and only a kilometer or two above the ground. As the cloud rolls, the leading edge continuously forms new cloud, while the trailing edge dissipates, giving the impression of a cloud that is rolling forward through the sky like a breaking wave. The morning glory is associated primarily with a small region of northern Australia, the Gulf of Carpentaria, where the unique geography of the peninsula and the surrounding seas creates the atmospheric conditions necessary for these extraordinary formations to develop during the spring months, particularly in September and October. Morning glory clouds arrive from the sea in the early hours of the day, rolling silently across the flat landscape, sometimes accompanied by a sudden gust of cool wind. As the wave passes overhead, local Aboriginal communities in the region have known about morning glory clouds for thousands of years, incorporating them into their cultural and spiritual traditions. European meteorologists began studying them seriously only in the latter half of the 20th century. Even now, the precise atmospheric dynamics that produce them are not completely understood. Hang glider pilots and paraglider pilots visit the region specifically to fly within the morning glory cloud, using the powerful updraft on the leading edge of the wave to soar for long distances, skimming along the rolling cloud in a form of flight possible nowhere else on Earth. Mammatus clouds are formations hang from the underside of a cloud. Most commonly, the anvil of a cumulonimbus in rounded, pouch-like lobes that look like a collection of smooth, rounded forms pressed downward from the cloud base above. The name mammatus comes from the Latin word for breast or udder, reflecting the rounded, pendulous appearance of these formations. They are visually extraordinary. An otherwise flat cloud base, suddenly broken by a field of smooth, rounded protrusions hanging down into the clear air below, sometimes extending over an area of hundreds of square kilometers. Mammatus clouds form through a process that is, in some respects, the reverse of ordinary cloud formation. Rather than rising air producing the cloud, in mammatus, it is sinking air descending from the cloud above, carrying ice crystals downward into the dry air beneath the cloud base, where they partially sublimate and produce the rounded pouches. The exact mechanism remains an area of active research, and there may be multiple processes capable of producing the mammatus form. What is certain is the visual impact a sky full of mammatus clouds, particularly when lit by the low, warm light of late afternoon. The clouds often appear beneath the anvil of a nearby or passing thunderstorm is one of the most dramatic and slightly unsettling sights available in the natural sky. The pouches glow amber and gold and deep orange in the slanted light. The sky feels heavy, charged, alive, with recent or approaching violence. It is a sky that feels like a held breath. Kelvin Helmholtz clouds are perhaps the most visually precise of all strange cloud formations. They appear as a series of breaking waves frozen in the sky, a row of curling crests, each one a perfect breaking wave shape, all arranged along a line in the cloud layer. They look as though a section of ocean surface has been lifted into the sky and held there motionless, the waves about to break, but never quite arriving. They are produced by the Kelvin Helmholtz instability, a fluid dynamics phenomenon that occurs at the interface between two fluids moving at different speeds in the atmosphere. When a faster moving layer of air flows over a slower moving layer of different density, interface between them can become unstable. Small ripples develop at the boundary, and these ripples grow into the characteristic breaking wave forms. The process is the same one that produces waves on the surface of the ocean when the wind blows across the water. The wind moving faster than the water, creating the instability that grows into waves. In the sky, Kelvin-Helmholtz clouds are transient. They typically last only a few minutes before the mixing caused by the instability smooths out the wave pattern, and the cloud returns to its ordinary form. They are easy to miss, but when they appear, a row of perfect breaking waves drawn across a cloud layer, impossibly regular, impossibly graceful. They are one of the most memorable sights that the atmosphere produces. Polar stratospheric clouds form in the stratosphere at altitudes of 15 to 25 kilometers during the winter months in polar regions. At those altitudes and in those temperatures, sometimes as low as minus 85 degrees Celsius, the normally dry and cloud-free stratosphere becomes cold enough for clouds to form from the tiny amounts of water vapor and other compounds present. Polar stratospheric clouds are remarkable for their color. Unlike the white or gray of tropospheric clouds, polar stratospheric clouds display vivid, iridescent colors, deep crimsons, electric greens, brilliant purples and golds, shifting and changing as the angle of the light changes. The colors are produced by diffraction and interference of sunlight through the very uniform, very small particles of which the clouds are made. Similar in principle to cloud iridescence, but far more intense and far more saturated. They are beautiful beyond almost any other atmospheric sight. Observers who have seen them from polar research stations in Antarctica or the high Arctic describe them in terms usually reserved for religious or transcendent experiences, colors that seem impossible, light that seems to come from within the sky itself, a display that lasts for an hour or more in the polar twilight, shifting and evolving, never quite the same from 1 minute to the next, but polar stratospheric clouds carry a darker significance. The surfaces of their particles act as sites for chemical reactions that destroy ozone. The same ozone that protects the Earth's surface from ultraviolet radiation, the Antarctic ozone hole, which develops each spring over the southern polar region, is produced in part by reactions occurring on the surfaces of polar stratospheric cloud particles during the polar winter. These are clouds of extraordinary beauty, whose existence contributes to one of the most significant environmental problems of the modern era. Fire clouds, pyrocumulus and pyrocumulonimbus, are clouds generated by the heat of large fires when a wildfire or a volcanic eruption produces enough heat to generate a powerful updraft. That updraft can carry moisture and smoke particles high into the atmosphere, initiating the formation of a cumulus cloud above the fire. If the conditions are right, sufficient moisture, sufficient instability, this cloud can develop rapidly into a full cumulonimbus, complete with lightning. Lightning from a pyrocumulonimbus can then strike the ground around the fire and start new fires, spreading the blaze in directions and at speeds that fire crews cannot easily predict or contain. These fire-generated thunderstorms are among the most dangerous conditions a wildfire can produce. They are increasing in frequency as climate change makes large wildfires more common and more intense. The atmosphere, it turns out, is full of things that have not yet finished surprising us. New cloud types are still being identified. In 2017, the World Meteorological Organization added a new entry to the International Cloud Atlas for the first time since 1951. A cloud type called asperitas, from the Latin word for roughness. Asperitas clouds have a dramatically rough, wave-like underside, like the surface of a turbulent sea viewed from below, the waves illuminated from above. They were identified not by professional meteorologists, but by members of the public, documenting what they saw in the sky with cameras and sharing the images online, until the accumulated evidence became too compelling to ignore. The sky is always looking back, occasionally it shows you something entirely new. Let those extraordinary clouds drift through your imagination now, slowly and without effort. The glowing noctilucent at the edge of space, the stacked lenticulars above a mountain peak, the morning glory rolling silently across a flat Australian dawn, the breaking waves of Kelvin Helmholtz, held for a moment in the cloud and then gone. Strange, beautiful, momentary, there and then not there, like the thoughts that come at the edge of sleep, vivid for an instant, and then dissolving into something softer and quieter, and beyond the reach of description. Let them dissolve now, gently. Everything we have explored so far has been above your head, above the rooftop, above the city, above the highest aircraft and the tallest mountain, but still above your head, still part of the world you were born into, still made of the same water that fills the oceans and the rivers and the glass beside your bed, still lit by the same sun that rises every morning outside your window and sets every evening in the same direction it has always set. But the earth is not the only world with an atmosphere. It is not the only world with clouds. Out in the darkness, beyond the reach of any cloud you have ever seen, other planets are wrapped in their own atmospheres, brewing their own weather, forming their own clouds from entirely different materials, clouds that no human eye has ever seen from the ground, and that our instruments have only recently begun to describe. Tonight we are going to travel, not quickly, not urgently, simply drifting outward from the familiar sky above you, moving through the solar system at the unhurried pace of this late hour, visiting worlds where clouds are made of things that would astonish you, where storms have been raging for longer than human civilization has existed, where the sky is a color you have no word for. We begin close. We begin with our nearest planetary neighbor, and in many ways our most enigmatic one, Venus. Venus is almost exactly the same size as the Earth. It orbits the sun at a distance not dramatically different from our own. In the early history of planetary science, some astronomers hoped, perhaps even expected, that Venus might be a warm, habitable world beneath its perpetual cloud cover, perhaps even teeming with life. The reality is very different. Venus is covered completely and continuously by a thick layer of clouds, not clouds of water, clouds of sulfuric acid. The atmosphere of Venus is composed primarily of carbon dioxide, roughly 96 parts in every 100, and the pressure at its surface is approximately 90 times the pressure of the Earth's atmosphere at sea level. The temperature at the surface of Venus is around 465 degrees Celsius, hot enough to melt lead, hot enough to incinerate any spacecraft that descends through the clouds and reaches the ground. The few Soviet probes that managed to survive the descent in the 1970s lasted less than 2 hours on the surface before they were destroyed by the heat and pressure. The clouds of Venus form at altitudes of roughly 45 to 70 kilometers above the surface, well above the scorching lower atmosphere. They are organized into distinct layers. The upper cloud layer, at around 65 to 70 kilometers, consists of very small droplets of concentrated sulfuric acid, roughly 75 to 95% sulfuric acid by mass. Below this are middle and lower cloud layers with slightly larger droplets and different concentrations. The entire cloud system is extraordinarily thick and reflective. Venus has an albedo of around 70%, making it the most reflective planet in the solar system and the brightest object in the night sky after the moon. Because Venus reflects so much sunlight, it appears brilliantly white when seen from Earth. Ancient observers noted it as the morning star and the evening star, the bright object that appears near the horizon just before sunrise or just after sunset, the first star to appear in the fading light and the last to fade in the growing dawn. The beauty of its appearance in our sky gives no hint of the hellish conditions beneath its cloud layers. Within the cloud layers of Venus, the winds blow with extraordinary speed. At the cloud tops, winds reach 300 to 360 kilometers per hour, circling the entire planet in approximately 4 Earth days. This is remarkable because Venus itself rotates very slowly. A Venusian day is longer than a Venusian year, yet the atmosphere at cloud level is spinning 60 times faster than the planet beneath it. This phenomenon, called superrotation, is not fully understood. The mechanism by which the atmosphere of Venus maintains these extreme wind speeds against the drag of the slowly rotating surface below is an active area of research seen from above. In ultraviolet light, the clouds of Venus show banded and streaked patterns, dark features that rotate with the cloud layer, marking the wind patterns and the distribution of unknown ultraviolet absorbers within the cloud. These dark features have been known for decades, but their chemical identity remains uncertain. Some scientists have speculated, controversially, that the ultraviolet absorbers in the Venusian cloud layer might include microbial life, organisms that evolved to survive in the relatively mild temperatures of the middle cloud layer, around 50 kilometers altitude, where temperatures are close to those of the Earth's surface and pressures are similar to Earth's at sea level. This hypothesis remains highly speculative and contested, but it has not been definitively ruled out. From Venus, we move outward past the Earth and continue to the next planet, Mars. Mars has a thin atmosphere, less than 1% of the pressure of Earth's atmosphere at sea level, composed primarily of carbon dioxide. Its atmosphere is too thin and too cold for liquid water to exist stably at the surface, though water ice is abundant at the poles and in the shallow subsurface, and yet Mars has clouds. Martian clouds are made of water ice, tiny crystals of frozen water, similar in composition to the cirrus clouds of Earth's upper troposphere, forming at altitudes of 10 to 80 kilometers above the Martian surface. They are thin and wispy, often barely visible even to orbiting spacecraft. But they are real, and they show a seasonal pattern more common during the Martian spring and summer in each hemisphere, when warming of the surface and atmosphere generates enough moisture and convective activity to support cloud formation. There is also a type of Martian cloud made of carbon dioxide ice, dry ice clouds. At the Martian poles in winter, temperatures fall low enough for carbon dioxide itself to freeze out of the atmosphere and precipitate as dry ice snow, building the seasonal polar ice caps in the upper atmosphere. Carbon dioxide ice clouds form in the extremely cold mesosphere of Mars. At altitudes above 60 kilometers, analogous in some ways to the noctilucent clouds of Earth's mesosphere, though made of an entirely different substance. Mars also experiences dust storms, and these are perhaps its most dramatic atmospheric phenomenon. Martian dust storms can grow to cover the entire planet in a reddish-brown haze, blocking the sun and reducing surface temperatures significantly. The largest global dust storms on Mars can last for months, shrouding the surface in a continuous veil of fine dust particles lofted high into the thin atmosphere. The dust is so pervasive that it affects the operation of solar-powered spacecraft on the surface. Several Mars rovers have had their missions threatened or ended by the reduction in sunlight during major dust storms. The dust itself gives the Martian sky its characteristic color. On Earth, the sky is blue because air molecules scatter blue light more efficiently than red. The Rayleigh scattering that we will explore in a later section. On Mars, the sky is salmon pink or butterscotch, reddish and warm. Because the fine dust particles suspended in the atmosphere scatter light differently from gas molecules alone, giving the Martian sky a dusty, ruddy warmth that makes it look, in photographs, something like an overcast sunset on a desert world. We move outward now, past the asteroid belt, into the outer solar system. And here, everything changes scale. Jupiter. Jupiter is the largest planet in the solar system, more than 11 times the diameter of the Earth, more than 1,300 times its volume, and Jupiter is, essentially, atmosphere all the way through. It has no solid surface to speak of the atmosphere deepens and compresses until the gases become liquid and eventually a strange metallic state. But there is no ground, no coastline, no surface from which to look up at the clouds above. The clouds of Jupiter are arranged in distinct bands. The famous alternating light and dark stripes that give the planet its characteristic banded appearance. These bands are called zones and belts. The bright zones are regions of rising air and high clouds. The dark belts are regions of descending air and lower, thinner cloud cover. The boundary between zones and belts is marked by powerful jet streams, winds that blow in alternating directions at different latitudes, some eastward and some westward, maintaining the banded structure with remarkable persistence. Jupiter's clouds are arranged in multiple layers at different altitudes and made of different materials. The uppermost cloud layer, visible from space, is composed of ammonia ice crystals, white and bright, forming the light zones. Below this, at somewhat greater depths and pressures, are clouds of ammonium hydrosulfide, a compound formed from the reaction of ammonia and hydrogen sulfide. These clouds are thought to be responsible for the brown and orange coloration of the belt regions. Deeper still are water clouds, though these are largely hidden beneath the upper layers. The colors of Jupiter, the creams and oranges and browns and reds, are produced by complex organic and sulfur compounds whose precise chemistry is not fully determined. The atmosphere of Jupiter is a vast and poorly understood chemical laboratory, driven by solar radiation and the planet's own internal heat, producing compounds and reactions that we can observe from a distance, but have not yet sampled directly. And then there is the Great Red Spot. The Great Red Spot is a storm, an anticyclone, a high-pressure system, in Jovian terms, that has been continuously observed for at least 350 years and may be significantly older. It is large enough to contain the entire Earth within it, with room to spare. For most of recorded observation, it has been even larger. Estimates from the 19th century suggest it may once have been twice its current size. It has been shrinking over the past century or so for reasons that are not fully understood. The great red spot rotates anti-clockwise as a high-pressure system in Jupiter's southern hemisphere should completing a rotation approximately every 6 Earth days. The winds at its edge reach speeds of around 530 kilometers per hour. Its color, that distinctive brick red, is thought to come from complex organic molecules produced by chemical reactions in the upper atmosphere, or possibly from red phosphorus compounds dredged up from deeper layers. The precise chemistry of the color remains uncertain. The great red spot has been there for centuries. It will likely be there for centuries more. It is, in its way, one of the most enduring features of the solar system. A storm that has outlasted empires, that was already old when the first meteorologists were taking their first systematic weather observations on Earth, that was already ancient when Luke Howard was naming clouds in London. Saturn's clouds are similar in structure to Jupiter's, but less colorful, pale yellows and creams and subtle golds, banded in the same way, but with less contrast. Saturn's atmosphere is also thicker with a deeper cloud system, and the lower gravity and faster rotation produce winds even more extreme than Jupiter's. The equatorial jet stream of Saturn moves at around 1,800 kilometers per hour, the fastest sustained winds known on any planet in the solar system. Saturn has, periodically, an extraordinary weather event called the Great White Spot, a massive convective storm that erupts from the planet's atmosphere roughly every 30 Earth years, corresponding to 1 Saturnian year. The Great White Spot expands rapidly from a small, bright feature into a band of turbulence that can encircle the entire planet, persisting for months before gradually fading. The most recent Great White Spot was observed in 2010 and 2011 and was studied in extraordinary detail by the Cassini spacecraft, which was in orbit around Saturn at the time. Uranus and Neptune, the ice giants of the outer solar system, have their own systems. On Uranus, methane in the upper atmosphere absorbs red light and reflects blue-green light, giving the planet its pale aquamarine color. The methane also condenses into thin cloud layers at certain altitudes. On Neptune, similar methane clouds produce a deeper blue color, and the planet shows more active weather than Uranus, including the fastest winds in the solar system at the time of Voyager's visit in 1989, with wind speeds exceeding 2,100 kilometers per hour in some locations. Neptune's great dark spot, a storm system similar in concept to Jupiter's great red spot, observed by Voyager in 1989, had disappeared by the time the Hubble Space Telescope looked for it a few years later. Unlike the Great Red Spot, which has persisted for centuries, Neptune's Great Dark Spot lasted only years. New dark spots have since appeared and disappeared on Neptune, suggesting the planet's atmosphere is more dynamic and less stable than Jupiter's beyond Neptune. In the cold and dark of the outer solar system, even the dwarf planet Pluto has been found to have a thin atmosphere of nitrogen and methane, and evidence of haze layers, thin, bluish bands of photochemical haze produced by the interaction of sunlight with the nitrogen and methane in the upper atmosphere. When the New Horizons spacecraft flew past Pluto in 2015, images of the planet backlit by the sun revealed multiple distinct haze layers extending to altitudes of over 200 kilometers. The haze gives Pluto's thin atmosphere a faint blue color, the same color as Earth's sky, produced by the same Rayleigh scattering phenomenon, but in an atmosphere so thin and so cold and so far from the sun that its very existence is remarkable. The universe, it turns out, is full of clouds, not just in our solar system. Astronomers have detected clouds in the atmospheres of planets orbiting distant stars, exoplanets, as they are called, the atmospheres of hot Jupiters, gas giant planets orbiting very close to their stars, tidally locked so that one side always faces the sun, show evidence of clouds made of iron droplets, or clouds of silicate minerals, liquid rock, condensed and suspended in an atmosphere of hydrogen and helium at temperatures of 1,000 degrees or more on the night side of these planets, where temperatures are lower. Iron and silicate snow may fall from the clouds, raining molten metal onto a surface no spacecraft will ever visit. The clouds of Earth are familiar water ice clouds, our stratus and cumulus and cirrus, our fog and our drizzle and our snow, are modest and gentle things by the standards of the solar system. But they are ours. They are the clouds of a world that has liquid water on its surface, a world of moderate temperatures and remarkable life, a world where clouds form from the simplest and most abundant compound in the universe and fall as rain onto a surface where that rain is immediately useful, immediately life-sustaining, immediately welcome. The clouds of Jupiter and Venus are extraordinary. The storms of Saturn and Neptune are vast beyond imagining. But none of them fall as rain onto a garden. None of them form from the breath of living things. None of them carry in their water the memory of every ocean the water has passed through, every cloud it has been, every mountain stream it has run down, and every leaf it has dripped from. Our clouds are, in their quiet way, the most precious clouds in the solar system. Let that thought drift with you now, outward, and then gently back from the iron clouds of distant exoplanets, from the ammonia ice of Jupiter, from the sulfuric acid veils of Venus, back through the darkness of space, back to the thin blue shell of the Earth's atmosphere, back to the clouds drifting above you right now, made of nothing more than water, lit by nothing more than the sun, close, familiar, quietly extraordinary. To study a cloud, you must first find a way to reach it. That sounds simple enough. Clouds are visible from the ground. You can watch them, photograph them, measure the light they scatter and the radiation they emit. But watching a cloud from below is like watching a river from the bank, informative in some ways, but limited. To understand what is happening inside the cloud, you need to get inside it, to measure the size of the droplets, the concentration of condensation nuclei, the temperature and humidity and updraft velocity within the cloud. You need instruments that are there in the cloud. At the moment, it is forming and evolving, and eventually precipitating or dissipating. Cloud science is, in many ways, the science of getting to difficult places and making careful measurements once you arrive. The tools that scientists use to study clouds are as varied and ingenious as the clouds themselves, from the simplest rain gauge sitting in a garden to satellites carrying instruments of extraordinary sophistication, from weather balloons released at midnight to research aircraft threading through the heart of a thunderstorm. The study of clouds draws on almost every branch of physics, chemistry, engineering, and mathematics. Tonight, we will wander through that world of instruments and expeditions and measurements, gently and without hurry, following the curiosity of scientists who have spent their careers looking at the sky with very careful eyes. We begin at the ground. The most fundamental atmospheric measurement is temperature. Thermometers have been measuring air temperature systematically since the 17th century, and the global network of weather stations that now covers most of the planet has been accumulating temperature records for well over 100 years in many locations. These records are the backbone of our understanding of how the climate has changed, and they provide the surface observations that feed into weather forecast models. Alongside temperature, weather stations measure atmospheric pressure, humidity, wind speed and direction, precipitation, and cloud cover. Cloud cover is recorded in a unit called octaves, eighths of the sky. A sky with no cloud is 0 octaves. A completely overcast sky is 8 octaves. A human observer looks up at the sky, estimates what fraction is covered by cloud, and records the result. This simple human observation, someone looking up and using their judgment, has been the standard method of recording cloud cover for well over a century. And the continuity and consistency of these records makes them invaluable even in an age of satellite observation. Rain gauges measure precipitation, collecting whatever falls from the sky and measuring its depth in millimeters. The simplest rain gauge is a cylinder with a funnel, emptied and read at regular intervals. More sophisticated tipping bucket gauges record precipitation continuously, automatically counting each small measured volume that falls. Disdrometers measure not just the total amount of precipitation, but the size distribution of the raindrops. Information that is connected to how the precipitation formed within the cloud above. Lightning detection networks track every lightning strike across a continent, using the electromagnetic pulses that lightning produces to triangulate the location and intensity of each discharge. These networks provide a continuous, real-time map of thunderstorm activity, invaluable both for aviation safety and for scientific understanding of how severe convective storms are distributed across the landscape, and how that distribution changes with the seasons and the years from the ground. Scientists also look upward with instruments that send energy into the atmosphere and listen for the echo. Weather radar is perhaps the most familiar of these instruments. Familiar because its output, the colored radar map showing where precipitation is falling, has become a standard feature of weather forecasts and smartphone applications. A weather radar transmits pulses of microwave radiation and measures the strength and timing of the echoes that return from precipitation particles in the atmosphere. The strength of the echo tells you how much precipitation is present. The timing tells you how far away it is. And because the radar scans in all directions, sweeping around in a circle and tilting at different angles, it builds up a three-dimensional picture of where precipitation is occurring within a volume of atmosphere extending hundreds of kilometers from the radar site. But whether radar measures precipitation, raindrops and snowflakes and hailstones large enough to scatter microwaves effectively, cloud droplets, which are far too small to scatter microwaves efficiently, are essentially invisible to conventional weather radar to see the cloud itself, the droplets that have not yet grown to precipitation size. You need a different kind of radar, operating at shorter wavelengths. Cloud radar operates at millimeter wavelengths, much shorter than conventional weather radar, and is sensitive enough to detect the tiny cloud droplets that conventional radar misses. Cloud radars have been used both on the ground and in space, building up detailed vertical profiles of cloud structure, showing where cloud layers begin and end, how thick they are, and how the cloud properties change with altitude. The CloudSat satellite, launched in 2006 as part of a NASA Earth observing mission, carried a cloud profiling radar that could measure the vertical structure of clouds from orbit, building up a global picture of cloud thickness and layering with a level of detail never previously available. Over its mission, CloudSat produced an extraordinary dataset showing the three-dimensional structure of clouds across the entire planet, season by season, year by year, providing a global context for the understanding of how different cloud types are distributed and how they interact with the Earth's energy balance. Alongside radar, scientists use LiDAR, an acronym for light detection and ranging, the optical equivalent of radar. LiDAR systems send pulses of laser light into the atmosphere and measure the echoes returned by cloud droplets, aerosol particles, and air molecules. LiDAR is particularly sensitive to thin cloud layers and aerosols that radar misses, and can measure the altitude of cloud bases and tops with great precision. The CALIPSO satellite, launched at the same time as CloudSat and flying in close formation with it, carried a LiDAR instrument that complemented the radar measurements, together providing an unprecedented view of the vertical structure of the atmosphere. Radiometers measure the intensity of radiation at specific wavelengths, the amount of sunlight or infrared radiation passing through the atmosphere or being emitted by clouds by measuring the radiation balance at the top of the atmosphere, how much solar energy arrives, and how much infrared energy departs. Satellites can directly measure the net energy budget of the Earth, the Ceres instruments, clouds, and the Earth's radiant energy system have been measuring this energy budget from orbit since the late 1990s, building a record of how clouds are affecting the radiation balance year by year, whether balloons carry instruments called radiosondes into the atmosphere twice daily from hundreds of stations around the world, simultaneously at midnight and noon in universal time. A radiosonde is a small, lightweight package of sensors that measures temperature, humidity, and pressure as the balloon rises through the atmosphere. A GPS receiver tracks the balloon's position, allowing wind speed and direction to be calculated at every altitude the balloon rises for roughly 90 minutes, ascending at about 5 meters per second, measuring the atmosphere continuously until it reaches an altitude where the decreasing pressure causes it to expand and burst. The radiosonde then falls on a small parachute, and the balloon, or its remains, is occasionally found by someone walking in a field or a forest, wondering at the strange object drifting down from the sky. The radiosonde network is one of the most important data sources for weather forecasting and atmospheric research. The simultaneous, twice daily soundings from hundreds of stations provide a snapshot of the atmospheric profile, temperature, humidity, and wind at every altitude. That feeds directly into the weather forecast models. Without the radiosonde network, modern weather forecasting would be vastly less accurate. But radiosondes are passive observers. They measure the atmosphere, but do not enter the cloud in any controlled way. For in cloud measurements, scientists use research aircraft. Research aircraft are specially equipped planes that fly deliberately into clouds, and in some cases, deliberately into thunderstorms, to collect measurements from inside the cloud itself. These aircraft carry an array of instruments mounted on their wings, fuselage, and nose. Probes that measure the size distribution of cloud droplets and ice crystals. Instruments that count and characterize aerosol particles, sensors that measure temperature and humidity with extreme precision, and cameras that image the cloud particles directly, flying into a cumulonimbus for scientific purposes, requires both sophisticated instruments and considerable courage. Turbulence inside a large thunderstorm can be violent enough to damage an aircraft. Lightning poses a risk, though research aircraft are carefully designed to handle lightning strikes safely. Hail can damage the aircraft's surfaces and instruments. The updrafts and downdrafts within a severe storm can exceed the performance envelope of many aircraft, yet scientists have been flying research aircraft into clouds and storms for decades, gathering measurements that no other technique can provide. The data from these flights, showing the actual size distribution of particles inside a cloud, the actual updraft velocities, the actual temperatures and humidities within the cloud core, is essential for testing and improving the cloud physics schemes used in weather and climate models. Cloud chambers are a different approach entirely. Bringing the cloud into the laboratory rather than taking instruments into the cloud. A cloud chamber is a controlled environment in which temperature and humidity can be precisely adjusted to simulate the conditions inside a real cloud. By introducing aerosol particles into the chamber and cooling it to the dew point, scientists can generate real cloud droplets and ice crystals in a controlled setting and study their properties, their growth rates, their size distributions, their optical properties, their tendency to produce ice with a precision that is impossible in the field. Cloud chambers range in size from small desktop devices used for laboratory experiments in university physics departments to large walk-in facilities where scientists can step inside and experience the cloud directly, wearing cold weather gear and instrumented suits, surrounded by real cloud droplets formed from aerosol particles. They have introduced themselves. Some of the most important discoveries in cloud physics have come from cloud chamber experiments. The Bergeron process, the mechanism by which ice crystals grow at the expense of supercooled liquid droplets, was first understood through a combination of careful outdoor observation and controlled laboratory experiment, the conditions under which certain aerosol types promote ice nucleation, the formation of ice crystals, have been painstakingly mapped in laboratory cloud chambers, building up a picture of which particles are most effective at triggering the formation of ice in real clouds. Satellite observation has transformed cloud science over the past 4 decades, providing the global coverage that no ground-based or aircraft measurement network could ever achieve from their orbits hundreds of kilometers above the surface. Weather satellites observe the entire Earth at intervals of minutes to hours, measuring cloud cover, cloud top temperature, the reflection of sunlight, and the emission of infrared radiation. Geostationary satellites sit in orbits above a fixed point on the equator at an altitude of approximately 35,000 kilometers, rotating with the Earth so that they remain stationary relative to the surface. From this vantage point, a geostationary weather satellite can observe an entire hemisphere continuously, tracking the development and movement of weather systems in real time. The images they produce, the familiar animated cloud maps that appear in weather forecasts, are updated every few minutes, providing a continuous movie of the atmosphere's behavior across an entire ocean basin. Polar orbiting satellites fly in lower orbits that take them over the poles, scanning a different strip of the Earth with each orbit. Over the course of a day, a polar orbiting satellite covers the entire Earth, building up a complete global picture. The measurements from polar orbiters are more detailed and more spectrally diverse than those from geostationary satellites. They can observe in many more wavelengths of light and measure cloud properties with greater precision. But they see any given location less frequently. Computer modeling is the final essential tool in the cloud scientist's kit. Weather forecast models and climate models represent the atmosphere as a three-dimensional grid of cells, each one perhaps 10 or 20 kilometers wide in a global weather model, perhaps 1 kilometer wide in a high-resolution, cloud-resolving model within each cell. The equations of fluid dynamics and thermodynamics are solved repeatedly, stepping forward in time, predicting how the temperature and humidity and wind in each cell will change from one moment to the next. Cloud physics must be represented within these models, but the details of cloud formation and evolution happen at scales far smaller than any model grid can resolve. A cloud droplet is micrometers across. A model grid cell is kilometers across. The physics of individual droplets must be compressed into mathematical formulas called parameterizations that represent their collective behavior at the scale of the model grid. Getting these parameterizations right is one of the central challenges of atmospheric modeling, and it is the reason that cloud processes remain the largest source of uncertainty in climate projections. Scientists working on cloud parameterization use data from all the other sources we have described: rain gauge networks, radar, LIDAR, radiosonde profiles, research aircraft measurements, cloud chamber experiments, and satellite observations to test and refine their mathematical representations of cloud behavior. It is painstaking, iterative work, moving slowly toward a better and better description of clouds in models that are themselves running on some of the most powerful computers in the world. All of this effort, the weather balloons released in the dark, the research aircraft threading through storms, the satellites staring down at the Earth from orbit, the scientists in cloud chambers surrounded by laboratory fog, is directed toward understanding something that you can see simply by looking up, something that has been there your entire life, something that anyone, anywhere, with nothing more than their own eyes and a little patience, can observe. The clouds do not make themselves difficult. They are there in the sky, visible and present and continuous. It is the understanding of them that takes the work. The patient, careful, ingenious work of people who have decided that the sky is worth knowing, not just worth watching. And in that work, as in all science, the reward is not just knowledge, but something harder to name, the deepening of wonder. The discovery that a thing you thought you understood has layers you never suspected, that the simple white cloud drifting over the rooftop is, on closer inspection, a system of extraordinary complexity, governed by physics that took centuries to understand, connected to processes that span the entire planet, shaped by particles that began their journey on the other side of the world. The more you know about clouds, the more remarkable they become. Let that thought rest with you softly now. The clouds above you tonight have been studied and measured and modeled and observed from space. Instruments have been sent into clouds like themselves to measure their droplets and their temperatures. Satellites have mapped their extent and their reflectivity. Scientists have thought about them for decades, and still they drift quietly, carrying their water from one place to another, following the physics, indifferent to being understood, endlessly patient, endlessly present, endlessly moving through a sky that belongs to everyone who cares to look up. Long before there were instruments to measure them, there were people watching clouds. From the very beginning of human experience, from the first moments that any creature capable of wonder looked up at the sky, clouds were there, moving, changing, sometimes bringing rain onto dry ground, sometimes withholding it, sometimes casting cool shadow over a hot landscape, sometimes parting to let the sun through, present every day, in every climate, on every continent, at every moment of recorded history, and the long, unrecorded history before it. And people, being people, did not simply observe the clouds. They thought about them. They told stories about them. They read meaning into them, gave them names in languages we no longer speak, made them the dwelling places of gods and the vehicles of divine communication, painted them in pigments ground from minerals and mixed with oil, wrote about them in poems composed in 100 different languages across 5,000 years of recorded literature. Clouds have always been more than weather to the human imagination. They have been symbols. They have been characters. They have been, in the oldest and most most literal sense of the word. Signs, things that pointed beyond themselves to something else, something larger, something that mattered. Tonight, we are going to wander through that long history. Slowly, unhurriedly, the way you wander through a museum on a quiet afternoon when you have nowhere else to be. In the oldest religious traditions of the ancient world, clouds were the medium through which the divine communicated with the human. The gods lived above the mountains, above the clouds, in the high and unreachable places of the sky. When they wished to speak to the world below, they descended in cloud. Cloud was the veil between the divine and the mortal, the membrane through which the sacred became visible without becoming fully present. In the Hebrew Bible, the presence of the divine is repeatedly expressed through cloud. A pillar of cloud leads the people through the wilderness. The cloud settles on the mountain when Moses receives the law. The cloud fills the newly built temple as a sign of divine presence. Cloud is not merely weather in these texts, it is a theological category, a way of speaking about the nearness of the sacred, the closeness of something ordinarily too vast and too brilliant to be directly seen. In ancient Greek tradition, the clouds were the Nephilim nymphs who personified clouds, daughters of the great ocean, companions of the sky gods. Aristophanes wrote a comedy called The Clouds, in which the Nephilim appear as characters on stage, personifications of the atmosphere, both realistic and absurd, both natural phenomenon and comic presence. The play is partly a satire of intellectual pretension, but the choice of clouds as its central figures says something about how deeply embedded the clouds were in the Greek imagination. Familiar enough to be funny, significant enough to be meaningful. Zeus, king of the Olympian gods, was the cloud gatherer, Nephelegereta in Greek, the one who assembles the clouds. His authority over weather was part of his authority over the world, and clouds were his most immediate instrument. When Zeus wanted rain, the clouds gathered. When he wanted thunder, the clouds flickered with lightning. The clouds were not separate from divine power. They were its visible expression in Hindu tradition. The clouds, Meg in Sanskrit are associated with the monsoon, and the monsoon is associated with life. India's agricultural calendar, for much of its history, was organized entirely around the arrival and departure of the monsoon rains. When the rains came, the land turned green and the rivers filled and the crops grew. When they were delayed or failed, people went hungry. The stakes of cloud watching in monsoon India were existential in a way that is difficult for people in well-watered, temperate climates to fully appreciate. The god Indra in Vedic tradition was the lord of storms and rain, the wielder of the thunderbolt, the rider of the monsoon clouds, the one who split open the cloud serpent Vritra to release the waters imprisoned within. This myth, the dragon or serpent who hoards the waters and must be defeated to release them as rain, appears in various forms across many ancient cultures, speaking to the universal human experience of waiting for rain, of watching the clouds build and praying they would break. The great Indian poet Kalidasa, writing in the 4th or 5th century of the Common Era, composed a poem called the Meghajuta, the Cloud Messenger. In it, a spirit exiled from his home in the Himalayas begs a passing monsoon cloud to carry a message to his beloved, describing the landscape and cities the cloud must pass over on its journey northward. The poem is a meditation on longing and separation and the indifference of the natural world to human emotion. And it uses the cloud, that moving, shapeless, purposeless traveler, as the perfect image of a messenger who carries everything and guarantees nothing. The Meghajuta inaugurated a tradition in Sanskrit literature of cloud poems, poems in which clouds carry messages, in which the movement of clouds across the sky is read as an expression of longing or separation or the passage of time. The cloud in this tradition is both literal and metaphorical, a real weather phenomenon and a vehicle for the expression of emotion so powerful that it could not be contained in ordinary human speech. In Chinese culture, clouds have had a long and rich symbolic life. The Chinese character for cloud, yun, appears appears in some of the oldest surviving Chinese writing, inscribed on oracle bones more than 3,000 years ago. Clouds in Chinese art and philosophy represent transformation, the constant change from one state to another that characterizes all of existence. The cloud is never fixed. It is always becoming something else. It is the visible embodiment of the Taoist principle that all things are in flux, that nothing endures in its current form, that the attempt to grasp and hold any state of being is as futile as trying to hold a cloud in your hands. Chinese landscape painting, developed over many centuries, a sophisticated vocabulary of cloud depiction that is quite unlike the realistic representation of clouds in Western painting. Chinese clouds are simplified, formalized, rendered as curves and spirals, and stylized forms that suggest cloudness without attempting photographic accuracy. They exist not as meteorological observations, but as philosophical statements about the nature of the world. The mountains emerging from mist, the peaks dissolving back into cloud, the boundary between the solid and the vaporous, always soft and always shifting. In the art of Japan, clouds appear similarly, both as elements of landscape and as formal decorative motifs. The Kumagata cloud form is a recurring pattern in Japanese decorative arts, appearing on ceramics, textiles, lacquerwork, and architectural ornament. It is at once a representation of the natural sky and an abstract pattern, something between observation and convention, between the seen world and the designed world. In the indigenous traditions of the American Southwest, among the Hopi, the Zuni, the Pueblo peoples, clouds have a profound religious significance. The clouds are the homes of the Kachinas, spirit beings, who mediate between the human world and the divine. Cloud imagery is pervasive in the visual art of these cultures, on pottery, on woven textiles, in sand paintings, in the symbolic language of ceremony. The cloud is not simply a sign of coming rain. It is a living presence, an ancestor, a manifestation of the sacred in the visible world. The connection between clouds and rain, and between rain and life, is so fundamental in agricultural societies that clouds become sacred almost automatically, because the sacred is, in its most basic definition, that on which survival depends. In places where rain is reliable and plentiful, clouds may be taken for granted. In places where rain is scarce and uncertain, where the difference between a good year and a disastrous one is measured in the millimeters of water that fall from the sky, clouds become objects of prayer and ceremony and profound cultural significance. Rain dances, cloud prayers, ceremonies timed to the agricultural calendar, the reading of cloud signs as a form of divination. These practices appear across human cultures with a consistency that speaks to the universality of the human relationship with rain and the clouds that bring it. The specific forms differ enormously from one culture to another. The underlying need, the need to feel some connection to the forces that govern whether the rain comes or not, is the same everywhere. In Western painting, clouds have been a subject of serious artistic attention since the Renaissance, but it was in the 18th and 19th centuries that they became a subject of systematic study and passionate depiction. John Constable, the great English landscape painter of the early 19th century, made cloud study a central and deliberate part of his artistic practice. He spent the summers of 1821 and 1822 making rapid oil sketches of the sky above Hampstead Heath, a hill overlooking London, returning day after day to capture the clouds in different conditions: cumulus, cirrus, storm clouds. The complex layered skies of changeable English weather. These cloud sketches are among the most direct and immediate works in the history of landscape painting, done quickly outdoors in changing light, with no attempt to prettify or compose. They are observations, as rigorous in their way as any scientific notation. Constable wrote that the sky was the chief organ of sentiment in a landscape painting. The part of the picture that set the emotional tone and unified everything below it. He was aware of Luke Howard's cloud classification classification. Howard was his contemporary, and he brought to his cloud studies something of the same spirit of careful, systematic observation that Howard brought to his taxonomy, art and science in the early 19th century were not yet as separated as they would later become, and Constable's cloud sketches exist comfortably in the space between them. J.M.W. Turner, Constable's great contemporary and rival, approached clouds very differently. Where Constable sought accuracy, Turner sought atmosphere, the emotional truth of weather rather than its meteorological fact. Turner's skies are vortices of light and color, storms and sunsets rendered with a freedom that sometimes makes it difficult to identify any specific cloud type within them. He was painting what weather felt like rather than what it looked like. And in doing so, he produced some of the most emotionally powerful representations of sky and cloud in the history of art. Turner had a particular obsession with light. The way light changes color and intensity as it passes through different thicknesses of atmosphere, the way it scatters and reflects and transforms everything it touches. His late paintings, in which forms dissolve into swirling veils of color, and the distinction between sky and cloud and light becomes almost impossible to maintain, were bewildering to many of his contemporaries. They understood them only much later as a prefiguring of the Impressionists, and later still as something even more radical, a dissolution of the visible world into pure sensation. The Impressionists, Monet, Pissarro, Sisley, Renoir, made the sky a central subject of their practice, driven by their commitment to painting outdoors, in front of the motif, in changing light and weather. Monet's series paintings, the haystacks, the Rouen Cathedral, the Thames in fog, are essentially studies in how the same subject appears differently under different light conditions, different weather, different cloud cover. The clouds are not the subject of these paintings, but they are the condition that makes the subject what it is at any given moment. In poetry, clouds have been a constant presence across every literary tradition. The romantic poets of the early 19th century, Shelley, Keats, Byron, Wordsworth, found in clouds an image of the sublime. The natural world at its most overwhelming, most beautiful, most indifferent to human concerns. Percy Bysshe Shelley wrote a poem called simply The Cloud, a poem in which the cloud speaks in the first person, describing its own existence as an endless cycle of evaporation and precipitation, formation and dissolution. The cloud in Shelley's poem is immortal, not because it never dies, but because it never truly ends. It transforms. It changes form. It becomes rain, becomes ocean, becomes vapor, becomes cloud again. The immortality of the cloud is the immortality of matter in continuous transformation. The same immortality that belongs to every water molecule now falling as rain. William Wordsworth found in clouds, as in all of nature, a presence that communicated something beyond ordinary experience. His poem about daffodils, perhaps the most widely memorized poem in the English language, begins with the line that places the poet as a cloud, wandering lonely as a cloud, he writes. The cloud is the image of solitary, purposeless wandering, moving without destination, without intention, simply drifting on the currents of the world. In the 20th century, the Japanese poet Matsuo Basho's tradition of haiku, poems of 3 lines, 17 syllables, found in clouds, and whether an inexhaustible subject, the brevity of the haiku form captures something essential about clouds. The way they change too fast for extended description. The way a single image can hold more truth than a paragraph of explanation. A cloud appears in a haiku as it appears in the sky, briefly, precisely, and then it is gone. In music, clouds have inspired everything from gentle pastoral evocations. Debussy's Nuages, the 3rd of his nocturnes for orchestra, in which the strings and woodwinds drift and shift in long, slow harmonies that feel genuinely like watching clouds move, to the dramatic storm sequences in Beethoven's Pastoral Symphony, to the brooding atmospheric textures of 20th century composers who found in cloud, and whether an image of sound itself, sound as something shapeless and continuously changing, never quite the same from one moment to the next, never quite arriving at a final resting point. Weather and clouds in particular have shaped human language in ways we rarely notice. We speak of being on cloud 9, an expression derived from a cloud classification system used in a 1950 edition of the United States Weather Bureau's Cloud Atlas, in which cumulonimbus, the tallest and most dramatic of clouds, was designated Cloud 9. To be on Cloud 9 is to be at the highest point, the most elevated, the most exhilarated. We speak of every cloud having a silver lining, a phrase that reflects the actual optical phenomenon of a cloud edge illuminated by the sun behind it. The dark cloud bordered by a bright fringe of scattered light. The metaphor translates the visual observation directly into emotional meaning. Within the darkness, there is brightness at the edge. We speak of being under a cloud, meaning under suspicion or in disgrace, and of the clouds lifting, meaning the resolution of difficulty or sorrow. We speak of cloudless days as perfect days, of cloudy prospects as uncertain ones, of someone with their head in the clouds as someone disconnected from practical reality. The sky and the clouds within it have given the English language and every other language a whole vocabulary of metaphor, rooted in the daily experience of looking up and reading what is there. The cloud that drifts above you tonight is part of this long story. It has been watched and named and painted and prayed over and written about in 100 languages by people who lived in circumstances unimaginably different from yours, and yet who looked up at a sky that was, in its fundamental physics and its daily variation, exactly the same sky you look up at, the same clouds, the same questions, the same wonder. Something in the human heart, it seems, has always looked at the sky and found it worth looking at, worth thinking about, worth singing about and painting and writing down. Let that continuity settle over you now as you lie still in the quiet dark. Above you, the same clouds that have been forming and drifting and dissolving over this patch of sky since long before any building was here, before any road, before any human voice spoke in this part of the world. The sky does not remember any of it, but we do. We carry it with us in our language, in our art, in the instinct that makes us look up. Even now, even in the ordinary course of an ordinary day, and feel that the clouds are worth a moment's attention. They always have been. The sky has no color of its own. It borrows its color from the light that passes through it, from the sun, whose white light is a mixture of every color the human eye can see, and from the gases and particles that the light encounters on its journey through the atmosphere. The blue of a clear day, the gold of late afternoon, the deep crimson of a long sunset, the silver gray of an overcast morning. None of these are properties of the sky itself. They are what happens when light and atmosphere meet, when photons of different energies are scattered and absorbed and redirected by the molecules and particles of the air, producing the extraordinary palette of colors that has been looking down on human life. Since the first morning there was any life to look up, understanding the colors of the sky is understanding the interaction of light with matter at its most elegant and its most fundamental. And tonight we are going to follow that understanding slowly and carefully from the blue of a clear noon sky all the way through the burning colors of twilight and into the pale and curious light that comes after the sun has set. We begin with blue. A clear sky is blue because of a process called Rayleigh scattering, named after Lord Rayleigh, the 19th century British physicist John William Strutt, who first described the mathematics of how small particles scatter light. Rayleigh scattering occurs when light encounters particles that are much smaller than its wavelength. The molecules of nitrogen and oxygen that make up the bulk of the atmosphere are far smaller than the wavelengths of visible light, and they scatter light in a very particular way. The key property of Rayleigh scattering is its dependence on wavelength. Short wavelength light, the blue and violet end of the visible spectrum, is scattered much more strongly than long wavelength light. The red and orange end, the relationship is steep. Blue light is scattered roughly 10 times more strongly than red light. This means that as sunlight passes through the atmosphere, blue light is continuously redirected in all directions by the gas molecules, scattered sideways and downward, and at every angle, while red light passes through more or less undisturbed, continuing on its original path. When you look up at the clear blue sky, you are not looking directly at the sun. You are looking at the atmosphere, at the light that has been scattered sideways out of the direct solar beam and redirected toward your eyes from every part of the sky. That scattered light is enriched in blue wavelengths, because blue is what the atmosphere preferentially redirects. The sky is blue because the atmosphere is, in effect, a vast and diffuse blue light source, illuminated by the sun, and scattering that blue light in all directions. You might wonder why the sky is not violet. Violet light has an even shorter wavelength than blue, and should therefore be scattered even more strongly. The answer lies partly in the spectrum of sunlight. The sun emits somewhat less violet light than blue, and partly in the sensitivity of the human eye. The 3 types of color receptors in the human retina, the cones, are sensitive to red, green, and blue wavelengths. Violet light stimulates both the blue cones and, weakly, the red cones, producing a sensation that is interpreted as blue-violet rather than pure violet. The brain interprets the scattered light of the sky as blue, even though violet is present, because of the particular way human color vision is constructed. The blue of the sky is deepest at the zenith, directly above, where you are looking through the least possible thickness of atmosphere, and the background against which the scattered light is seen is the darkness of space near the horizon. The blue is paler and slightly whiter, because there you are looking through a much greater thickness of atmosphere, and more of all wavelengths have been scattered by the time the light reaches your eyes, diluting the blue with white. In the highest mountain environments, above most of the atmosphere's mass, the sky at the zenith is noticeably darker and more intensely blue. The reduction in atmospheric thickness makes the scattering less complete, and the background darkness of space becomes more apparent. Astronauts in orbit see no blue sky at all, only the unmediated blackness of space, with the sun, a brilliant, unscattered white disk. The color of the sky also depends on what is in the air after a major volcanic eruption. Fine particles of sulfuric acid aerosol in the stratosphere can scatter additional light, sometimes making the sky appear a slightly different shade of blue, sometimes slightly milkier, sometimes slightly more intensely colored. The eruption of Krakatoa in 1883 produced spectacular and unusual sky colors around the world for months afterward, inspiring the vivid crimson skies depicted in Edvard Munch's famous painting The Scream. Though scholars debate whether Munch was directly depicting a post-Krakatoa sky, or simply using extreme color for emotional effect in heavily polluted urban air, where large aerosol particles scatter all wavelengths more equally. The blue of the sky is diluted toward white or gray. The pristine blue of a sky over a remote ocean or a high mountain is noticeably different from the hazy, whitened blue of a sky over a city. The difference is visible to anyone who has traveled between such environments. Now we move the sun toward the horizon. As the sun descends from its noon position toward the edge of the sky, it travels an increasingly oblique path through the atmosphere. The thickness of atmosphere the sunlight must traverse to reach your eyes increases dramatically, so as the sun approaches the horizon. Near the horizon, sunlight is passing through many times more atmosphere than it passes through when the sun is overhead. The path length through the air at sunset is roughly 40 times longer than the path length at noon. With this much longer path through the atmosphere, much more scattering occurs. The blue light, already the most strongly scattered wavelength, is redirected away so thoroughly that almost none of it remains in the direct solar beam. By the time it reaches your eyes, what is left is the long wavelength light, the reds and oranges, yellows that the atmosphere scatters least efficiently. The sun turns orange, then deep red as it descends. The sky near the horizon glows with warm colors that deepen and intensify as the sun approaches the edge. But the colors of sunset are not limited to the vicinity of the sun. The light from the low sun strikes clouds at different angles and different altitudes, illuminating them with the warm, reddened light of the horizontal beam. High clouds, cirrus and cirrostratus, may catch this light while the lower sky is still in twilight, glowing in extraordinary golds and roses and purples, while the landscape below is already moving into shadow. The sequence of colors as the sun sets, from yellow to orange, to deep red to crimson, to purple to the deep blue of evening, is produced by the continuously changing path length of sunlight through the atmosphere, each color appearing as the sun's angle changes by a fraction of a degree. The best sunsets are not produced by a perfectly clear sky. They require clouds, specifically clouds at mid and high altitudes that catch the reddened, slanted light and scatter it back toward the observer in vivid colors. A sky with thin, broken cirrus or altocumulus above the western horizon will produce a far more spectacular sunset than a completely clear sky, because those clouds act as screens on which the colors of the setting sun are projected. The most extraordinary sunsets, the ones that make people stop what they are doing and simply look, are the product of exactly the right arrangement of clouds at exactly the right altitude, lit by exactly the right angle of fading light. There is a brief atmospheric phenomenon that occurs at the very moment the sun's upper edge disappears below the horizon, visible only under the right conditions of atmospheric clarity and a clean, sharp horizon, usually over the ocean. It is called the green flash. For a second or less, sometimes barely more than an instant, the last sliver of the setting sun appears green rather than red. This is produced by the atmosphere acting as a prism. The different wavelengths of light are refracted, bent by slightly different amounts as they pass through the atmosphere at the low angle of the setting sun. Red light, being least refracted, disappears below the horizon first. Blue and violet light, being most refracted, should appear last. But they are also most scattered by the atmosphere, and in all but the cleanest conditions, they are too dim to see. Green light, in the middle of the spectrum, in terms of refraction, appears last in conditions where the atmosphere is clear enough that some of the scattered green light survives to reach the observer's eyes. The green flash is brief, small, and easy to miss. A sudden change of color at the very last instant of the setting sun, lasting perhaps a second at most, sometimes less. It is real, not a legend, not an optical illusion, not a trick of the imagination, though it has sometimes been dismissed as such by people who have not seen it. Sailors who spent long hours watching ocean horizons were among the first to describe it consistently. Jules Verne wrote a novel in which a character searches for the green flash, believing that those who see it gain the ability to read the hearts of others. The green flash has the quality of a natural secret, something that rewards the patient and the attentive, something that is there for those who look carefully at the right moment. After the sun sets, the colors of the sky do not immediately vanish. The atmosphere continues to scatter and refract the light of the sun below the horizon, producing the sequence of colors we call twilight. Civil twilight is the period when the sun is less than 6 degrees below the horizon. The sky is still bright enough for most outdoor activities without artificial lighting. The western horizon glows with warm colors that fade upward through yellow and pale green into the deeper blue of the higher sky. Nautical twilight follows the sun between 6 and 12 degrees below the horizon. The horizon is still faintly visible, sufficient for navigation by sea, but the sky above has darkened significantly. Stars begin to appear at the zenith. Astronomical twilight is the last stage. The sun between 12 and 18 degrees below the horizon. The sky continues to darken, and by the end of astronomical twilight, the sky is dark enough for serious astronomical observation. The last traces of the sun's indirect influence on the sky's brightness have faded. During twilight, a beautiful phenomenon occurs on the eastern horizon that many people notice without knowing its name. The belt of Venus, also called the anti-twilight arch, is a pink or rosy band visible in the sky opposite the sun, just above the eastern horizon, separated from the darkening blue sky above it by a distinct boundary. It is produced by the reddened light of the setting sun, illuminating the atmosphere above the horizon in the east, and its boundary with the blue above it marks the edge of the Earth's shadow, the shadow of the planet itself, cast into the atmosphere. You are seeing in the belt of Venus the rounded silhouette of the Earth projected onto the sky. The shadow of the Earth on its own atmosphere, visible to the naked eye every clear evening by anyone who knows to look east when the sun sets in the west. There are very few natural phenomena that make the scale and geometry of the Earth so immediately and so simply apparent. After full dark, the colors of the sky are subtler. The deep blue-black of clear night air, the milky glow of the Milky Way in places dark enough to see it, the faint luminescence of air glow, a steady, faint emission of light from the upper atmosphere, produced by chemical reactions between atoms that were energized by sunlight during the day and are now releasing that energy as light in the dark. Air glow is too faint to see with the naked eye under ordinary conditions, but it is bright enough to be visible to long exposure cameras and to slightly brighten the night sky above the natural darkness of space. The rainbow deserves its own quiet moment here, because it is the most vivid and most beloved of all the color effects produced by the atmosphere. A rainbow appears when sunlight enters spherical water droplets, rain droplets falling through the air, is refracted as it enters the droplet, reflected off the inside back surface of the droplet, and refracted again as it exits. The two refractions separate the colors of sunlight by wavelength, just as a glass prism separates them, producing a spectrum, red on the outside, violet on the inside, the other colors arranged in order between them. Each color emerges from the droplet at a slightly different angle, and the rainbow you see is composed of light from an enormous number of droplets, each one contributing its particular color from its particular position in the sheet of falling rain. The arc of the rainbow is always centered on the point directly opposite the sun, the antisolar point, which is below the horizon when the sun is above it. This is why you can only see a rainbow when the sun is behind you and the rain is in front of you, and why the rainbow is always a semicircle or less. The full circle would extend below the horizon from an aircraft above a rain shower, with the antisolar point visible below. A complete circular rainbow is sometimes seen. The colors of the natural world, the blue sky, the golden afternoon, the crimson sunset, the silver gray of fog, the vivid arc of a rainbow against dark rain clouds, are all products of the same fundamental physics, light interacting with matter, photons scattering and refracting and absorbing, each wavelength behaving slightly differently from the others. The differences accumulating over distance until what began as white sunlight has been transformed into something the human eye experiences as color. The sky is a prism. The atmosphere is a lens. The clouds are screens and reflectors and diffusers. And the light passing through all of it arrives at your eyes having been shaped and colored by the most elaborate optical system in the solar system, the atmosphere of a living planet, full of molecules and particles and water in every form, all of them interacting with the light of a star 93 million miles away. That is what you are looking at when you look at the sky. That is what all of this color means. Let that knowledge soften into feeling now, the way the light softens in the hour after sunset, gently, without drama, the sharp colors fading into something quieter and cooler and deeper, the sky moving from gold through rose, through blue, through the first deep dark of evening. The colors are going now, one by one. The blue is deepening. The last warmth is fading from the horizon, and the night sky above you is soft and very dark and full of quiet light. There is something about a cloud that invites the mind to wander, not in a deliberate way, not with any intention. Simply you look up and the cloud is there, and your mind begins to move with it. It finds a shape in the shifting white, a face, a horse, a continent seen from above, a figure reaching for something just beyond its grasp. The cloud does not have these shapes, not really, not objectively, not in any way that another observer looking at the same cloud from a slightly different angle would necessarily agree with, but your mind puts them there effortlessly, without being asked. This tendency, the tendency to find meaningful patterns in random or ambiguous visual information, has a name: pareidolia, from the Greek words for beside and image. It is the same tendency that makes us see faces in the grain of wood, in the markings of a stone, in the shadows of a dimly lit room. The human brain is an extraordinarily powerful pattern recognition system, tuned by millions of years of evolution to detect faces and figures and meaningful shapes in the environment. Because for most of our evolutionary history, the ability to quickly identify a face or a figure in the foliage could mean the difference between safety and danger. Clouds are perfect objects for pareidolia. They have no fixed shape. They are close enough to feel real, large enough to project onto, varied enough to offer something different every time you look, and they are always moving, slowly transforming from one shape into another, so that the horse becomes a mountain, becomes a sleeping figure, becomes something with no name at all. There is a passage in Shakespeare's Antony and Cleopatra where the dying Antony, his world dissolving around him, describes the clouds. Sometimes we see a cloud that's dragonish, a vapor sometime like a bear or lion, a towered citadel, a pendant rock, a forked mountain, or blue promontory with trees upon it. The cloud shapes come and go as Antony lists them, the mind reaching for a solid thing and finding only vapor, the solid world itself becoming as insubstantial as cloud. Shakespeare uses the cloud's shapelessness as an image of the dissolution of identity, of the self becoming as formless as vapor. It is one of the most powerful uses of cloud imagery in all of literature. And it works because every member of the audience has experienced exactly what Antony describes. The mind finding shapes in clouds, shapes that are there and then not there, real and then dissolved. The imagination and the cloud have a long relationship. They share certain properties. Both are shapeless, or rather, both take whatever shape the moment and the observer give them. Both are in continuous motion. Both are made of something that seems substantial, thought, water, but is in practice almost impossibly light and ephemeral. The cloud and the thought both arise from conditions, develop according to their own internal logic, and eventually dissolve, leaving behind no trace of their particular form. In meditation traditions across the world, the cloud has been used as an image of the nature of thought itself. In Tibetan Buddhist practice, thoughts that arise during meditation are sometimes described as clouds passing through the sky of awareness, arising, existing briefly, and dissolving without being grasped or pushed away. The sky of awareness is always there, always clear, always unchanging, regardless of what clouds pass through it. The clouds are not the sky. The thoughts are not the self. This metaphor, simple and precise, has been guiding meditators for centuries, offering a way to relate to the arising and passing of mental events that is both gentle and liberating. The practice of cloud watching, of lying on one's back in the grass and simply observing the sky, is itself a form of meditation. Though most people who have done it would not call it that. It requires nothing, no technique, no posture, no instruction. Simply the willingness to be still and let the eye follow the slow movement of the clouds above. The mind quiets, not because it is forced to, but because there is something about watching clouds that naturally slows the pace of thought. The clouds do not hurry, and in the company of something that does not hurry, the mind gradually stops hurrying too. Children know this instinctively. The child lying in the summer grass, pointing at clouds and calling out the shapes they see, the rabbit, the castle, the face of someone they know is engaged in something that looks like play, but is also something more. It is an early and spontaneous form of contemplative attention, present moment awareness, as the meditation teachers would call it, directed at something beautiful and impermanent and requiring nothing. Many people remember cloud watching as one of the purest pleasures of childhood, a pleasure that requires no equipment, no skill, no money, no preparation. Just the ground beneath you and the sky above, and the slow parade of cloud shapes drifting overhead. It is a pleasure available to any person in any era, at any moment of their life. Yet, somehow the adult world tends to crowd it out, filling the spaces where it might naturally occur with tasks and screens, and the insistence of the immediate. The imagination has always used clouds as material, not just by finding shapes in them, though that is where it begins, but by building entire structures of feeling and association around them. The particular feeling of a certain kind of cloud on a certain kind of afternoon. The weight of thundercloud building at the horizon on a hot August day. The particular lightness of a sky scattered with small cumulus after rain. The intimacy of low cloud pressing down on a winter landscape. These are not just meteorological observations. They are emotional experiences, inseparable from the memories and associations they carry. Clouds carry memory, not in any literal sense. A cloud does not remember anything, but we remember them. Or rather, we remember the states of mind and feeling associated with particular kinds of cloud and sky. The smell of rain before it falls petrichor, the compound name given to the particular scent of rain on dry earth, produced by geosmin released from soil bacteria, is inseparable from the look of a particular dark cloud hanging low over a dry summer landscape. The quality of light under an overcast November sky is inseparable from the feelings, sometimes melancholy, sometimes strangely comforting, that such light tends to produce. The Japanese have a concept, mono no aware, that translates roughly as the pathos of things, or the gentle sadness of impermanence. It is the feeling evoked by things that are beautiful precisely because they do not last. The cherry blossom that falls within a week of opening, the moment of sunset that is gone before you have quite finished looking at it. Clouds are perhaps the quintessential objects of no aware. They are beautiful. They are here. And they are already becoming something else, already dissolving, already gone. There is a pleasure in watching the dissolution of a cloud, in choosing a particular small cumulus on a clear afternoon, and watching it thin and fray, and gradually disappear, the edges softening, the white dwindling, the blue reclaiming the space the cloud once occupied. It is one of the quieter pleasures of sky watching, requiring patience and a certain willingness to witness something ending. The cloud does not resist its dissolution. It simply thins and thins and is gone without drama, without protest, without any sense of loss on its own part. This quality of cloudness, this complete acceptance of its own impermanence, this perfect willingness to change form and disappear, is something the human imagination has returned to again and again in poetry and philosophy and spiritual practice, as though there were something to be learned from it, something about how to hold the present moment lightly, something about how to let go of what is already in the process of becoming something else. The cloud exists completely in the present tense. It is not the cloud it was 5 minutes ago. It will not be the cloud it is now in 5 minutes' time. It is entirely and exclusively what it is right now. This shape, this density, this particular arrangement of water, droplets in this particular portion of the sky, and then it is something else, equally completely and exclusively itself. There is a whole branch of philosophy, process philosophy, associated most closely with the 20th century thinker Alfred North Whitehead, that argues that reality is fundamentally constituted not of stable objects, but of processes, events, becomings. In this view, the cloud is actually more fundamental than the rock, because the cloud wears its processual nature on its face, makes no pretense of stability or permanence, is visibly and continuously in the act of becoming. rock only appears more stable. On the time scale of geology, it is no more permanent than the cloud. It is simply a slower cloud. This is perhaps too philosophical for the hour. Let us return to something simpler. Clouds have inspired music in ways that go beyond any particular composition or composer. There is a quality that certain kinds of music share with certain kinds of sky. A quality of spaciousness, of something large and unhurried, of patterns that repeat with variation, of a mood that is not quite any single emotion, but holds several emotions simultaneously in a kind of suspension, the slow movement of Schubert, the long, unresolved harmonies of late Brahms, the drifting, non-directional pieces of Eric Satie, who called some of his compositions gymnopedies, a word that suggests slow, ceremonial movement, unhurried, going nowhere in particular. Brian Eno's ambient music, explicitly designed to be as ignorable as it is interesting, to merge with the environment rather than demanding attention. His 1978 album, Ambient One, Music for Airports, has a particular quality of slow cloud movement, sounds forming and dissolving, patterns emerging and fading without resolution. There is music that sounds like fog. There is music that sounds like the light coming through a gap in overcast. There is music that sounds like the particular quality of silence that follows thunder. Music borrows from weather, from clouds and sky and atmosphere, not necessarily deliberately, but because the qualities of sound and the qualities of light share something at the level of how they affect the nervous system, how they create states of awareness and feeling that are below the threshold of rational description. Dreams, too, borrow from clouds. The logic of dreams, the way scenes dissolve and reform, the way identities blur and exchange, the way a hallway becomes a field, becomes a room you knew in childhood, becomes somewhere with no name, has something of the character of clouds. The dreaming mind moves through images the way a time lapse of clouds moves across the sky, with a logic that is not quite narrative, but is not quite random either, following some internal principle that is felt rather than understood. People who have difficulty falling asleep sometimes find that watching clouds or imagining clouds helps. Not because clouds are boring, though they are quiet, but because the slow movement of clouds, the gradual shifting of shapes, the absence of any resolution or conclusion or narrative endpoint gives the mind something to follow that does not require any effort or any decision. The mind can follow the cloud for a while, and the following is enough. The following is, in fact, a kind of letting go. There are guided meditations that use cloud imagery specifically for this purpose, inviting the listener to imagine lying on warm grass, looking up at a sky of gentle clouds, watching them drift and change, attaching each passing thought to a cloud, and watching it drift away. The imagery works because it is so familiar, so comfortable, so completely unthreatening. The cloud carries the thought away without drama. The sky remains. The next cloud arrives. The next thought arrives with it and is carried away in turn. Tonight, you have traveled through a great deal of sky. You have followed the atmosphere from its surface layers to the edge of space. You have visited clouds on other worlds and colors produced by the physics of light. You have heard about the history of cloud watching and the science of droplet formation and the extraordinary variety of rare and strange clouds that the atmosphere occasionally produces. And now the sky of this evening is simply itself. Whatever it is above you right now, however many clouds or few, whatever the particular quality of the darkness outside your window, you do not need to watch it. You do not need to name what is there. You do not need to remember any of the things you have heard tonight, or understand them more completely than you already do. Simply let the sky be above you. Let it be large and dark and patient. Let the clouds, if there are clouds, drift wherever the wind is taking them. Let the atmosphere breathe its slow and enormous breath above the rooftop, and let your own breath slow just a little more in the company of something that has always been there, has always been drifting, always been changing, always been quietly, continuously, unhurriedly present above every place you have ever been, and every place you will ever be. The clouds have no destination, and tonight neither do you. The atmosphere has been here for a very long time, not always in its current form. The atmosphere of the early earth was very different from the one that surrounds the planet tonight. The young earth, more than 4 billion years ago, had an atmosphere composed largely of hydrogen and helium, the lightest gases, the most abundant elements in the universe. But these were gradually lost to space, too light to be held by the planet's gravity over geological time. What replaced them came from within, from the volcanic outgassing of the interior of the earth, which released carbon dioxide, nitrogen, water vapor, sulfur dioxide, and other gases in vast quantities over hundreds of millions of years. That early atmosphere was not breathable. There was almost no oxygen in it. Oxygen is not a gas that accumulates naturally in an atmosphere without a very specific kind of help. And that help, when it came from life somewhere around 2.5 billion years ago. An almost incomprehensible span of time before the present. A time when the most complex things on Earth were single-celled organisms living in the shallow seas. A particular kind of bacterium evolved the ability to use sunlight to split water molecules and build organic compounds from carbon dioxide. This process was photosynthesis, and one of its byproducts was oxygen for hundreds of millions of years. The oxygen produced by these early photosynthetic organisms was absorbed by the rocks and minerals of the ocean floor. Iron dissolved in the seawater reacted with the oxygen and precipitated as iron oxide, the rusty red mineral that forms the great banded iron formations found in ancient rocks around the world. But eventually, the capacity of the rocks to absorb oxygen was saturated, and the oxygen began to accumulate in the atmosphere. This accumulation, sometimes called the Great Oxidation Event, was, in geological terms, a catastrophe. Oxygen is highly reactive. It is toxic to many forms of life that had evolved in its absence. The organisms that could not tolerate oxygen were driven to the margins, to the deep sea, to the sediments, to environments where oxygen could not reach, and the organisms that could tolerate oxygen. And eventually, that could use oxygen to release energy far more efficiently than any anaerobic process allowed, thrived and diversified, and eventually gave rise, over the following billions of years, to every complex living thing on Earth, including you. The oxygen in the breath you are taking right now, the quiet, slow breath of someone close to sleep, was put there by life, by billions of years of photosynthesis, by the patient work of plants and algae and cyanobacteria, building oxygen molecule by molecule from water and sunlight. The atmosphere you were born into is a biological creation, as much as it is a geological or chemical one. It has been shaped by life, just as life has been shaped by it. This is one of the most profound things about the atmosphere. It is not a passive backdrop to the story of life on Earth. It is a participant. It has been changed by life, and it changes life in return, in a continuous, billions of years old conversation between the living and the non-living, between the biological and the chemical, between the ocean and the sky. The atmosphere tonight is approximately 78% nitrogen and 21% oxygen, with small amounts of argon and carbon dioxide, and water vapor and trace gases. This composition has been broadly stable for hundreds of millions of years, stable enough for the extraordinary diversity of life that covers the planet to have evolved within it, adapted to it, dependent upon it in ways so fundamental that most living things could not survive even small changes to its composition for more than a few minutes. And yet stable does not mean unchanging. The atmosphere is always in motion, always redistributing itself, always cycling its components through the great biogeochemical cycles: the carbon cycle, the nitrogen cycle, the water cycle, that move matter between the atmosphere, the ocean, the land, and the bodies of living things, returning it and redistributing it, and making it available again in forms that living things can use. Carbon dioxide is exhaled by every breathing creature on Earth, produced by the decomposition of organic matter, released by the burning of fossil fuels, and emitted by volcanoes. It is absorbed by plants and algae through photosynthesis, dissolved in the ocean, incorporated into the shells of marine organisms that sink to the seafloor when they die and become, over geological time, limestone rock. The carbon cycle moves carbon continuously between the atmosphere and every other reservoir on the planet, maintaining the concentration of carbon dioxide within a range that has, for most of the Earth's history, kept the planet's temperature within the bounds that complex life requires. Nitrogen cycles from the atmosphere into the soil through the action of specialized bacteria that can fix atmospheric nitrogen, convert the stable nitrogen gas molecule into forms that plants can absorb and use to build proteins. These fixed nitrogen compounds move through food webs, passing from soil to plant to animal to decomposer, and eventually returning to the atmosphere as nitrogen gas through the action of denitrifying bacteria. The nitrogen in the protein molecules of your body was once atmospheric nitrogen, fixed by a bacterium in the soil of some field or forest, incorporated into a plant, eaten by something, and eventually, through many steps, incorporated into you. The oxygen cycle is driven primarily by photosynthesis and respiration. The complementary processes by which life builds organic molecules using sunlight and oxygen is consumed in releasing the energy they contain. Every molecule of oxygen in the atmosphere has been produced by photosynthesis. Every molecule of carbon dioxide in the atmosphere that was not produced by geological processes has been produced by respiration or combustion, by the reverse of photosynthesis, the burning of the organic compounds that photosynthesis created. These cycles are so vast and so continuous that they are invisible in daily life. The oxygen concentration of the atmosphere does does not noticeably fluctuate from day to night, from season to season, even though photosynthesis is running faster in the day than at night, faster in summer than in winter. The system is too large, too well buffered for the daily and seasonal variations to produce measurable changes in the composition of the air you breathe. It simply remains 78% nitrogen, 21% oxygen, steady and generous and completely reliable. This steadiness is one of the great gifts of the atmosphere, not its drama, not the thunderstorms and the blizzards and the hurricanes, which are real and impressive and important, but its steadiness, its day after day, year after year constancy. The air is there when you wake up. It was there when you fell asleep. It will be there in the morning. It has been there every morning of your life, and every morning of every human life before yours, back through all of history, all of prehistory, back to the first breathing creatures in the first ancient seas. The constancy of the atmosphere is so complete that it has no presence in ordinary experience. You do not notice the air because it is always there. You do not feel grateful for oxygen in the way you might feel grateful for a meal or a warm bed, because oxygen has never been absent in your experience, never withheld, never scarce. It is simply there, always, without condition or interruption. The atmosphere asks nothing of you. It does not require acknowledgement or gratitude. It does not need to be thanked or tended or maintained by any individual effort of yours. It simply continues, cycling and breathing and moving and redistributing, maintaining its composition and its pressure and its temperature with a patience and a continuity that makes all of human history look brief. There is something in this constancy that is, if you let yourself feel it, profoundly comforting. Not the comfort of safety from danger, though the atmosphere does provide that, shielding you from the ultraviolet radiation that would otherwise damage your cells, maintaining the temperature range that allows your chemistry to function, providing the oxygen that every cell in your body depends upon. All of that is real, and all of it is quietly happening right now, without any effort on your part. But the deeper comfort is simpler than that. It is the comfort of something that does not change. Something reliable, something that will be there when you wake up, as it has been there every time you have ever woken up, as it was there before you were born, and will be there after everything that is currently of concern to you has resolved itself one way or another. The atmosphere breathes. It has always breathed. It will breathe long after this night is over. And within that breath, that slow, planetary, billions of years old breath, your own smaller breath is happening, rising and falling, bringing oxygen to the blood, carrying the carbon dioxide away, participating in the most intimate and continuous way possible in the same cycle that connects every breathing thing on earth. You are not separate from the atmosphere. You are continuous with it. You are breathing it, and it is, in a sense, breathing through you. The oxygen moving from the sky into your lungs, into your blood, into every cell, doing the quiet chemical work that keeps you alive, and then returning, transformed, to the air around you. The boundary between you and the atmosphere is the boundary of your skin. And even that boundary is porous, permeable, continuously negotiated breath by breath. You are, at this very moment, exchanging molecules with the atmosphere, trading carbon for oxygen, participating in the most ancient and continuous transaction that life on Earth has ever engaged in. Breathe in. The atmosphere gives. Breathe out. You give back. This exchange has been happening every moment of your life, and the lives of every creature that has ever breathed for billions of years. It is so ordinary that it requires an effort of imagination to feel it as the extraordinary thing it actually is. But tonight, in the quiet and the dark, with the day's ordinary urgencies set aside, perhaps you can feel it, just a little. The breath coming in, carrying something the sky has made. The breath going out, returning something the sky will use again. The clouds above you tonight are part of this same exchange. They are water drawn up from the ocean, carried inland on the wind, gathered into visible form by the cool cooling of the air, waiting to return to the surface as rain. They have been doing this for as long as there has been an ocean and an atmosphere. They will continue doing it long after any building or road or town that exists beneath them has returned to dust. The clouds drift, the atmosphere breathes, the water cycles, the oxygen circulates, the nitrogen fixes and releases. The carbon moves through its vast, slow pathways from atmosphere to ocean, to rock, and back again. All of it happening right now, above you and around you and through you, completely regardless of whether you are awake or asleep, thinking about it or not thinking about it, aware of it or lost in the particular, immediate concerns of a human life. The atmosphere does not need your attention. It does not require you to stay awake to monitor it. It has been managing itself with extraordinary competence for longer than there have been any minds on this planet to appreciate it. You can let it do that tonight. You can release the day's accumulated attention, the things watched, the things noticed, the things thought about and worried over and considered from different angles, and simply rest within the envelope of air that holds you, that has always held you, that is holding you right now with the same steady, generous, completely reliable pressure that it has maintained every moment of your existence. The atmosphere is large enough to contain your sleep. It has been doing so every night of your life. The clouds are drifting in whatever direction the wind is taking them. The water cycle is turning. The oxygen is moving. The pressure is what it is at this latitude and this altitude, pressing gently and evenly on every surface, as it always has, as it always will. And you are part of all of it, breathing, warm, continuous with the air and the sky and the slow planetary systems that make this particular kind of life possible on this particular world. There is nowhere else to be. There is nothing else to do. The atmosphere has everything in hand. Rest now within it. Let your breath slow to its own natural rhythm, the rhythm it finds when nothing is required of it, when there is no effort, no task, no wakefulness to maintain, the rhythm of a body at peace with the air around it, taking what it needs, releasing what it doesn't, perfectly balanced within the oldest and most patient system on the planet. The clouds are above you. The atmosphere is around you. The night is quiet. And you are here within all of it, small and warm and very still. We have traveled a long way tonight, not in miles, not in any direction that a compass could point to, but through something vast and real and present all the same, through the atmosphere that surrounds this planet, through the science of clouds and air and water and light, through the history of how human beings have looked at the sky and found it beautiful and meaningful and worth knowing. We began at the surface, at the place where you are right now, lying still, breathing slowly. And we moved upward through the layers of the atmosphere, from the turbulent, cloud-filled troposphere to the ozone-rich stratosphere, through the cold and quiet mesosphere, into the vast, near-empty thermosphere, where the aurora shimmers and the space station moves silently overhead. We watched clouds form from invisible water vapor, gathering around particles of desert dust and ocean salt, and the ash of distant fires, building themselves from nothing into something visible, something luminous, something large enough to cast a shadow on the ground below. We learned the names that Luke Howard gave to the clouds in his quiet London drawing room more than 200 years ago. Cirrus, cumulus, stratus, nimbus, 4 Latin words from which an entire vocabulary of sky was built. We visited the low clouds that press close to the ground, and the middle clouds that arrive before the rain, and the high ice crystal clouds that catch the light of sunrise and sunset and transform it into colors that make people stop whatever they are doing and simply look up. We spent time with fog, the cloud that comes all the way down, that fills the valley and softens the morning and makes the world intimate and small and quiet. We followed the wind across oceans and over mountain ranges, feeling how it moves from high pressure to low, how the rotation of the earth bends it into spirals, how it builds the great weather systems that travel across the mid-latitudes, bringing rain and clearing, and the particular freshness of air after a storm. We stood inside a cumulonimbus and felt anvil spreading outward at the tropopause in a great, flat canopy of cirrus. We watched the rain form, droplet by droplet, through the patient physics of the burgeoning process. Ice crystals growing at the expense of supercooled water until they were heavy enough to fall. We saw the snowflake as a diary of its own formation, recording every temperature and humidity it encountered on its journey through the cloud. We traveled outward from the earth and visited the clouds of other worlds. The sulfuric acid veils of Venus, the water ice wisps of Mars, the great ammonia cloud bands of Jupiter with their centuries-old storm, the methane clouds of the distant ice giants, the iron and silicate rain of worlds orbiting other stars, and we came back to our own clouds with a renewed sense of their particular preciousness. Clouds made of water, falling as rain onto a world where that rain sustains life. We watched scientists send instruments into the atmosphere on balloons and aircraft and satellites, and in the controlled environment of cloud chambers, gathering measurements that slowly, carefully, painstakingly improve our understanding of how clouds work and how they will change in a warming world. We understood that clouds are not just decoration on the sky. They are active participants in the energy balance of the planet, reflecting sunlight and trapping heat, cooling and warming in complex and sometimes opposing ways. Their future behavior one of the great open questions of climate science. We wandered through the long history of how human beings have related to clouds, through the rain prayers of agricultural societies, the cloud imagery of ancient religious texts, the cloud spirits of indigenous traditions, the cloud paintings of Constable and Turner, the cloud poems of Kalidasa and Shelley, and the haiku masters of Japan. We understood that the urge to look at clouds and find meaning in them is not new, is not unique to any culture or any era, but is one of the oldest and most universal of all human impulses. We learned the colors of the sky, why it is blue at noon and gold in the afternoon, and crimson at sunset and silver in the fog, why the rainbow arcs across the rain in the colors it does, Why the belt of Venus glows pink on the eastern horizon at dusk. Why the green flash appears for a single brilliant instant at the very last moment of the setting sun. We understood that the sky's colors are not its own, but borrowed from the light that passes through it, shaped and sorted by the interaction of photons with the molecules and particles of the air. We sat with the clouds of the imagination, with pareidolia and poetry and dream logic, with the Japanese concept of mono, no aware, and the Buddhist image of thoughts as clouds passing through the sky of awareness. We understood that the human mind and the cloud have always had something in common, that both are shapeless and continuous, and always in the process of becoming something other than what they were. And finally, we rested with the constancy of the atmosphere itself, the billions of years old steadiness of the air, the oxygen given by life and taken back by life, the nitrogen cycling through soil and plant and creature and sky, the water moving endlessly between ocean and cloud and rain and river and ocean again. We felt how the atmosphere is not something separate from us, but something we are continuous with, breathing it, exchanging molecules with it, participating in its ancient cycles with every breath we take. All of that is still happening. Right now, as your eyes are closed or closing, as your breathing has settled into its own natural rhythm, as the weight of the day has receded and the body has found its way to stillness, the atmosphere is doing everything it has always done. The clouds are forming somewhere above you. Water vapor is condensing onto invisible seeds of dust and salt. Droplets are gathering, thickening, drifting on the slow air. Somewhere, rain is falling. The patient, unhurried rain of a cloud that has finally carried its water to the right place, at the right temperature, above a landscape that needs it. The wind is moving somewhere, not necessarily here. Perhaps the air outside your window is perfectly still tonight, the curtains unmoving, the leaves of the trees held motionless in the dark, but somewhere the pressure gradient is acting. Somewhere the air is flowing from high to low. Somewhere a front is advancing or retreating. Somewhere a sea breeze is dying as the land temperature equalizes with the ocean. The atmosphere is doing its work. The water cycle is turning. The oxygen is circulating. The planet is exchanging energy with the sun, and with the cold of space, finding its balance, maintaining the narrow range of temperature and composition within which you and everything else that breathes can exist. None of this requires anything of you tonight. You have done your part simply by being here, by breathing, by radiating your small warmth into the air around you, by participating in the cycles that you were born into and that have sustained every generation before yours and will sustain every generation after. You have also done something else tonight. You have paid attention. You have followed the science of clouds and atmosphere through all of its layers and all of its variety, from the microscopic physics of a single condensation nucleus to the planetary scale of the global circulation, from the intimate closeness of fog on a morning street to the distant strangeness of clouds made of iron on worlds orbiting other stars. You have given the sky the attention it deserves. And now you can let all of that settle. You do not need to hold it. It will be there tomorrow and the day after, in the clouds that form above you and the weather that moves through your life and the quality of light on every morning you wake into. The atmosphere will remind you of everything you have heard tonight in its own patient and continuous way, simply by being there. Let the facts go gently, the way a cloud thins at its edges in warm, dry air, not all at once, not with any effort, simply releasing what it was holding, becoming lighter, becoming translucent, the blue of the sky beginning to show through. Let the words go too. They have done their work. They carried you here to this place of stillness and slow breathing, to this late hour when the mind is soft and the body is heavy and the world outside is dark and quiet. The clouds are above you. They have always been above you. They will always be above you, not these particular clouds, which will be gone by morning, transformed by the wind into something new, but clouds. The process of clouds, the atmosphere making visible its own invisible motions, writing its temperature and humidity, on the sky in shapes that drift and change and dissolve and form again. Drift with them now. You have been learning about clouds all evening, and now you can simply be beneath them. Beneath whatever is up there tonight, cloud or clear sky, or something in between. It does not matter, simply beneath the atmosphere within it, held gently by the same pressure that has always held you, breathing the same air that has always sustained you. The sky is very large and very patient, and you are small and warm and very, very still. The breathing continues, slow and steady, the way the atmosphere breathes, not in any hurry, not going anywhere in particular, simply in and out, in and out, the most ordinary and the most essential motion of a living thing at rest, in and out. The clouds drift, the atmosphere breathes, the water cycles, patient and ancient and completely reliable. And you are here within all of it, as you have always been held, sustained, continuous with the sky above, and the air around, and the breath that moves through you like a slow, gentle wind through an open window on a quiet night. There is nothing more to know tonight. There is nothing more to do. Simply rest now within the atmosphere, within the clouds, within the slow and patient breath of a planet that has been breathing for 4 billion years and is breathing still. You are part of that